Yes.
I want
Morning.
to test my screen sharing.
Yes, go right ahead. I think you should be a co-host. And that should just let you screen share.
Can I also try the screen sharing?
Yes.
Can you see it now?
Yes, looks good.
Okay, I will stop sharing then.
Your mic's a little bit quiet.
That's probably better this way.
Yes, that sounds much better. Thank you.
Okay.
That looks good as well.
But it is not full screen. Yes,
That's better.
Now it is.
Okay. I will give the first talk.
Liangtian, I will introduce you. Could you tell me how to pronounce your name correctly?
Hi, Catherine. It's Tyrone, yeah?
Yeah, hello.
How's it going?
Good.
Good. I just wanted to check, am I chairing from the start of the session?
I realized I had asked from Joshua Morman's talk, but if you would like to chair from the very beginning, that would be great as well. I wasn't sure if you, yeah, whichever you're planning on. I can introduce the first talk if you want, or you can chair from the very beginning.
Yeah, I'm happy to do, yeah, from the beginning. That's fine with me. Unless there was something you wanted to start off with from your side.
No, there aren't any particular announcements today.
Okay, great.
Oh, and something I had forgot to remind yesterday, but if you can ask speakers what time they want a reminder that they're running out of time. We didn't really get a lot of live Q&A time yesterday because speakers mostly use the whole time for their talk. And so if you can encourage, it is up to the speaker how they want to use the time, but if you can encourage them to leave a couple minutes for Q&A, that would be good.
Okay, sure. I'll do my best.
Hey everyone, at Ryan, can I test my screen sharing quickly, please?
Yes, go try it right now.
Screen. Are we live?
Yes, we are, and I think we can see I think we can see your screen.
If I go into presenter mode, can you still see it?
Yes, we can.
Okay, sweet. All right.
Okay, should we get started?
Yeah, I think we can. I think it's now sort of 4:15 in here in South Africa, and I think that aligns with the first session. Catherine, I think you said there's nothing from your side that you wanted to announce or anything, so I can just kick off.
Yes, sounds good.
All right. Yeah, good morning, good afternoon, good evening to everyone. Welcome to day 2 of the first virtual Casper workshop. We've got a full morning, evening, or afternoon of talks lined up, depending on where you are. And I'm going to jump straight into it in the interest of time. Just a few housekeeping things. A reminder that conversations are continuing on the Slack channel. So if you haven't joined the Slack channel, please do that. During the presentations, feel free to post your questions that you have for the speaker in the chat, and I will monitor that. Yeah, and feel for questions to pose to the speaker. All right, our first speakers this evening are Lin Xu and Lin Zhao. I'm hoping I pronounced that correctly. Here to talk to us a bit about some new instruments that they've implemented on the Snap2 board, the beamformer for the Jian Lai cylinder array and a correlator for the heliograph array. So over to you.
Okay.
All right, just before you guys begin, how long into your talk would you like me to give you a warning for time?
Okay.
Should
Okay.
be 10 minutes.
Sorry. I will share my screen. Can you see my screen?
Yep, I can see that.
Okay. Thanks for the chairman's introduction. Hi everyone, I'm Liangtian Zhao, come from the Institute of Automation, Chinese Academy of Sciences, and I will introduce the applications based on Snap2. And my colleague, Dr. Lin Xu, will help me answer your questions. My presentation today is mainly divided into 3 parts. Firstly, I will briefly introduce several IP platforms that we have designed. Secondly, I will focus on the 2 major applications based on the above platforms. Finally, I will show you several newly developed data processing server products. Snap2 is a powerful and reliable FPGA platform. We have applied it in many projects. We have also delivered its board to many partners. Here is its main features. If you are interested, you can download the detailed manual of Snap2 from Casper's website or our website. Snap2 is very flexible to use. It can expand different ADC cards through 2 FMC connectors and can also expand different variables through ZD+ connector to provide diverse data interfaces. We have equipped Snap2 with a variety of ADC cards from 250 meg SPS at 8 bit to 6.4 gig SPS at 12 bit to meet different signal acquisition requirements. In addition to Snap2, we also provide other FPGA platforms. Compared with Snap2, CESI K7 has a higher cost performance ratio and can be connected to the server through a PCIe connector. And the second board supports 8 channels of ADC. The Snap3 board mainly upgrades FPGA from Context Autoscale to Vertex Autoscale Plus series. Snap2M can support 64 GB DDR4 cache, mainly used for data processing. Our next generation platform based on IF-SOC is also being designed, and it is expected to provide evaluation board in December this year. For ease of use, 3 FPGA platforms and 3 ADC cards have been imported into the Jasper tool flow. Based on the above FPGA platforms and the ADC cores, we have designed a series of module-level products, which can be widely used in all aspects of signal acquisition, processing, transmission, and storage. In the last 2 years, we have applied the above products to 2 projects. The first project is the meter-decameter radioheliograph correlation system located in Vinand in Mongolia, China. As shown in the figure, the system consists of about 100 antennas forming a telescope array with a longest baseline of 3 kilometers. The system performed spectral imaging observations with high time, frequency, spatial resolution for various phenomena from the source of the solar burst. This is the digital correlator system, and its main features: 202 input channels, sample rate 250 meg SPS at 12 bits, and the FFT channels 128. The digital correlator system is divided into 5 modules: clock and trigger, F engine, X engine, the Ethernet network switch, the data storage disk array, and the control and display software. The implementation process of the correlator faces many challenges. The first challenge is how to achieve synchronization between 202 input signals. Here are some methods we used. First, selecting ADC chip with synchronization function. For example, ADS 5407. Secondly, equal length design of hardware circuit, especially for data and clock. Thirdly, timing adjustment for data and clock using iDelay in FPGA. And lastly, synchronize the configuration, reset, trigger, and data upload between boards by using multifunction process. Finally, synchronization can be achieved automatically after each power on, and the delay difference between channels is less than 50 picoseconds. The second challenge is the parallel implementation of the correlation algorithms. The X engine module consists of 32 snap-to boards. Parallel computing between snap-to boards based on frequency channels, and each board realizes the correlation of 4 frequency channels. Parallel computing within snap-to board based on data blocks. Each block contains 8 input data channels and the correlation of the same color data blocks. You reuse the same computing unit. The correlation of different color blocks will be implemented by different computing units. The third challenge is how to achieve efficient data exchange between F engine boards and the X engine boards to avoid data congestion and packet loss. Firstly, it's necessary to design the packet data and IP rules to ensure correct data exchange. Secondly, it's necessary to ensure the traffic balance of switching network by pooling, sending, and receiving between source IP and the destination IP. After a long-term testing, the average transmission delay using the flow balancing solution has been reduced by 96.9%. The structural design of the system is also very important, which need to fully consider the power consumption, heat dissipation, electromagnetic shielding, and the maintainability. The figure shows the chassis design of X engine and the F engine. This is the overall installation of the system. A total of 2 F engine chassis and 4 X engine chassis, as well as other switches and storage devices, are placed into cabinets. The second project is the Tianlai cylindrical array digital beamforming system located in Balikun, Xinjiang, China, which is mainly used for searching FRB. The system adopts FB architecture. F engine is responsible for converting the real-time input signal from time domain to frequency domain, and the B engine is responsible for beamforming. Its main features: 196 input channels, intermediate bandwidth from DC to 100 MHz, sample rate 250 FPS at 12 bits, and the number of beams 96. The digital beamforming system is mainly composed of 4 functional modules: F engine, B engine, the switching network, clock and trigger, and the display control software. F engine is implemented by FPGA platform, which is responsible for signal processing. For the consideration of system cost and easy development, B engine module is implemented by GPU servers, which is responsible for beamforming. This is the system control software interface. It can remotely control the power on and the power off, start and stop, and monitor the status of the equipment. The data monitoring interface can view the data snapshot of each stage in a graphical way. The GPU server monitoring interface can view the resource utilization and the running status of each GPU computing node. This is the actual installation of the system, including an F engine chassis, 12 GPU servers. Each server consists of 2 independent computing nodes. In order to reduce the cost of the system, the common desktop computer motherboard is selected, and the network card and the GPU card are expanded through the PCIe riser card and the M.2 interface.
Sorry, Liangtian, you've got about 3 minutes left.
Okay. In response to the high-performance computing requirements of the astronomical data processing, we have developed 2 data processing servers. One is the high-performance computing server, and the second is the computing accelerated expansion server. The first server can provide 8 PCIe slots, and the second server can provide 16 slots. Each server can plug in computing cards, such as FPGA card and GPU card, and supports the virtualization of computing resources. Using the above FPGA platforms and servers, a general array signal acquisition and processing system can be constructed, including ADC acquisition array, FPGA processing array, FPGA or GPU computing accelerating card, and disk storage array. Finally, the advertising time. If you are interested in these products, you can visit our website for more information. Okay, that's all. Thank you.
All right, thanks, Liangtian. Yeah, I think very interesting talk. There was one question from Catherine, but I believe your colleague might have already answered it. But I'll just read it out for everyone's sake. So Catherine was asking, what is the maximum timing delay that you had to correct for when synchronizing? And the answer was roughly 20 microseconds. That was corrected for. I don't know if you want to add to that.
No.
Okay. All right. Thanks, Liangtian and Linshu for fielding the questions. All right. Then next speaker or speakers again that we have are from Perspector Labs, and they are going to be speaking about the GNU framework that we heard about yesterday, the GNU radio framework, in this case for using it for heterogeneous systems. And the speakers are Bastian, Bloessl, and Joshua Morman. So over to you guys.
Hello, everybody. Yeah, thank you very much for the chance to talk a bit more about GNU Radio and our ongoing efforts to rewrite core parts of the GNU Radio SCR framework. We are Bastian Bloessl from TU Darmstadt, and I'm giving this talk with Josh Morman from Perspector Labs, and we are both involved in the GNU Radio project. Do you also hear this static, or is it just me?
No, I hear it too.
Okay, that's me. I apologize. I will keep muted as long as I can.
Now it's better. Yeah. Thanks. So we are both involved in the GNU Radio project, and particularly interested in the runtime environment, which is the component of the system that manages the data flow and coordinates execution of these DSP kernels. And Josh is, in addition, also the maintainers in some weeks or months. Yeah. So I have a one-slide introduction to GNU Radio, since you already heard about it. I want to keep it brief. It's an active open source project with a lot of contributors with a very different backgrounds, from ham radio to academia to industry, government, whatnot. And in essence, we are a real-time signal processing library. So it can basically create the software part of a software-defined radio. And for the context of this talk, can you go back? Yeah. So for the context of this talk, the two main properties are that we are historically, and still at the moment are, maybe a GPP-based SDR platform. So that means it's supposed to run on a normal general purpose processor. That means CPU, just a normal PC. And secondly, we're a general purpose SDR framework, which means that we're not really targeted towards a particular application or application domain, but we try to support everything as good as we can. Yeah, so I want to go a bit more into details about these two aspects. First of all, yeah, as I said, we are still a CPU-only framework at the moment, and I guess you've seen this graph in one shape or form, where you have time on the x-axis and application performance on the y-axis, and you see that, okay, obviously CPU is kind of a dead end. So when we started GNU Radio, just get better with time if you bought a new PC, but this kind of stopped. And if you want to stay relevant, for example, for high performance, state-of-the-art implementations, it's obvious that we have to go and have to have first-class support for GPUs, for FPGAs, and various kinds of co-processors. So I think this is just key to stay relevant if you want to continue to support state-of-the-art wireless applications. But then there's also another aspect which I wanted to quickly mention, because there are a lot of applications, in my opinion, that are very well in reach for CPU implementations. And since I come from a wireless networking background, so I picked a bit from this sector, like Open Interface, SRS-ROM. These are 4G implementations, basically. And actually, they are able to run on CPUs, but they don't use GNU Radio or really any other of the general purpose SDR frameworks. And I thought, why is that? And I think we're just, at the moment, we're not good enough. We are not flexible enough. We don't provide enough benefits to the people who use GNU Radio for that. And so I wondered, okay, what does it mean for the future of general purpose SDR frameworks? So what can we do to stay relevant also in the future? And yeah, we took a step back from our day-to-day incremental changes business and thought a bit bigger about how we can more or less reinvent the wheel. It's what we call GNU Radio 4.0. Yeah, so, and this is what Josh and me are currently coordinating and working on. And in very short, there are three main areas where we want to improve. First one is obviously also CPU will stay relevant, so we want to be more flexible there. Allow application-specific schedulers to be blocked in, for example, ones that also can provide delay guarantees, which we cannot do at the moment, where we basically do best effort, maximum throughput scheduling, let's say. Yeah, then the second area is this heterogeneous architecture, so we already touched on this. And then the third one is distributed DSP, where we have something in mind where signal processing, can you go back a slide? Yeah, well, signal processing spans between various nodes. And for example, it could DSP could have on different machines, for example, in the cloud or different PCs, and also control is distributed. And we're hopeful we kind of expand the application space where GNU Radio becomes interesting. This is also why we are basically here today to talk with you about it, like what are we currently doing, where we are, but hopefully also get your feedback, what you would, for example, need from your application domain to make GNU Radio more usable, more relevant also in this area. And yeah, today we want to focus completely on this heterogeneous architectures aspect, like integration of FPGAs and mainly GPUs, But there are also pointers to talks where we also talked about the CPU part of the thing. And this 2 talks, the links will also be on the last slide. And we're also happy to share the slides with you to get the links, which are currently not really helpful on the slide. Okay, so let's dive a bit more into this heterogeneous platforms. Today, what we ideally wanted to support is for example, shown here, where you have Xilinx boards that have an FPGA, an ARM, a real-time ARM core, GPU, and some DSP maybe. And the question is, how do you make efficient use of all this? And in the future, it will get even more complicated. I mean, there's the new, can we go to the next slide? Yeah, so there's the Xilinx Bloessl architecture where you have this programmable accelerators, and there's currently the DARPA DSSoC program also, which kind of takes it to the extreme, where you the idea is to create a processor where you can mix and match processing elements with different properties or with different purposes. But obviously, once you have this chip, you also need a runtime that makes efficient use of all these things. And this is what we are trying to here support through GNU Radio. So that's the vision. But now let's break it a bit more down of what exactly we're working at. So with current GNU Radio, we have only a single buffer implementation at the moment. And it's like in the figure here on the right, where we have a simple, we call it flow graph, where you create some data, you add something to it, and then you continue to process it in a sync, I don't know. And at the moment, we only have a fixed buffer implementation. It's really baked into the code and not easy to change. But now if you assume that this block would use an accelerator like a GPU, then there's no way to integrate it really properly in GNU Radio. So what you would have to do is, like, you get the data in the CPU buffer, you copy it again over to the GPU buffer, execute the kernel, get the data in the GPU buffer, and then copy it again back. And obviously, so we call it, it's this double copy problem, so it's currently not easy to change. It's a limitation of the framework, and that means even though there is RFNOC, there is examples that use the GPU or the FPGA with GNU Radio, they all have to have this constraint. They all kind of have this inefficiency that you cannot easily overcome, and which kind of like avoids the idea of using an accelerator for speed with this inefficiency. And that's the solution. I mean, is very obvious. It's very obvious on the slide. Obviously, this just copy it directly to this accelerator memory. Just do it, and it's simple. The idea is clear, and but we looked into this for quite a long time, and it's not so easy to really have proper support. And very fortunately, there's currently the SDR 4.0 project, which is a DARPA-funded effort, and it's executed by a team at Blacklinks who are working on just that. So they already made progress and have the first implementations that allows you to plug in really custom buffers in a GNU Radio flow graph. So that means there's a dedicated edge that allows you to directly write into accelerator memory. And to make this work, it's more like only the implementation, but you also have to find a good abstraction where how a general purpose interface to a buffer looks like. And this turned out to be always a bit the challenge in the past, because there were several proof of concepts for integrating one accelerator, but to generalize the concept and make it really usable in GNU Radio and in this framework, this was really not so easy. And so it's really nice that they really put a lot of effort into also making this a general applicable interface for GNU Radio. Yeah, and these efforts are in a separate repository that's also linked there if you are interested into this and want to follow the development. And the current status is that they basically created this abstraction for the buffer, and based on this abstraction also made another CPU implementation that better translates them to DMA or accelerator buffers, and are currently about to release these device-specific buffers. Can you go to the next slide? Yeah. So this basically sums it up again. From the state of the art where we are now, we obviously want to go to this support for writing directly into accelerator memory. And for this, we currently already have this CPU implementation for buffers, and we have a GPU implementation for this concept. And this is where Josh is now going to give more details on how this looks and shows you some first results from that. Okay, so.
All right. Thanks, Basti. Yeah, I apologize for my fan noise here. For some reason on this laptop, they put the microphone right next to the fans. So it's gonna kick up because Zoom seems to be processing heavy, but keep going. So GNU Radio 4.0. So the previous slide that Basti talked about is SDR 4.0, which is a specific DARPA effort. GNU Radio 4.0 is kind of the forward-looking re-architecting of GNU Radio generally, where we'd like to be, in the future, beyond a year from now. And we've taken, in order to get to GNU Radio 4.0, we've taken a clean slate approach. GNU Radio was started some 20 years ago. So there's a lot of things baked into GNU Radio that, if you were doing them today, if you were designing GNU Radio today, you wouldn't do it that way necessarily. So we want to have this flexibility to take these requirements of heterogeneity and modularity and build it into the framework from the ground up. So we're not entirely restricted from just the way GNU Radio is coded up today. So that's what, when we talk about GNU Radio 4.0, it is this ground up from scratch approach of rebuilding GNU Radio the way we want it to look. So for these custom buffers that Bastian described, SDR 4.0 is integrating this concept into the current GNU Radio code base, as a bridge. GNU Radio 4.0, we can look a little bit further downstream and make a cleaner interface here. So, the idea is that if you implement a block, let's say that you have a GPU accelerated block, one of these green blocks here, blocks are connected by edges, and on those edges live buffers, and the buffers are, the memory transfer in between each block. And if they're accelerated, you have to handle getting that memory, getting the data onto the device memory. So we need to specify somehow what these buffers are going to do, how they're going to get the memory in and out. So in a GNU Radio 4.0 flow graph, we tried to make this as simple as possible. So if you've got a flow graph, you're going to connect some blocks together. So say I've got the same thing. I'm going to get onto the device memory. So I'm going to specify a host to device buffer when I connect these blocks together. Now these two blocks are both already on the device memory. So we can just leave the data in the device memory and then we'll go back. So basically we're abstracting the ingress and the egress from the device memory to and from the device memory in this way. So there's a big benefit of if you're doing lots of, let's say, for example, GPU kernel launches, there's a benefit to leaving things in device memory. The penalty of copying things in and out of device memory is pretty heavy, especially if you're not doing very much in the kernel itself. So one of the beauties of GNU Radio, is you can break up your processing into these blocks of smaller things, and you can visualize the little things. You don't necessarily have to have some mega processing block where you've put all your stuff in there manually and then push all your data in, do all your processing through a bunch of kernels or one mega kernel. So, we can break things up, and you can even distribute those across, different resources. But if we look at benchmarking these, the benefit here is fairly obvious. If we have a bunch of, say, copy blocks, so say this GPU block is doing nothing but copying the memory in and out. It's just a mem copy, but in the GPU memory. If we have a chain of these and we benchmark it, there's a big benefit once we get rid of the ingress and egress penalty, leave things in the device-to-device memory when we have a lot of blocks, like 16 blocks. It's not a particularly interesting example because we're not really doing anything, right? These kernels are just copying data. And as we're doing more in the GPU blocks here, the benefit is going to decrease. But this gives us kind of the worst case. We can see, yeah, that's a lot of penalty for copying things in and out of the device memory. So when we talk about when we talk about device-to-device transfers, that's the real benefit here. So what we're looking for is challenging and interesting examples to show what this this new framework can bring compared to the current iterations of GNU Radio. So that's this conference, this workshop is very interesting, to me at least, in that, you know, we see how people are doing things in the radio astronomy world and how people are using accelerators. So, you know, if you have specific things that pop out at you that would be a good test here within this framework, yeah, please let us know, and let us know if you'd like to get involved and, you know, try out this framework with your particular application. You know, as interesting as, you know, copy blocks are, you know, there's much more interesting and relevant things that we'd like to do. Some other things, I guess, beyond the radio astronomy, you know, we want to look at various digital receiver implementations. Some of the challenges with current GNU radio is packet-based processing. So we're looking at using this framework to improve GNU radio on that end. And then other transport mechanisms, whether from the radio into the GNU radio processing blocks onto accelerators, or network transport blocks, and then other applications that just kind of naturally use accelerators, like machine learning applications. So looking at all sorts of things, but, you know, any ideas are very helpful here. So one application that we have looked at in the past few months is taking an ATSC receiver and accelerating some of the blocks in there that are the heavy hitters processing wise. So if we look at the ATSC receiver, so this graph up in the left-hand side, it's on a, you know, decently powerful laptop. You know, we can get to real-time streaming of ATSC video signals, but it's, you know, we're pushing it. So it's a good candidate possibly for GPU acceleration. The only problem is some of the blocks in this flow graph don't necessarily lend themselves to GPU acceleration. You know, they're loops and things that require sample-to-sample dependencies. So, you know, we can rewrite the signal processing to not do that as much. But, you know, if we're able to take some of the blocks that maybe can be done in parallel, like Viterbi decoder, then, and maybe some filtering, you know, this long pole, which is this FPLL, you know, if we're limited by cores, now by pushing things off onto the GPU, now we've opened up the flow graph to be able to accelerate. So like if we're limited to 2 cores here, we can't get even close to real time, which is processing 10 seconds of this file. But by adding the GPU acceleration on 2 of the blocks, in this case, you know, we get that down by 30% or so, the processing speed. So it's not accelerating the whole flow graph, but just kind of pulling some of the load off onto the GPU. One of the areas, so this not the focus of this talk, but one of the areas where we can have more optimization potential is applying different scheduling paradigms to our flow graphs. So latency might be a concern in some applications. So basically the GNU Radio scheduler right now, it's a one-size-fits-all thing. There's a CPU scheduler, and part of this reworking is to have modular scheduling so that we can apply you know, one type of scheduling policy to one part of the graph, one type of scheduling policy, and that might be specific depending on what accelerators you have in the flow graph. You might want to do things differently if you're scheduling things for your GPU resources, or, you know, FPGA resources, you can't really do much with the scheduling, right? You push it into the FPGA domain and it just does its thing. There's also opportunities for, you know, perhaps you've got a burst processing flow graph. Maybe you can run a thread pool and do a whole bunch of things balanced across all this CPU cores. So if you're doing a receiver chain, you can do that same receiver chain on each CPU core, have it nicely balanced. That's something you can't currently do with the GNU Radio CPU scheduler. There's also been a lot of research funded by DARPA. Bastian mentioned this in one of the earlier slides, the DARPA DSOC program. So this DARPA program, it seeks to create domain-specific SOCs, and within that have all the tools to be able to schedule the tasks and the processing on those SOCs effectively. So these guys have done, there's, I don't know, 3 or 4 teams that are working on this problem, and they've done various research into scheduling mechanisms for heterogeneous systems. Well, now the benefit of having modular scheduling in GNU radios we might be able to integrate this research, not make it the main GNU Radio scheduler perhaps, but if there's a system that can benefit from this, it's a scheduler as a plugin. But the main point here is that there's so many things we haven't thought of and we're not going to think of. So we're trying to establish the framework in a nicely abstracted way and not solve the entire problem for everyone. So just one example. So this is kind of a contrived example just to show you if I've got a flow graph with some GPU accelerated blocks, if I just throw that at the current thread per block scheduler that GNU Radio has, it's kind of a scattershot scheduling of the kernels. So each of these, so this is in the Nvidia profiling tools. You can see the kernel operations are, kind of randomly. They're sequentially. It's just however the threads handle them. But we're not really necessarily maximizing the parallel resources of the scheduler. Now, this is not the right solution on the right. We can do better than this. But if you look at this, you can see that we're taking a more intelligent approach, perhaps by stepping the scheduling of resources throughout a chunk of samples. We don't like this gap between execution. We'd like those to squeeze closer together, but there's things we can do more intelligently here. So the idea is now we have this mechanism with modular scheduling where we can do things like this. Another big benefit of kind of this revamp in architecture is hitting on some of these secondary goals. There's things that are harder to do in GNU Radio right now, such as packet communications. Some of the constructs that are in place for doing that have not been the best. We have these polymorphic types, and so there's been some community work underway to replace this type and make it a more modern API and more performant as well. And then also, Bastian mentioned distributed flow graphs that span multiple processing nodes. And then another goal here is the ease of block development. We want to make it a framework's only as good as people are willing to use it, and we want the pain points to be as low as possible. So we want to get, if someone's a DSP developer, an FPGA developer, we want those tools and the workflow to get you from, I have an idea, I can write my little bit of code, and I just put it here. We want that to be as painless as possible. So we're trying to come up with mechanisms and kind of a new workflow for creating blocks, and then having all the boilerplate stuff just come out of it. Right now in GNU Radio, there's a lot of boilerplate things that you have to put in different places just manually. It's just, it's how it's evolved. So we're trying to improve that. So when does GR 4.0 become reality? GR 3.x is going to live on for a long time. We just released 3.9 back at the end of last year. And this work that Bastian mentioned from DARPA, the SDR 4.0 project, we're going to get that upstreamed into GR 3.10 at some point this year. So that is forthcoming, and that will provide some of these capabilities, such as custom buffers and maybe some modifications to the scheduler in the current GNU Radio. Now, new Sched, GR 4.0, it's under development. We're looking to get to this minimum viable product, a proof of concept that we can say, hey, folks, this is good. You guys can develop your own applications with it and help us develop the framework further in the process. And then once we do that and come up with this, stamped approval, this is good to go, then we fill in the gap, push forward with it, and then that eventually becomes the long-term implementation for GNU Radio. So thank you, everyone. Any questions? I guess we're looking at the screen here, at the chat here.
Yeah, thanks, Josh and Bastian. There were a couple of questions. The first one was from Catherine, and that sparked a bit of a discussion in the chat. It refers to slide 7 in your presentation on what does neuromorphic mean or refer to.
see. So we got this from the DARPA DSOC program. So I mean, they're developing these heterogeneous processors where, rather than just having generic, lookup tables and DSPs and things, having more of, I guess, more specific types of constructs you would have on a chip. So I'm not entirely sure what neuromorphic means.
Okay, I think the conversation in the chat alluded to it being cells that can take on different possible functional modes. For example, memory, CPU, etc. And then another question, while we still have a few minutes, from Amish asking, what GPUs have you guys specifically been testing on?
Sure. So I've mostly been testing on the Nvidia RTX 2070 I have in my laptop. So not any really hefty ones right now. Just been prototyping with what exists in my laptop. I'd love to get access to different types of GPUs, but mostly stuck with CUDA. I believe Bastian, you've done some work with other GPUs as well, right?
But also only with a normal desktop GPU. So I mainly looked into Vulkan, but at the moment we are not looking for the high throughput figures, but still trying to figure out what's the best way to interface the GPU through CUDA, Vulkan, or whatever API, and how to integrate a scheduler. And at the moment, we didn't look into really fancy GPUs to get big numbers or so. So we are still more in the kind of figuring out how to interface it best and how to integrate it best in the SDR framework.
Okay, thanks. See, we still have some time. You guys were quite spot on with your presentation time, so we can field some more questions. From Spiro, asking, first a comment saying that he's happy to see everything new in GNU Radio 4.0. But he says that he hasn't yet found the interface between GNU Radio and RF NOC to just work, conveniently. And his question is around whether or not that is in the scope of GNU Radio 4.0, or is that more conversation for USRP?
It's definitely in scope. We were just kind of black links as part of SDR 4.0 looked more in this normal Xilinx DMA, and we just, because it was easier to start it with a GPU, but we are just this week also talking with guys from Atlas and see how to make kind of integrate RF NOC early and see how that can work and how we can collaborate there. RF NOC should not be an afterthought of this architecture, but we want to integrate this and support this early on. Yeah, but at the moment, it's right. There's no code there yet.
Okay, thanks. And then the last question that I see, it's I think reference to the evolution that was shown in the last slide about whether GNU Radio would be able to stream tens of gigabits per second into GPUs via Ethernet, if that something is planned. And I see there is a comment from Derek saying that it's already possible. So I don't know, Josh or Bastian, if you want to just comment on that.
Sorry, I don't have a good answer to the solution. Answer to the question. I don't have access to such a platform at the moment. I'm not sure how good we can do. But as far as I see, I mean, there seems that there is something that seems to be possible. But yeah, sorry.
Okay, Josh.
Yeah, I don't have a specific answer here either. I mean, I'd like to find out more, more context as to, what types of systems are doing this, how they're getting the data directly in, and how we can leverage this and make it part of the framework, or make the framework natively support this. But
the interesting part would be, what application do you have in mind which needs this? Because then it might be a very nice example application that we could use to try to approach with this framework. So what exactly do you need? What application is this? Then maybe this could be one of the good example applications that we could implement.
Yeah. Okay. Yeah. So we sort of just on schedule now. So I'm going to ask that that conversation be carried on Slack. And I see Amish has also mentioned that there's another discussion later this afternoon or evening where we can continue that conversation, but also feel free to carry on Slack as well. All right, I'm going to swiftly move into our next speaker. And that is, according to my schedule, Dr. Andrew van der Bijl from the South African Radio Astronomy Observatory, so down here in South Africa. And he's going to be talking about the GPU F engine that we have planned for the MeerKAT extension correlator. So over to you, Andrew. And what sort of time warning would you prefer?
Ty, give me maybe 5 minutes, well, 3 minutes to go.
Okay,
that should be fine.
Sure.
Can you see the screen okay?
Yep, all good. Fantastic.
Okay, well, morning, afternoon, evening, everyone, depending where you are. My name is Andrew, and I'm part of the Zhao DSP team. And today I'm just going to be talking about the GPU F engine that we have got on the go. I'm very much representing a team here. I've had the privilege of working with some fine people, namely Bruce Mary, Gerrit Grutzeck, and James Smith. So they've all contributed to this. So I'm just going to be really the front man, I think, for a lot of this work, which I'm going to show. So just a quick overview. I'll just quickly refer back to MeerKAT and then what we call MeerKAT Extension or Plus. Tyrone did me a great favor yesterday of giving a very brief overview of that as well. So I won't harp on that too long. And then we'll dive straight into the F engine processing pipeline, but specifically for the GPU approach that we're going to be taking. And then we will wrap things up. So what is MeerKAT? It's not just a small furry friend, but it is a powerful instrument too. Currently, as we speak, it consists of 64 offset Gregorian dishes, powered by 288 scarabs, and currently works on 3 different bands, UHF, L band, and S band, all being dual polarization. So when we look at the general overview of MeerKAT, we have digitizers at the feed, which all feed into a 40 gigabit per second Ethernet network. And then off this network or collection of switches, we have got all these scarabs, which take on different personalities, either of an F engine or an X engine. But the hardware essentially is exactly the same. What we're now looking at doing is taking this one step up. MeerKAT Plus or extension, we're adding in some more antennas in the order of about 20 more antennas. We're going to be upgrading the network from 40 gigabits per second to 100 gigabits per second. And then we're going to be switching over most likely to GPU-based processing instead of the fully scarab or fully FPGA approach, I should say. What does this look like more practically? Where in this case, it'll be dropping in 100 gig switches and racking in the servers or the rack servers and the GPUs in as dense a configuration as we possibly can. It has the benefit of a smaller footprint than what we would currently have with the FPGAs. And then, of course, there's 100 gig NICs would have to go in these boxes as well. Taking on the same approach as what we have with the scarabs, the GPU boxes could also take on whichever role is required, either an X engine or an F engine. I'm only going to look at the F engine in this particular talk. So if we look at the processing pipeline, traditionally, or as we currently do it, we have, from an FPGA approach, we have data which comes in, goes through some buffer and reordering. That's just to handle out of order packets and so on. And then the first stage of delay compensation, which is course delay. And then we feed it into a multi-tap polyphase filter bank. Then finally, the next or last stage of our delay compensation. And then it goes through quantization, corner turning, and packetizing, and then back into the network, which would then go off to an X engine. The GPU approach is going to be the same processing type of pipeline. It's just split across 2 different domains, being the CPU and a GPU domain, where the CPU handles our packet reception, buffer and reordering. It then gets sent across to GPU world, where the actual processing takes place, and then sent back down into the system, and the CPU takes care of, by means of speed 2, the packetization and pushes it back into the network to then what would be the next stage being our X engine. Looking at it more from an architectural perspective, it's a case of ingest via our NICs, then into system RAM, and then we would ship it off to the various GPUs where the processing then takes place. And of course, the CPUs hang off this, typically where we're allocating dedicated cores to various processors. Now, the whole GPU approach is what we're looking at is an asynchronous loop. Effectively, data gets received, it is allocated into pieces of memory or chunks of memory, which then get passed along to the various stages and are indicated or tagged along by events, CUDA events, to indicate when a particular stage has finished processing. And these sort of chunks of memory flow through the system, and where we're performing things like course delay and FIR filtering, FFT, and so on, and it gets buffered along the way until it lands up being ready for transmission. And then that piece of memory which was used then gets freed up and gets put back into this available pool. The allocation of memory is expensive, so we want to try and prevent that sort of that cost being incurred repetitively. So there's this reuse model that is taking place all the time. What does it really look like under the hood? Well, we have this free pool of memory, and a chunk of data or a chunk is taken, gets filled up, and then it gets popped onto this active queue, one per polarization. And this queue then, when we do some time alignment to make sure that your pol 0 and pol 1 received data chunks are of the correct timestamp, this then lands up being put into a ring buffer. And eventually this ring buffer pops off this particular chunk, which is now going to be ready for processing, which now takes us to the next stage. And this, of course, we have now had the host to device transfer into memory. And now we've got these chunks of data, which we now start the processing. Now, on the FPGA approach, we have got a buffer of memory specifically for the polyphase filter bank. And we have got the history of what we have processed for your PFB window. And you're typically just filling this, sort of sliding this window along. In the case of the GPU, we've got to kind of do this little bit of a look ahead, take this vestige or this next slice from your next chunk of data so that you have this continuous window. And we have got 10-bit data coming in, which also has to be bit shifted and changed in terms of word length, as we have a floating point number coming out, a 32-bit number coming out. And the course delay implements timestamp modification. That's how we achieve the various delays. And of course, this is all threaded operations. Outside of the course delay, we then go to the FIR filter. After that, buffered again, and then into the CUDA FFT. Now, this is where one major difference actually comes along. When it comes to the FFT on the FPGA, we're typically only dealing with one spectrum at any one given point in time. The size or chunk of data that we're dealing with in terms of the GPU, we have the privilege of a lot more memory at our disposal. So this is actually a batched execution, a batched FFT. So we're actually dealing with multiple FFTs at any one given period of time. So it's a lot larger chunk of data which is actually being used. Once this batched FFT has finished executing, we then buffer it again, and then it goes into what will be the final fine delay, quantization, and corner turning stages. And then we interleave these two polarizations for the corner turning. And then our next stage is going to take us back out of GPU world, back down into system RAM, and it's handed over to speed 2 libraries or stage, where it will now be sent out as part of the egress. That chunk of memory that was then used is recycled again, and that's where the asynchronous loop comes in this entire process. From a profiling perspective, what does this really look like? Well, I mentioned that we're doing batch FFTs, which is obviously a much larger chunk of data. And if we break it down, you can see that we very much are bandwidth bound. There's a fairly heavy cost right up front to copy to the GPU for host to device. And then we have got these 3 separate kernel calls and passes to global memory. This seems to be a CUDA thing. And we suspect that might scale with, depending on the size of the FFTs that we're doing. If my memory serves me correct, we would looking at a 32K FFT in this particular example. And as I said, we're doing both polarization 0 and 1 with this lot. And in one of the previous slides, I showed it was being processed separately and then later gets combined in our fine delay and quantization corner turning stages. Once that is all finished in GPU world, then we send it back down to the system RAM and back down for the CPU to process. The question is, where are we right now? So the F engine is still very much under development. It's a proof of concept. A significant amount of work was done by Bruce Merry initially just to test this out. So not all of it has been fully fleshed out. Fine delay was not fully implemented, and there's no DDC. So in this particular talk, I focused exclusively on the wideband F engine. We do also have a narrowband case where we typically look at working with 1/8 or 1/16 of the bandwidth. We have got a proof of concept in place for that. It's been tested separately just as a DDC. It has not yet been rolled into what we call the FGPU. So that's still something that needs to be done. And there's still a lot of other work that's being investigated. We've de-risked a lot of the process thanks to Bruce's work. And now we're looking at, can we perform DDC by making use of tensor cores? And we are expecting to get in the region of 2 to 3 F engines per GPU, and where we're looking to get about 4 GPUs per rack server. And the limitation to this is going to be depending on what hardware we actually end up using. We're speculating on 3080s at the moment, but by the time we actually come to deploy, we will have a look and see what cards are the most practically feasible, both in terms of cost and performance. Hariharan did mention yesterday that we're looking at the consumer grade cards for this. So, we speculatively call them the 4080 or 5080 or whatever the current will allow us to get, and we'll try and maximize that for our given implementation. And then finally, the advantage, of course, with the GPU approach is that we can throw a lot of unit testing at it. FPGA world is a very, very different place in terms of testing. The GPU side of things, we can not only test individual stages of it, for example, the DDC, but we can also look at it as a whole as well. So we've got some very, very basic unit testing in place for some of this. Most of it probably will be rewritten and fleshed out and expanded to cover a lot more use cases. So that's kind of where we are at the moment. It is going under a bit of an architectural restructure. James Smith is doing a lot of work at that at the moment. And so it's one of these things that hopefully by the next Casper conference, we can say we've got a fully fledged F engine up and running. We can run one, we can ingest data off our DSIMs or from Telescope and get some sane looking things out of it. But there's still some good work to be done. So I think with that, I will hand over back to Ty.
Right. Thanks very much, Andrew, with 2 minutes to spare. So well done on your timekeeping. Yeah, thanks for that very detailed sort of dive into the MeerKAT extension GPU F engine. There are a couple of questions. I'm just trying to find where they started. So the first one is, I guess, more of a philosophical question that just is looking to discuss, why are we going for a full GPU approach as opposed to a heterogeneous approach used, with FPGAs and GPUs? My recommendation is that we maybe leave that question for one of the later discussions. It could be, there's good points to argue for both sides. Some people have added their own, thoughts already. And then there was a question from Harry, I think it is, asking that from the profiling, we are looking, let me just see. Yeah, it still seems to be single streams on the GPU and not multi-streaming.
I think it's already answered. Thanks.
Was that already answered?
Yeah.
Okay. Okay. I see James addressed that. Thanks, James. Then there was a question about block size, and I think that might also have been answered. I don't know, Andrew, do you want to confirm if it's 256 megabyte blocks that we're using?
The chunk sizes are 100 megabytes, if that's the block that's being referred to. And of course, when it comes to kernel sizes, we're splitting it up. The warps are 32 threads, and that, depending on the size of the FFT, is how that gets divided up as to how many blocks in that sense. I'm not quite sure what is the reference there to blocks, but if it's memory, each chunk is about 100 megabytes.
Okay, and then the last question, just as we're running out of time, from Jonathan Weintraub, asking if you can please comment more on the intended approach for fine delay. And I'm not sure if we have time to dive into that now, or if you'd want to answer that on Slack or offline.
I think we could probably chat about that offline. I don't think there has been a final decision as to how that approach is actually going to take. We are looking at re-architecting parts of the F engine at this particular point. So, that very much is in a state of flux. But I think maybe we can chat about that offline. I know James has probably got some thoughts. He's been looking quite intently at certain parts of it.
All right. Again, thanks, Andrew, for that presentation. And thanks to all of those questions. All right, then our next speaker, and you may start noticing a trend or theme this evening or this afternoon, with more of a focus towards GPUs. Next speaker is John Romein from Astron, and he's going to be presenting on the Tensor-Core Correlator, basically a library that he's put together that leverages the Tensor cores on Nvidia GPUs to perform more efficient correlation compared to existing solutions. John, over to you.
Yeah, okay. Can you see the slides?
Yeah, I can see that. Are you happy with a 3-minute time warning?
Yes, would be great. Or even 5 minutes, so that there's some time for discussion.
Okay, sure.
Okay, well, let me briefly start by explaining what these tensor cores are, and then I will talk about the Tensor-Core correlator, the GPU library for doing the correlations, and I will show performance and energy efficiency results from the Tensor-Core correlator. So, yeah, let me first explain briefly what these tensor cores are. They're not really cores because they do not execute instructions, but they are, the multiprocessor can dispatch operations to these tensor cores that perform matrix multiplication in hardware. And these matrix multiplications are unlimited precision data, 16 or 8-bit typically, and these tensor cores perform these matrix multiplications much faster than regular GPUs cores can do. And Nvidia introduced this in a couple of years ago to accelerate training and inference in deep learning, because they do many matrix operations on limited precision data. So how does this work? Actually, a bunch of threads cooperatively perform such a matrix multiplication in one go. And there are now, on the most recent GPUs, there are multiple input types are supported, of which I think 16, 8, and 4 bits are most interesting to us. But you can accumulate the results into 32 bits quantities, so that you can decompose a large matrix multiplication into these tensor core size units. And you can use these tensor cores either implicitly through one of the many Nvidia libraries or program them directly. So can we use them for signal processing? And basically you can use them for anything as long as two conditions are met. One is that the algorithm should be expressible as a matrix multiplication. And this is absolutely true for correlations. It's also true if you do beamforming and generate many beams at the same time while keeping the beam weights constant for a while. But you cannot do this, for example, you cannot use them for fast Fourier transforms because that are not matrix multiplications. And the second condition that it operates on limited precision input data. And that this is usually the case for radio astronomical purposes. So I started playing with these tensor cores, and eventually this evolved to a GPU library for correlations. It is not a complete correlator though, because it only performs the computations on these tensor cores, but it does not do the network I/O for you, and it does not do the corner turn. And the correlator itself is implemented in CUDA. You can use it in any CUDA application. But with a few hacks, you can also make this work in an OpenCL correlator. And it works on any recent Nvidia GPU. And over time, this library, it's starting to mature. So you can use it for any instrument, especially if there are many inputs, then it will be efficient. And it supports 16, 8, and 4-bit input. And it's really highly optimized. So the library, it's pretty limited functionality, and it only exports two functions. One of them is that compiles and links the GPU code, and it does so at runtime, because in many situations you only know the number of receivers, the number of channels, etc. At runtime. And the second function, it launches the GPU kernel that does the actually correlations for you. You must move the data to GPU memory yourself, but this GPU function performs the correlations. And there are some examples and tests that show how this can be used. So these tensor cores are quite difficult to program. It's very low level, and yeah, there were a couple of challenges that had to be tackled. One of them is the fact that these tensor cores do not support complex numbers, so there's no swizzling of real and imaginary parts or doing fused multiply subs. The second one is that the visibility data is in a triangular output format, which is also not supported by tensor cores. And the third challenge was that these tensor cores compute so extremely fast that it's very difficult to feed them fast enough with data from GPU device memory into these tensor cores. So I do not have the time to explain how all these problems were solved, but fortunately, all this complexity is hidden from the user and is inside the library. So I will show you some performance measurements that were obtained on an Nvidia A100. And I did not measure the PCI Express transfer times because I expect that this correlator library is part of a larger pipeline that does some filtering or maybe even imaging or whatever on the GPU. But I do provide, yeah, compared to the XGPU results, which is, well, I think the best performant GPU library for regular GPU cores. And if we look at this performance, the bottom two curves are for XGPU, that supports 32-bit and 8-bit data. And the top 3 curves are for the Tensor-Core correlator on 16, 8, and 4-bit data. So you see that there's an enormous performance difference between these Tensor cores and regular GPU cores. And the amount of operations, it's in the hundreds of teraops per second. And if you think about this, this is really a large number. And this graph looks very similar.
John, just a 5 minutes warning.
Yeah, okay, thank you. This graph shows the energy efficiency. It looks very similar. Yeah, for 8 and 4-bit operations, it even exceeds the teraops per joule milestone. So some further developments. I promised an open source distribution. It's not really ready for a public distribution yet, because the GPU code is fine, but the part that the examples that run on the CPU, they need some rework, and I'm working on this. But if you really want to play with this library, just drop me a note and I can give you something to play with. We also intend to implement an Tensor-Core beamformer, and we are about to start a new project with a Dutch hospital where we want to use this for medical imaging purposes. So it's not only radio astronomy anymore. So concluding, I think that these Tensor cores, these are really a disruptive technology. And this Tensor-Core correlator, I think it's a nice GPU library that is widely usable and performs up to an order of magnitude performance and energy efficiency improvement over the regular GPU cores. And a few words of thanks. So if there's time to answer any questions, I'm happy to take them now.
Yeah, thanks very much for that sort of introduction to Tensor-Core, John. And I just want to add a comment. The team at Zhao has been using John's Tensor-Core correlator implementation in our X-Engine investigations. So yeah, we have been playing around with it, and there is quite a big improvement over XGPU. There are some questions in the chat. One from Amish, and I think it's the same or along the similar lines as what Lincoln has asked. It's basically, would the code, the Tensor-Core correlator code, need to be adjusted to deal with changes in hierarchical memory architecture for the different GPU generations? And alongside that, have you tested this on any of the later generations, for example, the RTX 3000 series GPUs?
It has been tested on, well, on the bottom line, not the second one, on these GPUs, SM70-86. SM70 is Volta. Volta worked quite differently from the Turing and Ampere generation Tensor cores, and indeed I had to change quite a lot of code for these different architectures, but that's all hidden inside the implementation of the Tensor-Core correlator. You do not see the difference.
Okay,
the
thanks.
user interface is the same.
Okay, and then another question. There's a comment about, there's good performance when n is large, but what about small n? Is there sort of a crossover point where performance maybe becomes worse?
Well, I think it performs in any case better than regular GPU cores. But for small n, there's not enough memory bandwidth to get as good performance as for large n. You do see some drops, especially after 33 antennas or for 65 antennas, for example. That is something that probably can be, well, not fully fixed, but can be improved with some more efforts. But it requires specific optimizations for particular numbers of receivers.
Okay, all right. Yeah, that's all the time we have for this presentation. Thanks again, John, for that presentation and for answering some of those questions. There's a couple of more questions. One particularly asking if this Tensor-Core correlator will make XGPU obsolete. And I think there's a response from Jack saying that as soon as this is released, then it will. So maybe that's something we can discuss at one of the other sessions or continue on Slack. All right, thanks again, John. Our next speaker is again from the South African Radio Astronomy Observatory, Amish Patel, and he's going to really build on nicely from John's presentation. It's going to talk about the Python-based GPU X engine for MeerKAT extension that uses Nvidia's Tensor Cores for correlation. So over to you, Amish. What sort of time warning would you prefer?
Yeah, let's do 4 minutes. All
right.
Can you hear me though?
Yep, loud and clear.
Awesome. Well, I mean, I was going to go with the usual introduction. Hi, I'm from Soreo, but seeing as Andrew van der Bijl's presentation kind of covered most of what I was going to say, and of course, so does John Romein, we might just skip ahead to the things that I wasn't going to get around to presenting. But I mean, first and foremost, like Tyrone says, today I'll be presenting on something the DSP team and Soreo have been working on for the best part of the past year, I think. Admittedly, I only worked on one component of the greater engine. Gerrit Grutzeck, a colleague that we've alluded to before, he did a lot of the heavy lifting, as did John Romein. But hopefully I'll be able to give you a good overview of the main concepts involved in the X engine's operation. I say high level, mainly because there probably isn't enough time within the session to go into detail across the board, but as always, please do drop us messages. In terms of that overview, well, I was going to go with a short introduction and to provide background and context, go through the basic signal path of the data being processed, kind of touch on the actual files and software components where the magic happens, putting it all together, and then some notable mentions. That being said, you know, these components that I was going to touch on, they each warrant sort of 15-minute presentations on their own, as John has done as well. So we'll see how we go. Introduction and context. Well, this really is a Tensor-Core accelerated GPU-based X engine. X engine delivering the X part of an FX correlator. The F component is something like Andrew van der Bijl described. Again, based on the work of the esteemed John Romein from Astron. But in our case, for Soreo, it's incorporated into our specific use case using a library called CAT STP SIGPROC, made by another sort of subsystem in our Cape Town office. And that's mainly a framework to simplify programming for CUDA and OpenCL, including writing code that'll work on both APIs. In our case, obviously, we're using Tensor-Core, so we're only targeting the CUDA paradigm. Quite a lot of effort has gone into documentation and unit testing and really making sure this is easy to follow, you know, all things considered, but obviously there's some foundational knowledge required. For example, the speed protocol. A notable to-do is the B engine component of this, the beamforming component, but today we're speaking about X engine stuff. Moving on from there, a basic signal path. You know, you might have experience with X engines that receive data from multiple F engines. In this case, we're receiving onto a host server where we're collecting multiple speed heaps, incorporating them into a single chunk. We pass it on to the GPU to reorder, and then further on to correlate and output that back into the CPU and then further back onto the network. In a bit more detail, we receive at the NIC, obviously, the network interface card, and then the heaps, the speed heaps received are assembled in system RAM, then passed over into GPU RAM for the reorder kernel to perform the reorder. Once that's done, puts it back into GPU RAM for the next kernel to execute its operations, correlation in this case. Once that's done, back into GPU RAM and then system RAM we go, and finally out onto the NIC and onto the network. The arrows here basically indicate where memory bandwidth is kind of focused. And hopefully we'll have time to discuss that as well. Where the magic happens. So in terms of the main software components that implement the things mentioned on the previous slide, we have a receiver that receives multiple heaps collected into a single chunk. Again, we have the reorder, receiving chunks for correlation, the correlating kernel that correlates reorder data to produce baselines, and then finally the data transmitter. The files linked here are the files in the repo itself. Unfortunately, it's private at the moment, but if you ask nicely, I'm sure we could make a plan for you. More details on the receiver. Thank you very much for Andrew van der Bijl for explaining this, because for the person reading later on, maybe they'll have an idea already. But again, there's quite a lot of complicated stuff happening in the background in C++, but you mainly need to focus on the Python. Underlying implementation of the receiver is using Speed2's IB verbs transport. So that should give you an idea of the data rates we're playing with here. Of course, these ingest rates are far too high for the main Python thread to keep up. So again, that's why we alleviate some of this pressure by receiving multiple heaps at a time. Just so we're all on the same page, a chunk in this case, and in the FGPU case, is just a buffer in memory. So we give the receiver empty chunks to populate with data. We wait until it receives data, ultimately assembling these heaps into a chunk, and then finally pop the completed chunk off the ring buffer on the top right once it's ready. Even more detail and more contextual information. The X engine receives data from multiple F engines, and it actually starts off where we give the receiver object a free chunk in this free chunk stack. Once MeerKAT GPU starts receiving data, it grabs a free chunk of that stack and makes it active in a sense, and begins to populate with heaps from various F engines. Once it's received the requisite data from a fixed number of heaps per antenna for the active chunk, hands it over to the ring buffer, and that gets popped off to be used, ultimately copied over to the GPU. And Andrew van der Bijl made a note of reusing chunks where you give this ring buffer chunk that's it had its data being copied out back to the chunk stack, because memory allocation is an expensive operation. At the moment, to prevent the pipeline from stalling, if too much time has passed, a chunk with missing heaps is still passed on for processing. This is mainly to avoid dropping packets. Currently, we just log a warning, but we might need to update this functionality. The read order itself, some other presentations have alluded to needing to reorient data before it's gone on for further processing, and this is no different. The dimensions in this GPU sense are a bit odd. Ultimately, it's a one-dimensional array that you're accessing, but it represents data with 5 dimensions. And once it's reordered, it's 6 dimensions, as you can see. But for example, the batch dimension here basically represents, I guess, the total number of heaps per receiving F engine or antenna. So in this case, if we have a batch dimension of 10 and we're processing data from 64 antennas, you ultimately have 640 speed heaps in the chunk that you're processing. Again, links on the slide to where the specific implementations reside. And I note again that this was written using CAT SDP SIGPROC, which allows us to incorporate the kernel for the GPU using async IO and other features. And again, this holds true for the correlation kernel. John Romein and his Tensor-Core correlator. This is being brought in for our use case using CAT SDP SIGPROC. Another to do is to test compatibility with RTX 30 series. We've got a 3060 in-house, if I remember correctly. And for what Andre Renard said, this bodes well for testing on our GPU. In the sending example, again, it's a similar idea to the receiver. Andrew van der Bijl kind of went over this already, but it's the opposite of the receiver, where you give your transmitter full, complete heaps. It sends the data off, and it gives you back an empty heap. And in this case, the internal logic is written in Python because due to accumulation from the correlation kernel, we only need to send a heap every half a second. So again, it's designed to be asynchronous, i.e. non-blocking. So this, something I was going to go through is like a crash course on async IO, but we'll see if we have time for Q&A there. Putting it all together, like I said, there's 4 main components, and this is where you might find them in terms of specific methods and lines of code in specific files. And just to relate that back to that basic signal path we were talking about, you see there's your main point of contact, probably your command line sort of application, further into the XP engine, and you can see there's the receiver loop, the GPU processing loop that incorporates the reorder and the correlation, and then the transmitter. Again, notable mentions. I thought I would be fully pressed for time, and I was going to say, great effort has gone into unit tests using PyTest, if anyone's familiar with it. We've made provision for testing data transmission and reception using Speed2's in-process transport, so you don't need a full network to test these components. There's parameterized configurations to test the kernels themselves, as well as an end-to-end test of the X engine, and they can all be run locally on a capable machine or server, but also done using continuous integration on a Jenkins server. It fully builds and runs a Docker image from scratch to make sure you haven't broken anything at any point in the packages or the pipelines installation, and runs on every commit and pull request. And the detailed documentation is a huge help. And I'm not even trying to sell that to anyone else. For me personally, having not looked at this for a few days, it certainly helps me get up to speed almost every time. And there's tips in there for debugging, for resource utilization and tweaks for increased performance. Really very cool. And I encourage people to ask questions about this because it's something I definitely want to discuss more. I was going to end there. So Tyrone, what do you reckon? How are we doing for time?
You've got 3 minutes left. And there's 1 or 2 questions. So
yeah,
do you want to take those
please.
questions? Okay. All right. First question from Hari. How does the reordering cost compare with the rest of the kernels?
The reordering cost, let me just see if I've got from Insight Systems. The reorder itself, I think it's, all things considered, quite intensive because the memory accesses can't necessarily be coalesced. It's quick, obviously, but you can't do a kind of intermediate step with the shared memory like you might do for a matrix transpose. But needless to say, it's really quick. And as you can see here, the example that we've profiled is for a batch of 10 heaps, and that's with 10 batches in total. So I think we have our own rough utilization estimate for the reorder itself. And I think it was like 2% of a 2080 Ti. So if that answers your question.
Okay, thanks, Amish. And then lastly, you've still got like 1.5 minutes left. From Andre, how many system DRAM read and write cycles are needed for the packet receive and transmit paths between the NIC and GPU?
Ooh. That's a good question. I don't think, like the DRAM cycles themselves, I don't think that's something that I've profiled with any intent. I'll get on it and hopefully have feedback for you by the end of the workshop.
Okay, great. I think that's all the questions for you, Amish. So yeah, thanks for that overview and sort of dive into CAT X GPU. So yeah, the GPU X engine using John Romein's Tensor-Core correlator.
Cool.
All right, and then our next talk, I was just informed that it's actually a pre-recorded talk. So I'm assuming that Ryan, who's sort of the Zoom admin, will press play when necessary. But the next talk is by Vinand, Prayag and Nitish Ragoomundun. Hope I pronounced that correctly. And they'll be talking about an FPGA GPU, so a hybrid system, digital backend for the pathfinder of the Deuterium Experiment Telescope. So over to you, Ryan, I guess.
Can everyone see this all right?
Yep.
Good morning and good afternoon. We will be speaking about the Deuterium Experiment Telescope, which is a new instrument being designed and built in Mauritius. The aim is to observe the deuterium hyperfine line, which is centered at 327.4 MHz, and the line has an estimated bandwidth of 250 kHz. The instrument is to be used both for the deuterium total power measurement and as an imaging array. Observations of deuterium will be carried out over long periods of time to ensure credible detection and measurement. The facility will consist of many stations, and each station is a group of 19 antennas. For testing purposes, to prove the concept and to develop the necessary technology and skills, a single station is being set up and acts as a pathfinder for the final instrument. The analog chain consists of 3 distinct circuits. The signal is progressively conditioned by a series of amplifiers, attenuators, and filters to get to the final gain, impedance match, and bandpass required. The last stage consists of a bandpass filter which restricts the signal to a band of 10.7 MHz. This prevents too much RFI to reach the ADCs and also allows a simpler design for the rest of the pipeline. There are several constraints to the development of an instrument, of which the cost is the most important. The idea from the beginning was to use parallel computing platforms to build a low-cost compute-intensive system. A GPU can be used to implement 2 parallel distinct processing pipelines. As for the data acquisition unit, after further studies, we opted for ready-made FPGA-based solutions. The Casper hardwares offer solutions with high performance and lots of functionality at relatively low cost. And furthermore, the boards can be programmed using a tool flow based on a block programming model instead of hardware description language. The final choice is to use a Casper snapboard as the main component of our acquisition system, as it represents the lowest cost per signal channel. The plan is to have the snapboard sample and digitize the signal, then it should perform some preliminary processing and pass the data to the GPU processing nodes, where the rest of the parallel processing pipeline is implemented. The ADC chips on the snapboard can be operated in 3 different ways. We chose to sample at a rate of 250 MHz to obtain a maximum number of input channels per snapboard. This reduces the cost per channel. However, the input analog signal is a band around 327 MHz. Therefore, aliasing occurs. We obtain an alias at 77.4 MHz, but it's not all bad. The analog bandpass filter reduces the adverse effects of the aliasing, and this allows us to sample at this rate and use the aliasing to get our deuterium line. The basic point to remember is that the deuterium line resides in only a small 250 kHz band, and the rest of the signal can be discarded. This allows us to plan a digital down conversion to bring the band of interest to the 0 Hz mark, and subsequently filter out the rest of the bandwidth. This also opens the door to decimate the sample rate. The lower data rate reduces the pressure on the rest of the network and computing pipeline. First, we perform a quadrature mixing with a local oscillator frequency to bring the deuterium line to the baseband, and at the same time producing complex samples. Note how the spectrum is no more mirrored, since the complex signal occupies the full 250 MHz band. Now, to move from the 250 MHz to a 250 kHz band, we need to filter out a large chunk of the spectrum, then decimate the sample rate. It represents a decimation factor of 1,000. To obtain a sharply cut band and preserve a good signal-to-noise ratio, in a single filter stage, it would require quite a large number of computations. For this reason, we broke down the process into successive filtering and decimation, which, when put together, Kaiser-Bloessl window to have control over the cutoff frequency and attenuation. The filter coefficients are pre-calculated and input to the FIR compiler blocks when designing the system. A sharp output is achieved with a total of only 995 coefficients. There is a 99.8% in reduction of data rate per channel when compared to the output from the mixer block. The final stage of the FPGA data acquisition system is a packetizer. The data is sent over a network using UDP packets. An interesting feature which we included is a byte swapping stage where the data is converted to little endian before output. As the CPUs down the pipeline are Intel processors and they use little endian. The Xilinx bitbasher block is used to perform both the byte swapping and concatenate the real and imaginary parts of each sample. Following the FPGA scheme, the data rates achieved for a single snapboard and for the one-station pathfinder are well within the 10 GB limitations. Furthermore, the overall data rate from a large network of snapboards when considering a multiple-station instrument is relatively low and manageable. On the side of the GPU processing node, all this data need to be received, depacketized, and arranged in arrays in memory, then copied to the GPU for further processing. We designed a multi-threaded parallel control program to perform these tasks and provide the data throughput required for real-time processing. The control program also manages the processors running on the GPU. Data throughput achieved are sufficient for the one station. If more throughput is required, the depacketization can simply be distributed between a larger number of threads on the multi-core CPU. A custom parallel FX correlator runs on the GPU. The F engine is implemented as a polyphase filter bank. The Fourier transform is performed using the highly optimized CUFFT library provided by Nvidia's software development kit. The parallel X engine is a custom implementation which calculates and stores both auto and cross correlations. Thus, the data products can be used further to either compute the total power for the Deuterium experiment or for imaging the sky. We reformulated the way correlation is computed so that it takes the form of many independent multiplications in distinct frequency channels. Following this, the complex multiply accumulate is naturally obtained by the sum of subproducts when the rows of and columns of the matrices are multiplied. We did this so that we are able to implement the correlation using the high-performance QBLAS library, where a batch of thousands of matrices are multiplied in parallel to obtain all the correlated power spectra. However, there was a small issue where the QBLAS routine expects input data in a specific arrangement. So a custom reordering kernel had to be implemented to rearrange data prior to input to the QBLAS routine. The data throughputs achieved by both F and X engines of the correlator are sufficient to handle the processing for the telescope. The data flow across the pipeline was successfully tested using signal generators. The parallel data acquisition system, the network, and the GPU processing node can manage the data in real time. We also managed to perform test observations with 3 antennas. We had some issues, but we managed to obtain certain good results. An example of an uncalibrated measurement is shown here. It includes data for 12 hours of observation. The expected curve was calculated from the antenna beam profile and a sky map at the working frequency. Since the data is uncalibrated, we simply took the log to obtain a logarithmic scale on the y-axis. The pipeline works. There are just a few issues as we haven't implemented a gain calibration system yet. And we need more antennas and also perform more observation. So there are still a lot of work to be done. The cool part is that we are doing science with a gaming rig. More importantly, implementing most of the pipeline in software and using off-the-shelf equipment significantly reduces the development time, makes the system more flexible, and also makes science more affordable. Finally, we would like to thank Xilinx Inc. for having donated licenses for the SDK, without which we would not have been able to use the Casper toolkit. We also thank Nvidia Corporation for the grant of a powerful gaming graphics card, which we used for the project. And we are grateful to the Casper community for helping us through their Slack channels and the mailing list. We especially thank Jack Hickish and Dan Wertheimer for their constructive comments, which contributed a lot to our progress. Thank you.
All right. Thanks to Vinand and Nitish for that pre-recorded presentation. There is one question regarding the GPUs that we used. I'm not sure if Vinand or Nitish are online to take questions. I think they are.
Hi. Yeah, I'm online.
Hi. Yeah. The question is just which GPU models were you using?
Yeah, so we were using the Nvidia GTX Titan X.
Okay, thank you. I think those were all the questions. Yeah, Mish says thanks for answering that. Does anyone else have any other questions? We still have about 4 minutes before the end of this session. So if there are other questions, now is your opportunity to raise them. Okay, I'm gonna take it as there be no questions. But yeah, thanks again, Vinand and Nitish for your presentation. And with that, it sort of concludes the first session. We're a bit early. The break is only scheduled to take place at 6, but I'm sure the organizers won't mind if we break now and return at the usual time of 6:15 SA time or 9:15 California time. Unless there's anything else from the hosts, I won't catch you when we return from the break. Jack Hickish will be the session chair. So yeah, if there isn't anything else, thanks everyone, and catch you in a bit. Hickish will be the session chair. So yeah, if there isn't anything else, thanks everyone, and catch you in a bit. Hickish will be the session chair. So yeah, if there isn't anything else, thanks everyone.
Okay, I hope everyone had a good 15-minute break. We'll try to keep this on time, so let's get back to it. The schedule now tantalizingly has listed just under NVIDIA and NVIDIA 2, our two invited industry talks from NVIDIA. I hope I'm reliably informed by my secret sources in the local organizing committee that the first talk is from Beno Badash, who's going to talk to us, I believe, about the BlueField DPU. So please take it away. I'll give you a 5-minute warning.
Hi, everybody. I just want to check with you, Jack, that you can see my screen.
I can.
Okay. So hi, everybody. I'm very happy to be here together with you. And I'll try to give an overview on the NVIDIA BlueField DPU, or stands for Data Processing Units, during the next 30 minutes. I'll try to cover both to give you some deep dive in terms of the details of what is a DPU and give some use cases implementation that we are doing today with the different customers worldwide. And at the end, I'll try to leave some time for questions. So feel free to take notes and ask questions later on. Okay, so now in the area of AI accelerated computing, instead of a CPU-based server, the entire data center is the new unit of computing. And to make this model work requires the GPU for accelerated computing and the data processing unit, or the DPU, as I mentioned earlier, for accelerated data processing. The CPU is still part of the triad of computing. However, with a GPU and a DPU, the CPU is freed to perform application processing, which is good at for a long time. So the CPU performance actually perform basic single thread applications, while the GPU performs massively parallel processing, while the DPU performs data intensive functions like communication processing, compression and encryption, and we'll see some additional accelerations that we have in the DPU. The new architecture in the future of, is the future of accelerated computing, and depends fundamentally on the GPU and the DPU building blocks to make the data center scalable and efficient. So how actually are we, doing that? If you look on the current slide that I'm showing on the left side, you see actually a typical view of a server as it seems today, where you have a lot of software-based infrastructure, whether it's infrastructure for the management of software-defined security, software-defined networking, software-defined storage. All the infrastructure are becoming more and more software-dependent, and in general, we call it software-defined infrastructure. And all those software-defined infrastructure tasks are today running on the CPU, on the x86 of the server, consume about 30 to 35% of the CPU of a typical server. Well, if you get into the right side, which is the same server exactly, but when you install a DPU inside it, you get three main things. You get the ability to offload your software-defined infrastructure. You have the ability to accelerate it, and you have the ability to isolate whatever infrastructure task is being running on the DPU. So in a way, you are able to offload all the software-defined infrastructure over to the DPU, as you see on the picture on the right. You are able to run right now the software-defined security, the storage, the networking services, all of those utilizing the outdoor-based offload engines that we have on the DPU. And since it's outdoor-based and it's all kind of embedded inside the DPU as silicon SoC, you are now able to accelerate your task and not just getting it offload, but getting even higher performance compared to what you had previously in your typical server. And finally, since you now move all the infrastructure tasks to be based on the DPU, you have a physical isolation between the x86 and whatever application is running on a CPU, between the infrastructure which is running on the DPU. So in a way, you get back your CPUs, the 30% that you have spent on the software-defined infrastructure. Now you have more CPUs in the same exact server. You can utilize more CPUs to make money-making applications. And at the same time, you are able to offload the infrastructure tasks, not only the data path, but also the control path. So in a way, you are totally independent running your task on a DPU in a fully isolated and secure environment. Let me show you one example of implication of what can be done, or based on the high-level description that I showed earlier on the slide, how exactly we do that in a specific security application example. So if you look on the left side, again, you can find a typical server. When you want to run, let's say, I took some example application like layer 4 to layer 7 inspection, whether you want to run firewall or microsegmentation, for example, or any kind of encryption service like IPsec or TLS. And on top of that, of course, you have your SDN, the software-defined networking service, and the software-defined storage for your storage services. And you left out with certain amount of CPUs to run your workloads. But as I mentioned earlier, about 35% of your CPUs are just occupied by those software-defined infrastructure as the main infrastructure that you have to run in your server. While if you move to the right side, and here we use the same exact server, but we installed, instead of a regular NIC, we installed a DPU, the Nvidia BlueField DPU. So now you are able to offload those services that I mentioned earlier. You are able to run L4 to L7 inspection using our regular expression engine. You are able to implement microsegmentation on next generation firewall. You are able to utilize the encryption, the inline encryption engines that we have, whether you need that for IPsec encryption or for TLS. And of course, the network, the software-defined network services and the storage are also being offloaded using our capabilities and engines accelerations on the DPU. And you can see finally what I mentioned earlier about the isolation. Now you have what we call kind of a physical gap between the x86 domain and the DPU domain that allows you to keep all your infrastructure services to be fully secured and isolated from the main CPU. You get back more CPUs to run additional workloads. And overall, you do that with just reusing and implementing a DPU inside your server compared to a regular NIC. So just to give you one example of our capabilities, if you look here, I just tried to capture some performance slides for IPsec encryption that we have. So IPsec in a DPU implemented by an inline hardware-based acceleration engine, which means it's part of the pipeline. And that can perform up to 100 gig bandwidth of encryption and decryption. So the BlueField DPU, if you look on the slides, you'll find out that the DPU delivers about 4x higher performance compared to a software-based IPsec solution running on the x86 on the CPU, and saves about 30% core utilization compared to the use case when you run your IPsec encryption and decryption on the main x86 cores in the server. Of course, if you want to get the same level of highest performance of 100 gig, you will see even higher saving and more saving in terms of the cores and higher bandwidth in terms of overall solution that you can implement. Now, it's not only possible, to get higher performance with lower CPU utilization. It's also possible to have the DPU in each and every node, and now you can do actually having encryption and decryption in each and every node for east and west traffic encryption, as well as required in the data center of today. Another use case that I want to mention is GeForce Now, which is NVIDIA GeForce Cloud is in a service. It serves about 10 million members around the world. GeForce Now is a tremendous, complicated service to deliver. Everything is Matter. whether you look on the visual quality, the frame rate, response time, server cost, and most important of all, security. We transition GeForce now into BlueField. With BlueField, we can isolate the infrastructure from the GAM instances and offload and accelerate the networking, storage, and security in a very similar way to what I showed earlier in the previous slides. With BlueField, we will improve our quality of service and increase the concurrent users at the same time. The ROI that we get out of BlueField here is excellent. So what exactly is, BlueField 2 DPU? Let's look in more details what we deliver. So if you look on the right side on the picture, on the high-level picture of the SoC, you see that a major building block of the BlueField 2 DPU is the Connectix 6DX, a great network interface processor that we have from Nvidia for a long time. It can serve up to 200 gig Ethernet using SerDes of PAM4 or NRZ. We have integrated to the Connectix 6DX and 8 ARM cores, A72, that can run up to 2.75 gig. with the internal embedded memory and cache subsystem. On top of that, we have the PCI Gen 4 switch embedded, which can serve different type of configuration. Some of the configuration can be as an endpoint in a server, and it can also be configured as a root complex to manage some other endpoints on the PCI. So for example, in a storage application, we can use this GPU to be the main controller in a JBOF to manage a bunch of SSDs. In addition to that, we have the DDR4 memory interface and some additional accelerations, of course, hardware-based engines on top of what we have on the Connectix 6DX engines. So those can be, vary from security, storage, and networking accelerations. On the security side, you can find some types of different type of encryption and decryption, as I mentioned earlier, IPsec, for example, or TLS. We also support encryption at rest for the storage, ASXTS. We also have regular expression engine, which can perform deep packet inspection application, for example. On the storage, we have an NVMe or Fabric acceleration dedicated engine that I'll touch base in a moment and show some performance according to that, et cetera, et cetera. So to give you some type of the performance that we can achieve, I try to add a few slides here with showing some performance benchmark that we have performed. So looking at 100 gig VirtIO net in virtualized cloud environment, the DPU-based server performs about 7x higher performance compared to a software solution without acceleration, of course. Overall, the DPU, which of course using its engines to offload the control path as well as the data path, consumes 0 x86 cores, and that is a huge advantage on the top of the performance. As I showed earlier, this is the way we can free up CPUs and at the same time get a much higher performance to perform better accelerations. Another example is for the storage. You can look on the storage emulation, what we call Snap, that I showed in here on this slide. And Snap or storage emulation is being used for a bare metal cloud or bare metal as a service use case, where in general what we do is we emulate the NVMe protocol over the DPU PCI bus and translate it from the DPU PCI bus into an NVMe of a Fabric transaction on the Fabric, on the network. And this actually provides a remote storage like feeling and look and feel, I would say, like it was a local one. So in a way, you don't need to rely on your local storage anymore in the server, but you can just translate any NVMe transaction into NVMe of a Fabric to the network and utilize a remote storage like a JBOF or something else. So if you look on the numbers here, we showed a 100 gig performance and a 200 gig performance that goes up to 5.4 million IOPS. Two type of, I would say, acceleration we have in the BlueField 2 DPU. We can use the non-offload and the full offload. And the non-offload is a path which actually utilize the ARM cores using SPDK, which is the open source for the storage community. And the full offload is actually using the NVMe over Fabric acceleration engine that we have built in the DPU. And by that, you, of course, get higher performance. So we can see the performance of 100 gig and the performance of 200 gig based on the DPU acceleration engine. So all of these capabilities are being enabled by Docker. And Docker is, in fact, NVIDIA framework for application developers and third-party companies to enable them to easily develop applications and programs for the DPU. Docker stands for Data Center on a Chip architecture. It's leveraging industry standard API as well as NVIDIA Docker libraries. Docker is an open and modular, and is going to enable an ecosystem of developers who are bringing their own value, their own differentiated services, which they can containerize and launch via Docker platform and repository. Docker, in fact, for DPU is the same as CUDA for GPU. So the Docker stack includes, different, I would say, parts. A lowest level, it has a firmware, a bootloader, and drivers, enabling the low-level control of the DPU. And also have libraries and SDK with APIs for developers and runtime libraries to easily enhance applications performance. We are actually engaging with leading companies around the world for each and different services, as you can see on the slide, whether we are talking about platform infrastructure companies like Canonical, Red Hat, and VMware, for cybersecurity services like Checkpoint, Deep Instinct, etc., and also for the edge and telco, as well as for storage. Let me give you one example of how we utilize the GPU and the DPU in AI-based framework, and also using Docker. So if we look on the next example, we'll see where Docker and Morpheus AI framework are being used. So on the left side, what you see is the Morpheus AI framework, and on the right side is the BlueField DPU. Traditional approach to data center security are no longer adequate. And the reasons for that is actually, it can take up to 6 months to identify a breach. And even then, a few additional months to contain it. Your cybersecurity strategy, for example, no longer be to simplify, sample your data, and send off offline data take for analysis. So it's taking too long to identify breaches and too long to contain. And with modern security solutions, there's a few goals that we are trying to address. We want to reduce the attack surface. We want to identify breach in real time. And we want to contain breach with a minimal damage. So what we do at Morpheus is actually an AI cybersecurity framework intended to help accelerate the cyber ecosystem. The Morpheus AI framework helps the cyber ecosystem do pre-processing, inference, post-processing, and form a set of recommended action. It also includes a set of examples, models, such as looking for a personal identification information, phishing, anomaly detection, etc. So the Morpheus actually brings new assets like a suite of pre-trained models designed specifically to accelerate cybersecurity and cybersecurity AI workflow. So Morpheus at its own, which you see on the left side, we at NVIDIA are leveraging the power of the GPU acceleration with a Morpheus software stack to enable cybersecurity. But we want to also do that and leverage the DPU, and together with the framework of Morpheus AI with the DPU to deliver something which is really, really new. the addition of the DPU really enhanced the solution. You have already heard about, talking about the isolation and the acceleration engines that we mentioned. So what we introduce here for this specific solution, we introduce the Docker telemetry agent, one of the services that is being developed under Docker. And this is kind of, I would say, cool IP that we have leveraged from our previous Cumulus acquisition. It brings an advanced network visibility with the ability to pre-process and identify anomalous traffic, and even implement policies at the I/O. So think about it, the BlueField DPU sits on the network and becomes the source of real-time telemetry data. Essentially, it's now a cybersecurity sensor which feeds the data into the Morpheus platform. So this telemetry data from the DPU might be tagged and suspicious, and all of that being done via the Docker telemetry agent. The data right now, it's the telemetry aggregator and being sent to the Morpheus, while the Morpheus engine now is doing pre-processing, inference, and confirm anomalies. And at the end of the day, if there's any, I would say, policy which needs to be updated, it can send it back to the DPU for policy enforcement. So the DPU is not just, kind of a cyber security sensor. It's also have the ability to pre-processor and action implementer, because now we're going to use the Docker to force the new rules and do some policy enforcement on the I/O in order to implement the learning and the outcome of the Morpheus AI-based security. In a similar way, what we are also doing, as I showed previously on the previous slide, we are working intensively on new use cases where the GPU plus the DPU brings unmatched value to non-solvable problems. We are moving one step further to what we call converged accelerated computing, where in effect, we attach GPU and a DPU on a single card to accelerate AI-based workloads and be able to scale out in each node. So if you look on the current slide, in a way, try to illustrate, if you remember the two pictures on the left, I would call, that you saw earlier, the moving from a regular infrastructure today into a DPU-based infrastructure. And then we move it to what we call to the converged accelerated computing, where we have also the GPU as part of it to implement an AI-based accelerated workloads. In a way, what we do is what I show you here. We build the converged accelerated card, which is actually a DPU and a GPU on one card. And it can actually work in two different modes, but I would like to talk about one, I would say, unique mode, which is the what we call the DPU hosted mode. So in a regular environment, when you have a DPU and a CPU, each one of them is being or can be seen by the x86 on a PCI side. While if you're using this card, we can configure the PCI to be on the DPU to be a root complex, as I mentioned earlier. And in that case, the DPU will actually manage the GPU directly. So in a way, the GPU will not be seen on the x86. And by that, the use case, for example, which I mentioned earlier, can be fully contained on one card, and not only on this specific card, but just imagine that you have these cards implemented in all other nodes in your data center. So each node is like an agent, and still, can be act as an enforcement to implement any kind of update on the rules or on the network, depends on whatever processing you have been able to do, and act according to the GPU new performance rules that need to implement on the DPU.
5 minutes left.
Yeah. So to sum up, I want to give you some, looking on the future, when we kind of announcing just lately on the last GDC by our CEO. So we have announced the next generation of BlueField DPU, which is BlueField 3 DPU. So that's going to be an amazing processor that we're looking forward to bring to the market and serve our customers. It's going to offload and accelerate data center infrastructure, similar to what I showed earlier, but much, much more further. It's going to be a 400 gig Ethernet and InfiniBand connectivity. It's going to have a crypto engine accelerations up to 400 gig. We're going to utilize 16 ARM cores CPU embedded with Connectix 7. And performance will be just dramatically increased and can be performance, for example, on the elastic block storage, we can get up to 18 million IOPS. And all the other engines are going to be fully utilized for the max bandwidth of 400 gig. And processing, networking, and storage and security will be also up to 400 gig total bandwidth. If we want to look on some numbers that I've also added here, so a quick comparison between BlueField 2 and BlueField 3 APU, you can see that we increased the bandwidth from 200 gig to 400 gig. Performance of DVDK, for example, in RDMA are going to increase accordingly. If you look on a spec-int compute, so we are moving from 70 to 350. VTIO acceleration that we have talked earlier, so we are going to double the performance from 40 mega per packet per second. We're going to hit 80 mega packet per second. On the IPsec accelerations, we're going to get up to 400, and as well as on the TLS. MaxSec acceleration will be added, and the NVMe snap, which stands for the NVMe emulation, NVMe fabric and emulation, is going to also increase dramatically from 5.4 million IOPS up to 18 million IOPS. To sum up with and give you some highlight for the future, so we talked about the BlueField 2, which is today in production and being used by a wide range of customers and partners. We talked about the BlueField 3, which we just announced in the latest DJC. That's going to be upcoming next year. And also BlueField 4 on the roadmap, which is going to be in 2023, in which we're going to have 1,000 spec-int, and that's going to be a huge SoC performance and answer with the embedded GPU inside it that will be able to perform very, I would say, enhanced workloads for the data center of tomorrow. And by that, I leave about, I don't know, 2 minutes for questions, if we can address any quick questions.
Beno, Gadi here. There are a lot of good questions in the chat. It will take more than 2 minutes, so I guess you can also address them by message. But just to speed things up, people are asking about the BlueField 2X. What is the timeline for that?
So that's going to be the first sampling will be by the end of this year.
Okay, perfect. Thank you. And then we had some questions about GPU Direct and the DDR speed. Is it going to be higher in Spectrum 2X? Is it going to be DDR4, for example?
So today on BlueField 2, we support DDR4 3200. In BlueField 3, which is the next one, we're going to support DDR5 5600. And that's going to be also equivalent for the BlueField 2X and BlueField 3X. For BlueField 4, it's still under design, so I don't have numbers yet for that one.
Then we also had 2 questions about deliveries, the fact that we can, the BlueField are certified also outside of Nvidia products and systems. So you can get the cards today and plug it to your own server and use that and test that. We also had questions about deep packet inspection capabilities.
What is the question?
1 second.
The question largely is about looking at packet headers in custom UDP packets, which is what we deal in, and then using that to make decisions on where to DMA packets to.
So we can perform that. We can do that. As I mentioned, there is a regular expression engine that we have embedded inside the BlueField DPU, which together with the Connectix inline actually can do this kind of inspection that you mentioned. We also have some other applications that utilize this engine. This is all available under Docker. and you can log on. I didn't mention that, but you can log on to the Docker webpage, register, and get access to these libraries, to documents, and many other good stuff that can give a lot of information on how to implement and what kind of, even some examples, okay, some example applications that you can also run on your end and get some idea of how things are working and what kind of things you can develop based on the engines.
That's great. Unfortunately, I'm going to have to cut you off there, but by all means, continue the discussion on Slack and in the Zoom chat. Gadi, it seems like you've already jumped into the fray. Maybe you could share your screen and we could get going with your talk.
You all right there, Gadi?
We can see your screen, so whenever you'd like to go.
Oh, sorry, I was on mute.
Yeah.
Sorry about that. So Gadi Godanian, I've been with Nvidia for the past 9 years. I'm mostly focused on the Ethernet switch product for Nvidia for EMEA. Today I wanted to talk to you about cloud scale efficiency. Basically, what can we learn from the big cloud and hyperscalers, and how can we implement those methodologies into our own data centers and enterprise, and wherever there is a network requirement. So basically, you've seen this slide. My focus will be on the networking itself. So that means the switches, also the DPU, where everything connects together, CPU, GPU, and DPUs. So what we're seeing today is, how do I remove this? Anyways, so what we're seeing today in the networking industry, that there is a move to the cloud model, right? Wherever it's possible to do that, we are doing it. So whether like literally putting stuff in the public cloud or creating a cloud-like infrastructure internally. And what we see there is that a lot of it is pushing actually for software-defined automation. That means that eventually, moving forward, we want to reduce as much as possible the manual operations. A lot of those approach are considered DevOps-like approach. So things that we've seen so far with code, literally the same way that we are looking at managing our code and our application. So taking those approach and getting them into the networking world. So creating the net DevOps approach. So taking a look at your network configuration as if it was a real code for your application using GitHub or GitLab, and we'll of course expand about that in the coming slides. And then we're also seeing a cultural shift when it comes to skills. So back in the days, right, getting a certification from a specific vendor was the most important part, because then you knew how to talk the language, right? So it could be, Cisco, Juniper, whoever, and taking the certification. What we're seeing today is there is a shift there from CLIs to more of an API. So now it's more important to be, for example, AWS certified than a specific vendor CLI certified, right? And we're seeing it from across the industry. This is just a quick example. I won't go too deep into that in terms of the data center switching market, right? Where we see the move to public and private cloud. So you can see different vendors, tier 1 cloud, tier 2 and 3, telco, and you can see that the legacy enterprise is going away, where more cloud-like solutions or deployments are getting providing more and more revenue in the billions. So when it comes to private and public cloud, right? What are the main cloud needs? We're looking at operational efficiency, hardware efficiency, and actionable visibility, right? Visibility that can makes us can get us to time to innocent, time to result very fast. So and these are the three topics I wanted to talk about. So let's start with the operational efficiency. The way we see it today, the more automation you add into your infrastructure, right? It doesn't have to be day one. It's a gradual process. You need to learn the languages. You need to understand how it works. You need to train your people. But the graduate process will eventually save a lot of time in terms of IT. And then we'll also talk about hardware and the visibility. So we're starting with operational efficiency. 1 second before that, everything I'm saying here, like for example, this number 36 times less IT, right? This is coming from an IDC report done for networking, for Nvidia networking when it comes to automation. I'm not going to focus on that. I'm not here to promote this specific, our specific vendor, but I'm here more to talk, technically to technical people on where we see this going. So I won't go over this slide, but a lot of the information is backed by this report. If you're interested, I can share this report. We also have a webinar from IDC explaining this. But this report backs up what I'm saying about the efficiency. So let's start with the first bullet, which is the cloud scale efficiency. Now, as you know, NVIDIA have acquired Mellanox and Cumulus, and now we're all together are part of this the NVIDIA and networking business unit. And what we're doing right now is we're learning from NVIDIA as the networking arm of NVIDIA on how to do things, how to be much better. And one of those items that we see here in my screen is actually on first glance looks like it's not even relevant. But in NVIDIA believes that anything that is built will be virtualized. Everything that you have today and it's built, it's physical, will be virtualized beforehand. Anything that moves will be autonomous, and anything autonomous will be simulated. So basically what we're doing here is taking it to the networking world. So in GTC, we've presented one of our customers that have created a digital twin of its own production line for the car manufacturer. And basically what this specific customer of NVIDIA did is made a one-to-one exact copy of their real production into simulation, where the robots and where the car crashes and where everything can be tested into much higher degrees before even putting a car into the production line, before putting the first doll into the car and crashing it into the wall. And by doing so, of course, you can get much more data before even starting to deploy, before you have any hardware once at all. And the same concept is now being moved into networking. So basically what I'm saying here is, before the first box even arrived to the site, 90%, 95% of what you're doing can be automated, can be simulated, and can be tested in a virtualized environment. So when the boxes are there, when the cables are connected, you basically push a button, and everything, all the configuration, all the automation, all the needed items for the network to work will already be implemented beforehand. And this concept, basically, we call it the digital twin. And we see it as a way to transform network operation, right? This is not necessarily NVIDIA. Every customer, every vendor will have their own approach. Some customer will build their own infrastructure to talk about what I'm saying, but this is the general idea: is that you have the physical twin, which is the actual network that you want to build, right? This is where you want to go. When you buy the kit, this is how the kit will be connected. This is how the data center will look like. So even before ordering the kit, you will create a digital twin. We can talk about what we did in NVIDIA in order to create that. And then simulate everything, automate everything, use your tools in virtual environment, which is exactly one-to-one as your physical twin. So, and by doing so, when you're ready to deploy, all the errors have been caught already. All the validations, all the automations have been done already on the digital twin. So we simulate the network, then we start a validation process for security, automation. You can do upgrade processes, failovers, and so on and so forth. And then when you're ready, you basically deploy with confidence, because the Automation tools are ready. The upgrade process have been tested, and everything is even before the kit have arrived into the destination. Things we cannot test are things, of course, that are hardware related, like scale, like latency, like packet buffers, and those things. But other than that, everything else, monitoring, automation, configuration, can be done in the digital twin. And one service that we have in NVIDIA is called NVIDIA Air. Basically, we built in the backend using third-party open source tools, a proper CI/CD pipeline that lets you build your own virtual twin environment. It can be as big as you want. Everything runs automatically on our services. So we use it as a sales cycle, as a sales tool in the sales cycles, but it's a service that you can use NVIDIA in order to get the confidence in the product that you want to. So if you're interested in that, that means spinning live environment that is a copy of your environment that you're testing, that you're playing, that you're mimicking. Reach out to me and I can show you how you can get access to it. It's free of charge. It's open for partners and customers of NVIDIA, and also potential customers. And this is just an example of how are we doing the entire CI/CD process. So using GitLab, using the Air that I mentioned, Ansible for automation, NetQuits are validation tools. We also have and Neo. This is a different flavor of validation tools. And then you're also getting the report saying, oh, this configuration was wrong, was okay, problem with it, so on and so forth. Any questions? Now it will be a good time before we move on to like hardware efficiency and telemetry. So super simple idea and concept as part of the CI/CD, part of the digital twin. Yeah.
If no one else has a question, I'll interject with one. You noted in passing that you can simulate everything except latency and hardware buffers and things like that. And I think a lot of people on this call have been burnt by those very things. Mm-hmm. Is there a way to investigate those aspects of networks prior to deployment for the kind of large networks that we use in radio astronomy?
Yes. So I'll give you an example. One of my focus verticals in the past few years was financials, right? So a lot of it is talking about microburst absorption and latency and jitter and fairness. So those are things that you need boxes, right? So basically, the way to look at it is if those things are important for you, first of all, we can share what we have today in terms of like performance through our QA cycles. And then if you're happy with it, right? So you need to take a look as two avenues. One is the automation, is the visibility, is the configuration. This is what I'm talking about here. Second is the actual performance that you got burnt on. So first of all, on that avenue, you can take a look at what we're showing in terms of our reports. If you're happy and you like it, then we work together, we ship you a box so you can test yourself, or we offer our own lab in Israel, which is connected to XCI equipment with a dedicated field application engineer that works through the POC stage with you and run your reports if you need help with that. So it basically, we're running the report for you, or you're running your own reports with the kit that got shipped into your environment. But that answers like 1-2 switches, right, when it comes to performance. But looking at the grand scheme of things, when you want to connect multiple pods with exit lifts, and then you need tens of switches, then this is a problem, but you don't need any live kit for it. You can use it. You can use, for example, NVIDIA Air. So to your questions, it's basically a mixture of doing whatever you can with Air, and whatever you cannot do with that, which is related to performance, you're working closely with us, and we can either send you a kit and you can deal with it, or we can work together internally. That answer your question?
Yeah, thanks. That was a great answer.
Cool. But I think the first step is you look at our reports. You like it? Perfect. You don't like it? That's fine. But this is like something that we already have because we ran it for several different use cases, several different verticals. I just give finance as an example because this is where I was involved. So if you have any concerns, if you have any questions about performance, reach out to me. I have reports which are ready. We have third-party reports. And if it's relevant and we move on, then we can create your own reports with our assistance. So It's a good question because it's a good segue for the next topic, which is the best-in-class performance. Again, I'm not here to push Nvidia down your throat, but this is just like our Ethernet switch portfolio when it comes to hardware. When it comes to software, real quick, we have a different flavor of operating system. We have Cumulus, we have Onyx, we support Sonic. So this is a bit of a different topic. I only have 30 minutes, so I was not talking about it. But I've already seen questions about Sonic in chat. So any questions about the operating system itself, reach out to me. We have different flavors for different use cases, or ask now in chat, and I will answer at the end of my session. What you see in front of your eyes is just to give you basically to let you know that whatever hardware platform you need, we'll probably have it. And now let's dig deeper into what you need to look for when it comes to like cloud scale operation. So over here, we have 3 examples of very important items when it comes to hardware efficiency that I'm looking at. I really want to focus, just because we don't have too much time today, on a fair bandwidth sharing, which is how the switch manage buffers. When it comes to buffer, from my experience, it's almost like religion. Some people believe that deep buffer is the right way. Some other people go with shared buffer and fixed buffer. We are seeing a massive important to the buffer between, for example, the use case and the application to the buffer architecture. And we're real believers in a shared buffer architecture. So what you see on the screen right now, on the left, here in the middle on the left, is a shared buffer architecture, meaning that each color is a port. Each port gets fair share of the pie, where competitors, whatever, this is a fixed buffer architecture. You can see one port consuming half of the buffer, while the rest of the port can consume a fight for the bandwidth. So that literally means that the port physically that the cable is connected have an impact on performance. And this is something that we do not like. So 2 examples here. On top, shared buffer, 3 senders, 1 receiver. We have a congestion here. On a shared buffer architecture, doesn't matter where you connect those servers, there will be a weighted round, there will be a pure round robin between the 3, and each one will get 33%. On the split buffer architecture, you can see the first server is connected to 1 split of the buffer, while the other 2 servers are connected to a different split of the buffer, and the round robin is actually being operated between buffers. So in that case, you will see 50 gig, 20, 25, and 25 when it comes to congestion. This is a Facebook report showing the problem with a shared buffer architecture. In fairness, this is an open report. You can read about it. This specifically was done for storage, but there are other applications as well. So basically what we're saying nowadays, it's not only buying a switch, you also need to understand what the switch buffer architecture like, where is the right use case for it, is it sensitive, is the latency affecting it, is just the buffer, what's going on with the buffer absorption, if the traffic is very bursty. It really depends on the use case. Any questions about the hardware before I move to visibility? Let's see, how are we in time? Cool, 10 minutes. Okay, so again, questions, feel free to shoot in chat. When it comes to visibility, what we're seeing nowadays is that if you take a look at the data center, in terms of like protocol, there is reduction in complexity. We're seeing less and less like traditional protocol being used, and there is more shift to like BGP based, or if it's multicast, so PIM and EVPN, VXLAN. So there is less focus on actual protocols and more focus on visibility, on understanding what those protocols are doing. So in NVIDIA, we came up with something which is called What Just Happened. This is a tool to accelerate the time to root cause. The idea behind it is because we manufacture, one of our unique selling point is actually that we manufacture the silicon, the system, and then the operating system on top. So we have an end-to-end capability to take a look at each packet that got dropped in the network. And instead of just raising a counter somewhere, we have an ability to mirror this specific packet into CPU and produce a what just happened event for any packet that got dropped. So that means that instead of just sending you SNMP, syslog, sflow. So a lot of information which are good in many cases that you don't need to do anything about it. We can send that, right? These are protocols, standard protocols in the industry. What we'll also do is we will stream what just happened, distilled stream that holds the packet header and the detailed description on why the packet got dropped. So I will give you an example in a few minutes. So now basically we baked the some sort of analytics level into the silicon itself. So all you need to do, whatever you're using, third party, Mellanox, Onyx, and Neo, Mellanox, Cumulus, and NetU, those are our own operating systems and visibility tools, or open third party like Grafana, Kibana. We are sending you a detailed stream of what just happened event that tells you about problems and packet drops in the network. And this is an example. You can see different flavors of operating system here. Onyx, Cumulus, Sonic. What just happened run on all of them. We have an agent running on the switch, communicating directly with the SDK. This is why it's OS agnostic. And then the streaming telemetry is being done automatically to whatever controller you're using, whatever database, time series database you're using. We support several of those. Any questions about it, feel free to reach out to me and I can tell you if it's supported or not. And I want to show you some examples. It's a very strong tool. So over here, this is one of our management tools called Neo. So you can see over here the pie that shows you real problems. So port loopback filter, destination IP is a loopback, IPv4 IP source MAC equals destination MAC. This is a bit of a weird one, right? A cable and transceiver are maybe overheated, auto negotiation failure, access list drop. So literally the actual problem, the actual reason for the packet drop. And then you can drill down into each flow and see what's the switch name, the IP address, the port, Ethernet, and then literally like almost like a pickup, the Ethernet, the IP, the transport, the VXLAN header. So the entire header is also being kept. So this is an example from Neo. This is an example from the switch itself. If you don't want to go to a centralized location and you want to do it on a per switch, this is from the Onyx operating system. And this is from the CLI. Few examples here. You can see things like buffer drop in terms of the drop reason. This one looks a bit synthetic coming from Ixia, but you can see like buffer drops that in the network. Weighted red, so that means that we drop because of tail drop or weighted red, and so on and so forth. So it can be more of a network monitoring like we see here, like port loopback, destination MAC, VLAN, spanning tree, stuff like that. Or it can be more deep packet related, buffer related, like those events here. And I have for more example, you can extract it into pickup and store it in pickup and analyze it if you want to. This is another example just from a different management tools that we have called NetQ. And this is from Grafana, for example. Basically, I think this was a TIG instance. So Telegraph, InfluxDB, and Grafana. I do have 5 more minutes. There is a small but very interesting topic I wanted to follow up on when it comes to the DPU discussion. We are now pushing to something that we called host-based networking. We believe that the BlueField, the DPU, gives you now the ability to take the functionality, some of the functionality of the switch, of the Cumulus switch, for example, in that case, and push it into the DPU on the right side. So basically, by doing so, let me just jump into this slide. By doing so, where this is what you see right now is the modern data center today, what we're saying is instead of having the line over here in terms of the top of rack, where it comes to things like layer 3 or management or access. Basically what we're saying, we're moving this line of network responsibility from the top of rack to the actual server. So if, for example, the unit that's and the unit in the organization that controls the DPU is not the server team, but the network team, basically we can extend the networking influence into the server. And by doing so, we can have layer 3 running from the server itself. We can have the same automation tools that we're using for the top of rack, for the spine switches, also for the DPUs, and so on and so forth. I don't have too much time to talk about this, but that's the idea. That's what we're pushing. That's where we think the next generation of data centers will evolve when it comes to networking over the DPU. We have many ways that I can explain why and how are we doing it with Open vSwitch and so on and so forth. We don't have time for this. I just want to give you the idea behind it. And what I'm presenting here is running Cumulus Linux inside of the DPU. And by doing so, extend the layer 3 into the network and start having a host-based networking approach in the data center. I will take one more minute, and then I will look at answering the questions. So this is a summary of the idea. Some advantages that we can see here, which is it dramatically simplifies the host networking configuration, because if the BlueField is taking care of all of the networking side, then the host itself, in terms of configuration, is pretty straightforward. All the links, the virtual links, are trunk between the host to the BlueField, and that just makes the server teams' lives much simpler. Think about it like almost like the same thing that happened in the storage, where we moved from the old days of the storage, or we're moving into a more IP-based, Ethernet-based storage. So the same thing is happening here. End-to-end control for the networking team, and some other advantages here. I really want to stop here in order to answer some questions. But again, if you have any other questions outside of this, or when you're taking your coffee break and suddenly you get this question in your head, feel free to reach out to me. This is my email. Feel free to find me in LinkedIn. I will be happy to take this discussion deeper. We only had 30 minutes. I wanted to plant like some ideas, but if we want to get deeper technically, we can do it easily. Questions?
Going through the chat, Gadi, there's a question from early on from Lincoln Greenhill asking about how the AI switches differ from spine switches.
Yeah. Okay. So that's so basically when it comes to AI switches and spine switches, what we're seeing is that first of all, it's a 200 gig base. And this is where we see more use cases when it comes to AI. There is no real like the switch itself it's the same switch, right? It's more of the configuration methods. How do you make the switch work the same way that you need it to? Because when it comes to AI, in many cases, it's an InfiniBand. It's an InfiniBand play in some cases, and when you want to use Ethernet there are some use cases in terms of how you need to manage the network, making it from a lossless network from a lossy network into a lossless. So I wouldn't say it's a marketing name, AI switches, but it's less on the platform, more on the configuration of the buffer and the ASIC and RDMA on Rocky or those things. I hope it answers it. But I think like it's more of a marketing name, putting the AI switch. It's basically the way you manage the switch, and the fact that it's 200 gig base, and the fact that it uses the right buffer. I'm sorry, it's not more sophisticated than that.
Okay, I think that covers all the questions in the chat. As always, continue on Slack as necessary. Thank you both, Gadi and Beno, for those great talks from Nvidia. I think a lot for all of us to think about, and I think Nvidia will keep playing a key part of all of our lives as we keep building things.
Thank you.
Thank you. And with that in mind, maybe let's move over to Gerrit Grutzeck now, who is at Max Planck in Bonn, talking about another bit of NVIDIA technology, this time the Jetson, used in concert with FPGAs for DSP. Take it away. I'll give you a 2-minute warning.
Welcome everybody to my today's talk. The title is the U-Board, a heterogeneous platform for FPGA and GPU-based signal processing. As already said, I'm at the Max Planck Institute for Radio Astronomy and I'm a second-year PhD candidate. And before I start with my presentation, I would like to thank the Casper community and the local organization committee to allow or make it possible that I can today share my work with you. So let's start with a brief look at the heterogeneous architectures. Heterogeneous architectures are architectures where we have two different processing systems. For example, we have an FPGA, which is hard real-time capabilities and has flexible interfaces, so we can interface our ADCs and DACs with it. On the other side, we have a GPU, which has compared to an FPGA in high floating point computing power. But as soon as we have a GPU in our systems, we have an operation system involved. That means we have a latency and we have a jitter every time we call some kernel functions or something like this. So now the idea of a heterogeneous architecture is to take the best of both worlds and combine it. And for this approach, we are using the Jetson AGX Xavier module from Nvidia. This is a system on a module which is primarily used for autonomous machines like self-driving cars. The system on a module consists of different parts. The most important part is, of course, the processing system in the middle. This is composed of CUDA cores and ARM cores as CPUs. Furthermore, we also have DDR memory around the processing system and a non-volatile flash module, for example, for the exploration system and configuration data and the programs itself. If we now want to connect such a module to our custom PCB or the developer kit from Nvidia, we have this module connector and then can just plug in this module on our PCB. Now let's have a look on the technical details of this module. We have a GPU with 512 CUDA cores and 64 Tensor cores. And these are also very interesting, as we have seen in the talks before. The CPU is an 8-core ARM CPU with 64 bits. And the typical size is for L2 and L3 caches. Interesting here is the memory. It's 32 gigabytes with 137 gigabytes per second as bandwidth. And this is due to the architecture, both usable from the CPU side and the GPU side. So we don't need these expensive copies we have seen all day long. Now we also have to connect this module to our FPGA. For this, we have 8 lines of PCI Express generation 4. And finally, for controlling and as controlling interface, we have a gigabit Ethernet. Now let's start with the U-Board itself. We are developing this U-Board as a general and universal board for both signal generation and acquisition. And we have a very important point here. We want to have a phase current signal generation and acquisition, as we have some applications in mind for this board, which heavily depends on this phase current signal generation and acquisition. As already mentioned, we are using PCI Express as interface between the FPGA and the Jetson module. This allows us to access not only one memory region from the CPU and GPU, but also the same memory region from the FPGA side via DMR transactions over the PCI Express bus. And furthermore, we can now use the DDR memory of the Jetson module as a buffer to hide the jitter which is introduced by the operation system. This is done in the following way. We have some queue for transactions in the FPGA, and we try to always make sure that this queue is quite filled, so that if a hiccup happens in the operation system, the FPGA still have target addresses where you can send data from or to, so that no data is lost and the system is running all the time. Now let's look at some example applications for such a system. As already mentioned, these are applications which are sensitive on the phase between signal generation and acquisition. One example are MeerKAT readouts, and another example is the time domain integration, which is, for example, used in laboratory spectroscopy. To these two applications, I will later show also more information. Now, give the hardware itself a look. And we want to start with the signal acquisition. We have two ADCs on the board, one high resolution ADC with a high sample rate and one low resolution ADC with a lower sample rate. The bigger ADC, so the one with higher resolution and higher sample rate, has 12 bits of 12 bits resolution and 10.4 gigasamples per second as sample rate. We can configure this ADC both in single channel mode, so that we have one channel with 10.4 gigasamples per second, and also in dual channel mode, so that we have two channels which with 5.2 gigasamples per second each. The second ADC only has a resolution of 8-bit and can run up to 2.56 gigasamples per second. This one can, for example, be used to optimize the calibration of EQ mixers in our MeerKAT setup. The signal generation is done with two DACs. Both of them have 16-bit resolution and run with a sample rate of 5.2 gigasamples per second. An important mark here, both the fast ADC and the both DACs are running on the same sample clock. And this is due to this constraint that we want to have a phase currents between both systems. And if we would, for example, use two PLLs to generate a sample clock for the ADC and one PLL for the sample clock for the DAC, we would introduce a small jitter between both clocks, which would result in a not so good phase currents between the signal generation and acquisition. As we now have cleared what is used for the analog conversion, we now want to look at the digital signal processing capabilities of the system. Currently, we are using a VCU 118 board, which enhouses an Xilinx AltaScale Plus Vertex, which also has connected 5 GB of DDR4 memory. And of course, we're also using the Nvidia Jetson module I introduced earlier. So now give the current prototype a look. This is the current state of the project. On the left-hand side, we see our custom PCB, where the DACs and ADCs are placed. This custom PCB is connected via an VMC Plus connector to the Xilinx board, the big board you see in the middle. And from the back, a little bit difficult to see, is the Jetson developer kit connected via PCI Express. And on the custom PCB, you see different SMA connectors for reference clocks, for ADC inputs for the fast ADC, DAC outputs, and the ADC input for the slow ADC. Now we come back to the possible applications we are targeting with this board. So let's start with the MeerKAT readout. MeerKAT is a detector which is supraconducting, and its resonance frequency changes with the infalling photons. This means if we place a readout tone in this resonance frequency of the MeerKAT, we can reconstruct the unfolding photons or the flux of the photons due to the phase change of the signal after it passed through the MeerKAT. And then normally we don't use one MKit, but 1,000 MKits, for example. This means we have to generate 1,000 different tones, which are then applied to the MKits and then read back and analyzed what is the phase change here. For this, we are saving the waveform with the tones in the DDR4 memory, which is located on the Xilinx board, so close to the directly connected to the FPGA. From this memory, we are streaming the waveform to a component which is doing a fine-tuning. This means we are shifting the readout tones all together a little bit in frequency to hit the MKit resonances as good as possible, and then stream the data to the DACs, which then outputs the analog signal, which is then applied after mixing up to the MKits. The resulting signal after the MKits is mixed down again and connected to the ADCs. The data from the ADC is then streamed again into the fine-tuning, which is doing the inverse operation now. And the resulting data stream then is given to 16 parallel 64K FFTs. And after this FFTs, we have a masking. Because we know where our tones are in the frequency band, we don't have to process all the frequency bins of the FFT, but only the bins where we have placed a tone. So we only transmit these tones via PCI Express into the main memory of the Jetson module, where we then have a CUDA kernel, which combines this 16 parallel data sets from the FFTs into one result. This result is then post-processed, like doing some noise decorrelation, filtering, and integration. And the result is then sent via the gigabit Ethernet to some PC, which is writing it to the disk. And the controlling of the whole system is done via the software which is running in the CPU cores, which is also controlled via the Ethernet connection. Now, this is a limited MKit readout, as we cannot place the tones as we like. We only can place it directly in the center of each FFT bin. We are also thinking about a more complicated MKit readout, which use an analysis and synthesis filter bank to allow more freedom here. Now, the second application we already had in mind is the time domain integration for laboratory spectroscopy. For example, in the short pulse spectroscopy, we are generating a short pulse, which excites our molecules, which are then sometime later giving photons back, radiating photons back into our receiver, which is then connected somehow to our ADC. In this design, we are streaming the data from the Jetson module via a waveform buffer directly to the DACs, because we need the DDR4 memory as an integration buffer. And straightforward, we get the data back from the ADC, which is then combined with the already integrated data from the memory in the first stage integration on the FPGA. Here we also select some subset of the samples, of the integrated samples, to send them to the Jetson module, where we then have a second stage integration. That we are doing because the DDR4 memory of the FPGA, or connected to the FPGA, is quite limited, while we have on the Jetson GPU module much more memory available. So on the FPGA side, we are handling 16 bits, while at the Jetson module, we can integrate up to 64 bits. And again, the system is controlled and read out over the Ethernet connection. Okay, so much to the concept. A short conclusion. I presented you a new closely coupled heterogeneous architecture, which is based on the FPGA and GPU, which uses PCI Express as fast communication channel. And the GPU is an embedded module which can be placed on the edge. This means directly in our instruments. And we also saw that we have a wide range of applications, a broad instantaneous bandwidth of 5.2 gigahertz, both in signal generation and acquisition. The CUDA framework allows our fast prototyping because we don't have time-consuming synthesis and implementation runs. And furthermore, the machine learning environment gives us possibilities to enhance our instruments to get even more out of our data. The current state is that the timeout integration and the MeerKAT readout are implemented on the FPGA and CUDA, and I'm currently working on control flow and infrastructure. And the target for the MeerKAT readout is a complete custom board where we just plug in the Jetson module. And maybe a little outlook, what can come in the future. On the roadmap from Nvidia, we have a device similar to this one, which has 2048 CUDA cores, and so much more processing power as we have currently. Thank you very much for your attention.
Thank you, Gerrit. There are some questions in chat as well as some applause and general expressions of this being cool work. Unfortunately, we're a bit over, so I'm going to have to usher you out, but yeah, I encourage you to read through those. And then without further ado, if we could have Hariharan Krishnan from Arizona State, who I think now is going to be talking about the EPIC imaging correlator.
Can you hear me?
We can hear you and we can see your slides.
Okay, thanks. Okay, hello everyone. So I'm Hari, I'm a postdoc at ASU. So I'll be talking about a novel GPU-based real-time imager for compact radio arrays that we have been developing for the last couple of years. And here you have the team members from different universities. So this work is mostly in collaboration with the folks at UNM. Here's a broad outline of my talk. So I'll give a very brief motivation for the project and talk about radio interferometry and conventional correlator concept, and discuss the direct radio imager called EPIC, and show you the optimization and conventional imaging results and give the current status and finish up with a summary. So the motivation for this project is mostly to develop a real-time imaging system that can observe radio transients like FRBs and meteor radio afterglows and so on. And of course, the technical motivation for current generation and next generation radio telescopes is sensitivity, wide field of view, and so on. And to achieve these transient science goals, you always require imaging at wideband frequency and very high time resolution. And the current and next generation radio telescopes, of course, rely heavily on the technological advancements with the digital signal processing hardware. So just a brief introduction to radio interferometry for non-radio astronomy folks at the Casper Workshop. So the basic receiving element in any radio telescope is an antenna. And the fundamental unit of any interferometric synthesis telescope is a two-element interferometer, which is simply which consists of two antennas separated by a distance. And these antennas record the sky signal as voltages, which are then multiplied and integrated, which is a record of the correlation function. And the correlation function is a direct measure of what we call the visibilities, which is simply a spatial sampling of the sky at an angular resolution corresponding to the baseline separation between these antennas. So the implementation of this correlation operation is done using conventionally using an FX correlator, where we Fourier transform the voltage signals from the individual antennas to frequency domain, and each of the voltage streams in individual frequency channels are then multiplied and integrated to get the visibility function for every frequency. As you can see, this design has worked so well for decades for antenna arrays which consist of tens of antennas, or even hundreds of, or even maybe a few hundreds of antennas. But the complexity, the computational complexity of FX correlators obviously increases when you consider more than like 1,000 elements or even 500s of elements and so on. So to solve or to as an alternate solution to this FX correlator, we propose a new correlator called the E-field parallel imaging correlator, which is highly found to be highly efficient for real-time imaging for large N on the order of thousands of antennas and densely packed arrays like Hera, Sky, Idea, and Hyrax, and so on. So it is based on the modular optimal frequency Fourier mathematical concept for direct Fourier imaging. So without getting into the mathematical details, what we do is, instead of measuring the visibilities, we directly grid the electric fields that are measured with the antennas onto the EV plane, and then take a spatial Fourier transform, a 2D Fourier transform, just synthesizing the aperture on the fly. So the significance here is that we are able to reduce the computational scaling by a factor of number of grids into the multiplied by the number of logarithm of the number of grids instead of number of antennas squared. So this is significant computational reduction. So here's a block diagram representation which represents the flow of the signal in EPIC. So we get the antenna voltages from each antennas, which are then Fourier transformed to the frequency domain, and then these are delay calibrated and then gridded onto a UV plane. And this UV gridded voltage pattern is then Fourier transformed, squared, and integrated to get the final image. So we have the first deployment of EPIC on one of the LWA stations at Sevialta National Park. So LWA stands for the long wavelength array. So it works in the frequency range between 3 and 88 megahertz. So it's basically a compact array of 256 dual polarized dipole antennas that are arranged in a pseudo-random pattern within an effective aperture of approximately 100 meters. At the LWA Sevialta, we have an advanced digital signal processor, which gives out different modes of data. We have a raw F-engine data that comes from a Roach 2 board, and we have beamform data, and then a transient buffer node data. For the EPIC, the F-engine data is more relevant, and so each of the backends that we use is commensal. So the LASI is the LWA all-sky imager, and Wilbur is another pulsar backend, and EPIC is the one that we are developing. So each of these is on different servers, and the EPIC is on sits on a different server that's connected with a 40 gig connection with the ADP, and it receives the F-engine data in 12 different streams. So each of these 12 streams is 12 subbands of data, with each subband corresponding to 3.3 megahertz of band, and consists of 132 frequency channels at a frequency resolution of 25 kilohertz and a frequency resolution of 25 kilohertz and a time resolution of 40 microseconds. The overall data rate that we get is approximately 1.5 to 1.6 gigabytes per second. So the complex spectra is the input that goes to EPIC. So EPIC can actually operate in two modes, either an offline mode, which uses the TBN data, which is basically voltage data, and which is then Fourier transformed and delay calibrated and gridded, and the online mode, where we directly use the F-engine complex voltage waveform. So here's a block diagram representation of what happens in EPIC. So the packets are first captured and then decimated in frequency, and then we do a delay calibration, or basically a delay correction actually, and then we grid the voltages using a gridding module, and then we have the FFT of the gridding module, which gives you a gridded X and Y voltage pattern, and these gridded X and Y voltage pattern are then cross multiplied and sort of integrated to get the different polarization polarization outputs, and then these are squared and accumulated to get the final image. So here's an input sequence that goes into EPIC. So we have the X and Y polarizations alternating, and then we have the channelized sequence, and these channelized sequences are then sequenced in time. So this sort of pattern is required to maintain the memory coalescence that is required for EPIC to achieve high optimal performance. So here's the first result from the deployment. So it's a snapshot image of the sky that shows you a meteor reflection event that was recorded with the first deployment. This was, I think, a couple of years back. You can refer more details on the implementation itself at Kent et al. 2019. So the instantaneous bandwidth that we achieved with the initial deployment was approximately 400 kilohertz per GPU. So we needed to sort of optimize this to get to be able to process more bandwidth. So one of the main changes that we made was the hardware. So the first deployment was implemented on a GeForce 980 GPU, and the current commensal system, which consists of 2 GPUs, has GeForce 2080 Ti. So this is the one that we are using right now. So this hardware change, of course, obviously improves the performance by at least a factor of 2. And in addition to the hardware change, we always had to optimize the EPIC, specifically the independent modules that are used in EPIC. So the first optimization strategy that we adopt is the memory optimization, where we try to reduce redundant memory accesses in the GPU, within the GPU, and increase the memory coalescence by changing the memory access pattern itself. This was something that was touched upon by James yesterday in his talk, because the computation itself may not be the limitation, but the memory access pattern can severely limit the performance of your pipeline. And we also increased the shared memory usage and reduced the global memory accesses within EPIC. And we also changed some instruction level optimization. We also made some instruction level optimizations, and we replaced some atomic functionalities that were implemented, which were not required for EPIC. So this sort of improved the performance of EPIC, and we are now able to run EPIC at about 80 to 90% of the data gulp time. So here's a sample. So here's a plot of the gridding module that we use. So we base our gridding module on the work distribution strategy that was described by John Romein in 2011. So we sort of optimized the gridding module by increasing the parallelization of how the antennas are gridded within the module. And you can see that we are able to gain a factor of 2 improvement almost. And this is one of the crucial blocks within the EPIC, because this also has to, but at this point we don't really do any convolution operation, but we have now given provision for convolution operation and also increase the speed of processing for this particular module. And we also replaced a module that was already in Bifrost. So in Bifrost has different blocks, which are so one of the blocks is the map kernel. So the map kernel was used to implement the grid multiplication and getting the final polarization product output. So we replaced the map kernel with the matrix multiplication module that is specifically optimized for EPIC, and that again shows you a significant improvement in the speed. The matrix multiplication here is basically a Hadamard product and then some amount of addition. So more details on the Bifrost will be discussed by Jayce in his talk and maybe the tutorial. So here's a sample image from the commensal imaging that we performed on the LWS station. So what you see on the left is an EPIC image that's at 31 megahertz. That's band integrated for 1 megahertz and time integrated for 1 second. And you can see that I'm also showing you a comparison with the Lassie image, which is a sort of a 4 megahertz integration and a 5-second integration. So you can just to compare the sky, how the sky looks with the EPIC and the Lassie. So in addition to the imaging, we are also able to extract light curves from each of the individual, from different sources within the field of view of the sky. So here you see a dynamic spectrum recorded from the sun. These intense features are actually solar bursts that were recorded during this time. Just to compare that these are not artifacts, we also extracted the dynamic spectrum for a different region in the sky where there are no sources, and you can see that it's quite clean. So in addition to the comparison of the light curves from different source locations within the field of view, we also make simultaneous beamformed observations during one of the commissioning tests. So what you see here on the left is on the top panel is an EPIC image just before the radio burst that was recorded using the beamformed observations, and on the bottom you can see a radio image during the burst. So of course the dynamic range is always a limitation when the sun is active. And here's another comparison for the wide field effect. So EPIC, I should just note that EPIC produces dirty images and not cleaned images. And we compared we took the TBN data and did an offline processing with EPIC, and we also did a simultaneous offline processing for the same data set with WSClean. So you can see that even though it's the dirty image, it still compares pretty well in terms of the sky image quality. But of course, cleaning and wild field effects need to be corrected. So that's the next planned upgrade that we have for EPIC, which we call the ARTIST, or the Aperture Array Radio Transient Imaging System, where we want to integrate additional modules like trigger processing, wide field correction, and de-dispersion, and RFI mitigation, and so on. So the trigger processing module, what we plan to do is sort of have a similar capability like what's already there available with the MWA, which will process VOE event triggers. And this is useful for EPIC because we don't really have additional, since we are already doing an all-sky imaging, we don't really have a very large response time or delay in doing this triggered processing.
Just 2 minutes.
Yeah, thanks. And there's already an incoherent dedispersion module that's available in Bifrost, which is called the fast dispersion measure transform. So all we have to do, as I showed you, we can already extract intensity for every pixel in the sky. So the input to the FTMT module is supposed to be an intensity in frequency and time, which is basically the dynamic spectrum. So we are able to give that. So once we integrate that with the FTMT module, we should have incoherent dedispersion for selected source locations in the sky, which is useful for transient sources like FRBs or even some giant pulsars and so on. And of course, the last improvement that we would like to include is the white field correction. We already have provision for a convolution kernel to be implemented in the gridding section itself. So we are just thinking about white field correction using W projection or W stacking method. So we are still exploring this at this point. So of course, depending on funding and other things, it may or may not go forward. So that's a different thing. So that brings me to the summary slide. So what you see here is a movie of 100-second images that were recorded during one of the commissioning tests. What you see is the galactic plane and the Cassie source and the solar burst that was recorded. The time resolution or the time separation between each frame is about 80 milliseconds. So this is a 1 megahertz integrated 1 megahertz bandwidth integrated image. So what we have with EPIC right now is we could process almost a full stream, that is 120 channels, 33 megahertz at a 32 cross 32 grid size, and the 72 channel or 1.8 megahertz 64 cross 64 grid size for single polarization. And we are just going through the commissioning tests and assessing the data quality and so on. So we're still preparing the paper on that. So, and we also have plans to upgrade the EPIC. If you have more questions or comments, you can always reach out to me. Thank you.
Thank you very much. We're running a little over because I am tardy. And so if I could direct you to the chat where a few people have asked questions, but in the meantime, if we could get Jayce Zhao set up. Jayce is at the University of New Mexico, where he is one of the co-authors of the Bifrost streaming pipelining engine, which he'll be talking about on behalf of himself and his collaborators. Take it away, Jayce. I'll give you a 2-minute warning.
Jayce, I think you might still be muted.
Let's try this again.
There you go.
Okay, share. Okay.
I can always
talk.
Okay. Go ahead.
Okay, yeah. So I'm going to be talking today about Bifrost, and so I want to give everyone an overview of what Bifrost is. Talk about some of the key concepts in Bifrost and what I think some of its advantages are over other pipelining systems. And then I'd like to shift gears a little bit and just give everyone a flavor of who is using Bifrost right now and where we're hoping to go with this. So to start off, Bifrost is a C++ Python framework for building CPU and GPU-based pipelines. So, you know, a lot of what has been discussed today is building these hybrid FPGA and GPU systems. And so Bifrost is definitely, you know, designed to work with those. But I also want to emphasize that it's also trying to be general purpose so it can work with standalone pipelines. So you can use it both in an online system where you're doing live data captures analysis, and you can also use it in this kind of offline standalone mode where you have some kind of pre-recorded data that you want to get through. And so we're trying to support both of these worlds here. And so for the GPU-based pipelines, we're using CUDA as our main driver. So we're targeting Nvidia GPUs. This is largely historical since Bifrost is the brainchild of Ben Barsdale, who worked with Lincoln Greenhill before being sucked up by Nvidia and never to be seen again. And we have a paper that's describing the Bifrost framework and the motivations and giving some examples that's in this Cranmer et al. Publication here. And everything that we do is also open source, and so you can find us on GitHub by either going directly to the URL listed or searching for LIDA Telescope Bifrost. Okay, so getting into the Bifrost concepts, I mean, there are a couple of core things here in Bifrost, and those are blocks and ring buffers, or simply rings. So blocks I kind of think of as atomic units of processing. So over here on the right, we have this kind of pipeline schematic, and so we have these gray boxes which represent blocks. And so this one is some kind of read operation. We have a copy operation that moves things from the CPU to the GPU, and then we do some work over on the GPU. We do an FFT, and then we come back off to the CPU in order to write. And so in Bifrost, these blocks are implemented as independent threads, and they take in some data, they do some processing, and they write it out. And so everything is connected together. These blocks are connected together by these ring buffers. They kind of glue everything together and make sure that the data can flow in between the blocks. So as their name suggests, they emulate wraparound memory. So you can kind of put data in and kind of continuously write to them if you have a long stream of data. And the rings also have a property that they are assigned to a specific space. So over in the diagram on the right here, you can see the rings. They live in particular area on GPU memory. And so that kind of saves you copy operations going between the host and the GPU, because you can have a GPU-based ring to shepherd data between all of your GPU-based blocks. And you only really incur that copy penalty when you initially get on the GPU, and then when again you're coming off of the GPU when you need to work on the CPU side of things. And I'll talk a little bit more about rings here in a minute. But you combine these blocks and these rings together, and you make pipelines. And so everything on the right would be a pipeline. So getting a little more into specifics, Bifrost is basically a Python front end that wraps fast C++ and CUDA on the back end. So we try to put everything that's really performance critical in that C++ and CUDA layer. So that's where the ring buffers are implemented, which we use for all of our interblock communication. So they have many nice properties. They're thread safe. They support multiple readers. So they have a single writer, multiple reader access pattern. And they also have an ability to guarantee data integrity inside the ring, such that data cannot be overwritten until all of the consumers of that data have released any locks they have on it. In the low-level C++, we also have a variety of common type definitions and this kind of BF array abstraction, which we use for shepherding data around. So when you access data in a ring, you get a BF array, which is basically a multi-dimensional array with C ordering. And as I mentioned, we try to put as much as we can into the C++ layer. So we have several modules implemented. We have FFT via cuFFT. We have matrix multiplications with cuBLAS. We have fur filters. We have a variety of things like that in the low end. And then up above that, we have the Python interface. And so the Python interface just exposes all of the functions inside C++ and all the classes as objects that can be interacted with. And so we do this exposure with C-type wrapping of all of the calls. So we use a module called C-typesGen, which automatically generates all of the C-types wrappings that we need for Bifrost. And then the Python front end makes it a lot easier to put things together. And we also expose all of the data. So the analog of the BF array in the Python space is a subclass of the NumPy ND array, which makes it really easy for you to work with the data that you get from the rings inside Python, because it works a lot like a NumPy array. And you can also use it with other things that work there and build on a lot of the existing tools. So one of the things that I really like about Bifrost is that the ring buffers aren't just a slab of memory that wraps around. They also are descriptive in the sense that they have headers tagged to them, and these headers can contain various information about what's actually in the data. And so you can use this to contain like observing parameters, what the axes and the dimensionality of the data actually are. And you can even put units in there in order to help keep track of this. And so this allows you to take the metadata at ingest and then propagate it seamlessly down your pipeline so that you always know what you're doing. And then if you keep up with this, you can also allow blocks to update the metadata. You know, if you have complex voltages on one axis and you FFT, then you can update the metadata to say that these are now frequencies and pass that downstream. The rings also support multiple sequences. So in Bifrost parlance, a sequence is a stream of data that has a common set of observational parameters. And so Bifrost can give you a dynamic pipeline where if your observation parameters change, you can change, the Bifrost will detect that as a change in the sequence, and you will receive a new stream of data with a new set of metadata, which propagates down that pipeline. We also make sure that we keep some kind of time tagging inside all of the ring buffers so that when you receive data, you know when that data is from, which is particularly critical if you want to do some kind of triggered reduction mode, you know, where you're looking for data from a particular time and you want to dump that or do some kind of extra processing. So with all these things, you know, as I mentioned, we have a lot of tools already in there. Hari has mentioned that we have FDMT, we have FTs, the FIR filters, and a variety of other things. And we try to make sure that what is in Bifrost is relatively general so that it can work kind of on quasi-arbitrarily sized problems. Okay. And then I guess the last big thing I want to talk about with Bifrost is this kind of built-in logging and performance benchmarking. So we don't just give you a framework and say, good luck. We include a variety of tools in there to help you really understand what your pipeline is doing, what the individual blocks in the pipeline are doing, how much time they're taking, how much data they're moving around, and try to give you some idea of what's going on. And we also expose that for all the networking work. So you can look at, you know, the actual packet ingress and what packets are being discarded, which ones are missing from the data stream and things like that. And so we try to make this complete package where you can build your pipeline and then have some way to analyze its performance and see how it's working and just generally keep up with what it's doing. So shifting now to talking about, you know, who is currently using Bifrost and where we're going. I guess the obvious thing is that I'm using Bifrost, particularly on this telescope here in the back, the long wavelength array. So we have a couple of pictures of some of the stations here. So this is a hybrid FPGA-GPU architecture. So we're using a combination of Roach 2s or Snap 2 boards to digitize and run an F engine and then transmitting that data to GPU servers where we do a variety of data processing. So we have modes where you can get data from all the dipoles. We have beamforming modes. We have wideband correlator modes and things like that. And so that's the kind of thing that you can do. And Bifrost allows you to do this because, you know, with the single writer multi-reader framework for the rings, it's easy to make branching pipelines. So you can take one data stream and replicate it through mini processing. I probably won't dwell too much on this because Hari did a good job explaining EPIC and what's going on, but I just wanted to point out that this is another use case for EPIC, where we're using this as a commensal system. For Bifrost, using this commensal system to capture data from the F engines out at an LW station and do this kind of real-time imaging. It's also being used for Utmost 2D. So this is work done with Bifrost collaborator Danny Price. So this is an upgrade of Longlow to do FRB localization at about 800 megahertz. And Danny's put together a beamformer and a correlator module that's using the DP4A instructions on the cards to do this. And so they use the correlator to do the basic calibration of the beamformer, and then they use the beamformer to look for sources. He sent me this nice plot of J1644. So this is a single pulse detection here of what they're getting off the telescope. And then the final thing I wanted to mention is that the radio camera initiative is exploring the use of Bifrost for building their ultimate pipeline here. And so the goal for RCI is to build this kind of pipeline that works with data from large N arrays. And rather than taking in data and writing out visibilities, you take in data, you do all the calibration, all the flagging, and then you also go ahead and grid and image the data. And so rather than getting out a collection of visibilities, you get out an image at whatever time cadence you're looking at.
2 minutes, Jayce.
It's pretty cool. And so where are we going with this? So the current development is focused on trying to improve the packet capture. So we're working on a new packet capture framework to make it a lot easier to add new UDP formats to it and be able to capture it. And it's not just capture that we're concerned about, we're also concerned about outputting if you're interested in sending your data to another system. And so trying to make that a lot easier to use. We're also working on integrating this with InfiniBand verbs so that we can bypass the kernel for some of this stuff and get a little bit more speed improvement. I'm kind of excited about the verbs idea because I've been thinking about how you could do kind of an RDMA-based Bifrost ring, so you could have this kind of distributed memory space and make it a little bit easier to bring up multi-node systems. So rather than an explicit packetize and unpacketize operation, you could go to this kind of distributed ring. And the work we also want to do is add an interface for plugins to make it easier for other people to easily bring their algorithms and operations or optimized blocks inside of Bifrost and be able to hook it into the rings, and just an overall improvement of usability. And so I'm happy to say that this work has actually been funded so that we can go forward and continue to develop on Bifrost through an NSF Cyber Infrastructure for Sustained Scientific Innovation grant. And so this will not only help us work on addressing some of these near-term goals for Bifrost, but it also allows us to look forward to domains outside of radio astronomy. So we've been talking with biophysicists about adaptive microscopy methods where Bifrost might be useful. And I think the most important thing that I'll end with here is that this also includes funding for a postdoc. So we'll probably be advertising this fall for someone to help us with this work, and to also reach out to communities like the Casper community and see what their needs are and to help them get started with Bifrost and help us move it along. And this is work that's going to be done at UNM and Long Island University. Okay, and that is all I have. And I'll leave up my final slide, which has a collection of URLs for everything. And we also have a tutorial this afternoon to give you kind of a flavor of Bifrost and its Python API. Thanks.
Thank you, Jayce. Again, we're a little bit over, so if you could take the questions to chat and Slack. Again, as Jay said, there is a Bifrost tutorial later in the day at 19:30 GMT. Continuing now our pipeline theme, Dave McMahon, staff engineer at UC Berkeley, for I guess what is a Bifrost competitor, really, HashPipe. Dave, I'll give you a 2-minute warning. Take it away.
Thanks. Can you see my screen okay? You hear me okay?
Yes.
Great, thanks. I'm Dave McMahon. I'm at University of California at Berkeley. I'd like to thank the organizing committee, virtual this year, I guess, not necessarily local, for hosting or organizing this whole meeting. It's been really awesome. Really been awesome to have this workshop going on. It's really been enjoyable. And the start time is great because it's a little before my usual start time, so I get the same jet lag feel that I would have at a regular conference. So that's really, really special. I'm going to talk about HashPipe, past, present, and future, and get right into it here. I can get my slides to advance. Here we go. So the past, start here. This is a little bit before HashPipe started. This is, of course, the UNIVAC 1 console. I think Dan might have one of these in his garage, but I wanted to put this back in because it's important to look where we started from so we can understand where we're going. This does have a few innovations that I think are still kind of relevant today. There's the ergonomic split keyboard, block subdivision selector, which is, I guess today we'd call a speed heap selector. And it even has a mysterious overflow indicator, not unlike the Casper FFT block. So moving up to more recent times, HashPipe started back as a sort of evolution of existing programs that had already pre-existed before it. There was Guppy, the Green Bank Ultimate Pulsar Processing Instrument, and that morphed into the versatile Green Bank Astronomical Spectrometer Vegas. And then from Vegas came HashPipe. And what made HashPipe different was it was much more flexible than the predecessors. You could run it, configure it at runtime. It supported multiple users per host and multiple instances per user. And when I first shared this with the world at the Casper conference in 2012, I promised that in Q4 of 2012, I would have the threads implemented in shared libraries. And I guess that actually happened because in 2013, I had the threads implemented in external shared libraries as user plugin modules. I showed this exact slide in the middle here. There's some other things here that happened in 2013 as well. But this was a slide I showed, it's still a slide I show for explaining how HashPipe works. It shows the status buffer and the data buffers and these sort of threads as in different colors to delineate what the HashPipe executable provides and what the user plugin modules provide. And as we'll see in a later slide, this isn't exactly accurate, but it's a pretty good overview of what happens. You have data coming in, there's a thread here. I have followed the opposite convention from Bifrost, I guess, where the ring buffers are shown as rectangles and the threads are shown as circular arrows. Go figure. Anyways, the data comes in, the thread receives it, stores it in the data buffer. The next thread in the pipeline processes the completed blocks and fills the processed data into the next data buffer, and so on down the line. With all of the functionality for the application happening in a plugin module, it's not so clear what, HashPipe is really an engine anymore. High availability shared pipeline engine is what HashPipe stands for. But it's not really an engine, it's more of like a framework. And so I don't want to really rename it because HashPipe is such a great name. So I still call it HashPipe. But it's more of a framework, and that's kind of the important thing to know about it, that it's not really an engine itself. It tries to, it abstracts away a lot of the details of setting up a pipeline for the shared memory setups, getting the threads in the right order, so the threads know where they are in the pipeline, setting up the CPU affinity for the threads, and it has a fair bit of networking support to deal with the ingress of networked packets, network data. HashPipe doesn't do much more than that. It tries to stay out of the way and lets the application do what it does. And so all the application functionality, correlators, beamformers, spectrometers, whatever, they come in user-supplied plugins, which are developed out of the HashPipe tree. HashPipe is just a program you install on your system, and then you can develop your own plugin. It's in your own source code repository. You version control it yourself, and you install it yourself, and then HashPipe loads it dynamically at runtime and incorporates it into set up the pipeline for your application. So that brings us kind of up to the present. Here we are in 2021. These are projects that use HashPipe. Some of them are no longer exist. Serendip 6 was at Arecibo, which is in transition now. Greenburst is at Green Bank. Paper became Hera. I think Mitch at BYU and his group's using it with Flag. Fast has some backends that use it. PanoSETI is using it. I don't know if Dan's giving a talk on PanoSETI this workshop, but we use it with the Breakthrough Listen program as well. If you don't see your project that uses HashPipe on this list, please let me know. I'd be happy to include it. This is just a picture of some systems, a test system we have in the lab. This is the kind of system that HashPipe is intended to run on, I guess. It's sort of pretty current, modern kind of hardware. 2 AMD EPYC CPUs. We have 2 A40 GPUs, 2 dual port 100 gig NICs. There's some RAID controllers can go in the middle. It's not populated in here. On the outside edge, we have these NVMe carrier cards that each hold 4 NVMe M.2 modules. This chassis that they're in is very nice. It's a Supermicro chassis. It's 4U. It has the power supplies underneath, and so you get the full width for the cards to go in there. But because the power supply is underneath, it's low clearance here, not much overhead. And so this particular card here is an Asus NVMe carrier card. This is a little bit too tall, and so the normal lid doesn't fit on. And if you use NVLink, I think the normal lid won't fit on either. So they actually, Supermicro actually provides a 1U lid that kind of is a pop-up top, like a pop-up camper or something for your thing. So it turns into a 5U chassis to give you an extra 1U of clearance along the top. But if you stick with these, nice compact GPUs, and you don't use NVLink, and you get cards like this is a Gigabyte Aorus card. This does fit in with this. This is full height PCIe spec, but a lot of chassis have extra headroom, and a lot of card manufacturers kind of use that extra headroom. But the spec is the spec, and this does fit, and this card does fit with the normal lid. So if you want a 4U system with this NVMe stuff in it, it can be done. AMD CPUs are pretty awesome these days. They have PCIe 4 already, so these are all like PCIe 4 all throughout here. Twice as fast as PCIe 3. So it's kind of essential if you're going to do 100 gig, especially dual port 100 gig NICs. HashPipe supports IB verbs. It has a lot of convenience wrappers for it. Before IB verbs, we supported something called packet sockets, which we still, HashPipe still supports. It is, there are convenience functions that are given in HashPipe that kind of make it easier to work with some of these things. So it's a little bit higher level interface to set up this particular data flow for this. IB verbs is very rich and has a lot of functionality. We only use a small sliver of it called raw datagram packets. And so it's a much narrower usage of it. So we kind of can mask away a lot of the other complexity and make it a little bit simpler to use. But the idea is this would be your network thread. Can you see my pointer? I can find the...
Yes.
All right, I don't know where the laser pointer is on this thing. So anyways, the thread is like the network input ingest thread, and it would allocate some packet receive buffers, and then it generates these little data structures called work requests that it posts in, and the work requests have pointers to the packet receive buffers and passes these work requests into the IB verbs library. And the IB verbs library talks to the NIC, and it sets up so when the packet comes in, the NIC will DMA the data directly into the packet receive buffer. It bypasses the kernel completely and goes straight into the memory of the application. Then it puts the work request in this thing called a completion queue. And so the thread just pulls these work requests out of the completion queue and then parses the packet, and it can copy or assemble it into this other sort of data buffer. So this is sort of showing the packets have like lots of little pieces of data in them, and then the bigger data buffer that we're assembling here that may come from multiple antennas or different frequency channels or all of the above kind of gets built up into this giant mosaic of data. It's kind of like another brick in the wall sort of thing. But eventually you get this thing filled up, and this gets passed to the downstream thread where more processing takes place. So that works, and that's all fine and good, but the the copying and the parsing of the packets takes a little bit of time here, and if you don't turn these work requests around fast enough, it's possible, if you have a high packet rate, that these you'll run out of work requests, and they'll be sitting in the completion queue, and then you end up with dropped packets, and that's no good. So the next way to use hash pipe is to, or IB verbs. Thank you. Is to DMA directly into the data buffer itself. So you have a data buffer that ends up getting full of packets that are just packets in random order, but they get filled up. And so all the thread has to do when a work request comes in is just update the pointer to the next slot in the data buffer and then pass it back in. So this is all very quick and fast. And then this whole block of packets gets passed to the next thread, which can do the parsing and the reassembly, or even maybe pass that whole thing up to the GPU, and it would never have to be, this would just be a little waypoint for the data between network and GPU. So then there's one more IB verbs trick that you can do is work requests have the packet receive buffer that does not need to be contiguous. You can use a scatter gather linked list to scatter the parts of the packet to slightly different memory locations. And so, for example, if you want to use, if you have this as your packet structure on the left here with like typical packet header sizes, this is this actual speed packet structure from MeerKAT. You would have these packet offsets, different parts would be at these different offsets, which are not optimally aligned for using vectorized instructions. And so you can use scatter gather lists to insert gaps in here and get these things aligned at offsets that are more favorable for vectorized instructions. So now we're going to the future part. This is very quick. This is, I think Dan has one of these in his garage too. So the future direction is to move the IB verbs to a one network thread into hash pipes. That thing I showed you is actually exists. It's in a plugin that we've developed for Breakthrough Listen, but it has nothing specific to that application. So that could be easily moved into hash pipe itself and become general purpose. Obviously, we're going to try to support future data transports as we get more and more into, they get more and more widely available, supported, and understood by me and others, I guess. Go to PCI 5 after 4. Obviously, that's sort of marching along. So this is the thing that is where I told you we were not fully accurate. It shows this is all living in one thread. All these threads live in one process, I mean. But they don't have to. And the shared memory buffers, they don't live in any of the processes, right? So this isn't part of hash pipe, and this data buffer isn't part of the application plugin. They're just separate. They live in live by themselves. And so you can make these things multi-process. So instead of a thread and all of these threads in a single process, you can have multiple processes. Each
minus 1 minute, Dave.
Pipeline. All right, I'm wrapping up here very quickly. And so then you can have a multilingual pipeline where the processes actually are implemented in different languages like C or Julia or Python. And in fact, Julia has been pursued by our intern, former intern now, Max Hawkins from the University of Alabama, who has made a Julia package that you can call into hash pipe libraries and implement hash pipe threads in Julia, and will interoperate with existing C-based hash pipe threads. And that is super exciting, and the end of my talk. Thank you.
Thank you, Dave. So we still get a little bit of a break. Let's move all the questions to Slack and chat. Thank you to all our speakers, Beno, Gadi, Gerrit, Harry, Jayce, and Dave. In particular, Jayce and Dave, I think, will be key players in the upcoming pipeline discussion, which begins in about 10 minutes. Are there any announcements from our local organizing committee?
No announcements. The discussion is going to be in the same Zoom.
Great. So yeah, that discussion, I guess, will begin in 10 minutes. Sorry for eating into 5 minutes of your break. see you, back in a few minutes. Cheers.
Okay, let's get started on the back end pipeline discussion if enough people are back from the break.
I'm back.
As am I.
Oh, and Ryan is asking if we'll want separate multiple Zoom breakout rooms to have small group discussions at the same time, or if it'll work to be in one big breakout room, and that'll just be up to the organizers of this discussion. So, if you have a preference.
I would vote for one big room so people don't have to choose, and then have sort of like fear of missing out.
Yeah, sounds good to me.
So I guess one of us should take notes. I can maybe share a Google Doc screen to take notes on. I can find it. I don't think any of us have an agenda prepared. Do any of the co-chairs have agendas? I guess we can just sort of dive into like a free-form discussion.
Oh, Dave, one topic I'd like to make sure we address is, I guess, how much attention needs to be paid to optimization in using IB verbs to push the limit. That is, I saw the approach in HashPipe in your talk, and by the way, I enjoyed the talk very much, not simply because it was ribbing Dan, but also just a matter of, IB verbs are featured in the South African approaches for speed to packet ingest, and I think Kodakan is also using IB verbs.
Kodakan, we're still on DPDK.
Oh, okay, sorry. Of course, I don't know what I was thinking.
Having said that, I am looking into IB verbs, but more for the RDMA side of things and less necessarily for the packet capture, because I think DPDK is probably about as good as you can get for packet ingest, but for host-to-host transfer, IB verbs with RDMA is definitely superior.
Would you, not meaning to now dive into something, does that mean that you would be having IB verbs and the current Kodakan approach for packet capture, or there'd be, if you're trying to do RDMA, you'd have to sacrifice the latter?
I'm thinking of that as I would have two network interfaces. So in the case of like an FX design, where you did both the F and the X in GPUs, you might have an F node where one side of it was packet ingest on one NIC, and then you had another NIC that went out to your X engine.
Okay.
Yeah, I mean, multicast is that is an issue. There's also, I mean, I don't know, this is a long and complicated topic for network packet optimization, where I want to go with it.
Have Dave put, maybe you and I should just highlight headings, and then Dave will copy them down.
Yeah, I'm just trying to capture some ideas and topics, concepts, whatever that we can discuss going on. I don't think it's kind of, I think, a free form, open forum free flow of ideas kind of thing. So
I think Bifrost already supports multicast networking, because we use this multicast networking for Epic itself in the Bifrost. And I think Jayce was mentioning about IBWeb's, including IBWeb's capability in Bifrost. I think it was there in Python 2 version of the Bifrost. Maybe Jayce can confirm.
It's there.
So the question about multicastability is not so much about IBverbs or UDP in general, which can certainly do it. But I guess I have a question is about RDMA. And if you do RDMA, can RDMA be a multicast RDMA, or is RDMA too specific between the two endpoints that you can only be endpoint to endpoint?
Okay, so that's an
exact same sort of question, I guess, because MeerKAT has this fantastic multicast backend, and it's very easy to plug in other instruments and sort of participate in this ongoing observation, and it's really convenient from a facility point of view, I would imagine. And so, these other things like GPU Direct are awesome, but maybe they're only useful intra-instrument and not sort of facility-wide, and how does that sort of impact?
Yeah, I suspect, I don't actually know for sure, so somebody should correct me if I'm wrong, but as far as I know, RDMA is pretty specific. I don't imagine that it would work quite as nicely as a multicast subscriber model.
Dave, one topic I'd be interested in is just very rough benchmarks of how these different techniques are, how many bits per second are they moving between a NIC and a GPU, and are they doing that multiple times in a single server?
Yeah, so there's sort of multiple benchmarks, I guess, right? There's like NIC to memory, well, NIC to, let's call it DRAM.
Yeah.
NIC to,
although the one I'm most interested in is, I don't really care if it moves through the DRAM or goes directly. I just really care about how fast can you get data into a GPU.
Yeah, so I've been spending a bunch of time on that question recently. So I do have some numbers, which I really regret having not put together a talk for this. But I can certainly say some of the numbers that I've gotten recently.
Sure.
Dave, well, maybe we should get the topics first, if you guys don't mind, because I think we should. And my third thing was just, can you do that multiple times in the server? Like, what?
Can't get
multiple
back to
instances of NIC to GPU.
There we go. Oh, multiple times in benchmarks.
Yeah.
In one box, I guess.
Yeah, like I think a lot of people want to have, 100 gigabits per GPU, or I don't know.
But this is our parallel in a box, because we're all assuming this is all going to be sustained, like streaming kind of forever, right? So how many per box?
Yeah.
I'd like to add a question. Well, it's a topic, I guess, whether or not PCIe backplanes, where you might have a teeny tiny CPU and then a separate box connected via some whatever SFF cable, enables you to have zillions of NICs and an equivalent zillions of GPUs or DPUs, so that essentially it's the ideal case of the CPU and its memory don't matter, and you're purely dealing with essentially a PCIe network and a bunch of fairly self-sufficient devices.
So peer-to-peer DMA over PCIe?
Yeah, I guess. I think that's not a problem in a unified address, unified memory address system.
I guess that depends on Nvidia's or AMD, whoever the GPU vendor is, the GPU kind of memory model, how open they make that and how.
Yeah, so I think presently the best we could hope to do there would be, assuming that all the BlueField stuff actually lets you access the memory of a GPU directly, then maybe you could do something like that over the PCIe bus. I don't think I got a clear picture of that from the NVIDIA talks today, but it's something that I want to look into more now that those cards are actually coming to market.
So having GPU maybe as a separate topic. I'm glad you went to BlueFields. I was forgetting where I was going. So let's have DPUs version 2x and up as referring to BlueFields as how could we best use those?
So it's okay to have BlueField be a same line as DPUs? Or should BlueField be a separate?
Oh, I meant when I say 2x and up, I'm referring to BlueField numbering. Kind of.
Is BlueField not just the name for the DPUs in the same way that GeForce is the name of a GPU?
Yes.
Okay.
Yeah, I think the only potential consideration there is there's the BlueFields that are purely DPUs, and then there's the X variant of all the BlueFields, which are the ones with the GPUs embedded on them as well. Right. And so that's almost a different technology, right? Because you can talk about DPUs in terms of like BlueFields or the various FPGA products, or Intel now has some DPUs that do like accelerated storage, but they're all going to be separate from your GPU. Whereas the BlueField 2X is really, or the number X is really a special product category.
And I think NVIDIA includes the very important word converged in their description of the 2x and up. So, right, maybe it's a converged DPU.
It's kind of like, I guess, you could put Argume/Rocky here.
Right.
Speaking of converged. I don't know if I want to put this down as a topic, but I would like to just take a moment to trumpet Julia. I think it's really an amazing, has a lot of amazing potential. They compile the code down to the LLVM level, and then from there they go down to native bytecode. But they also have a CUDA package that goes from Julia code to PTX instructions, which is also very interesting.
What are PTX instructions?
Isn't it like native CUDA assembly, basically?
Oh, okay.
Yeah, it's the NVIDIA bytecode, I think, yeah.
Okay. Is 8 enough?
That's probably more than enough.
Yes.
Yes.
These are sort of general questions. Do we want to have anything about specific pipelines that exist today? Like, do we want to have any more discussions about HashPipe or Bifrost specific to the pipelines, or any other pipelines that we have? I guess there's PSR data, which we haven't had any representative of at this particular conference.
PSR data isn't moving past its current packet capture, so it won't be migrating to IB verbs or anything like that. So I think it's probably safe to let it fall into obscurity.
Okay. I was going to ask you, Jonathan, for your insights on that, since you're sort of the person I hear most about PSR data from on a technical level.
Yeah, so Andrew Jameson, who wrote PSR data, has developed now SPIP, which is a Swinburne pulsar something pipeline or something, which has been used on the pulsar instruments on the MeerKAT and all the rest of it. So that is more advanced, but that's sort of a derivative of PSR data or a rewrite or something like that to make it nicer, but I have no experience with it.
Okay, so we could add that to the list, though, I guess. Instead of PSR data, we call it SPIP. And it's different, but sort of the next generation.
Yeah.
And of course, I'm going to make a shameless plug for Kodokan.
Oh, quite, of course. How do you spell it? K-O-T?
E-K-A-N.
Yeah.
maybe we can also add OpenCL based developments that are happening.
OpenCL?
GPUs. Yeah, I'm not sure if anyone is doing that here, but I think that seems to be a good, more generic like cross-platform thing.
So Codecan uses OpenCL internally for some of its projects, but it also uses CUDA and HIP, and basically whatever the manufacturer supports best for the GPUs we're using.
Yeah, the library files. But I think the CUDA libraries are more specific to NVIDIA GPUs, right? So you cannot actually port them or use them with GPUs like AMDs or AMD GPUs or other things. But OpenCL allows that.
Yeah, so OpenCL is one of those.
OpenCL has been used for, yeah, please.
Yeah, so we use I use OpenCL for Chime. And that most of the Chime kernels are written in OpenCL with AMD GPUs. It's pretty rare, though, to use OpenCL for NVIDIA GPUs because it tends to be harder to optimize OpenCL for NVIDIA GPUs. So if you're going to be using NVIDIA GPUs and you're really going to be taking like full advantage of them, to some degree, it makes sense just to go and port your code to CUDA and take full advantage of the instructions that are available there. So Codecan has a backend for doing CUDA, so that's what we do for John Romein's kernels, but we also have a backend for OpenCL, and that's what we've done for the AMD cards.
Yeah, so if you are exclusively, people are going to stick to NVIDIA devices, then CUDA is obviously the way to go because they are always optimized for NVIDIA devices. But if people are looking at cross-platform applications, then I think OpenCL might be helpful. And I think OpenCL is also useful for programming FPGAs in addition to GPUs. Although I don't know if anyone has actually tested them on FPGAs.
We've done a little bit of that with mixed results.
Yeah, I also tried that. Well, granted, this is now going back like 5 or 6 years, so I'm sure it's improved since then. But I could never really get even to the 10% sort of the theoretical performance that the VHDL people could get out of the same FPGAs.
So Xilinx have high-level synthesis tools which they want us to use now, and it would have been useful to have Wesley around. He probably would be able to comment more on this than what I would.
Dave, I think you should maybe stop adding topics because we're down to 4 minutes per topic.
Okay, yeah. That's a good idea.
Maybe we should, do you want to take them in order or what's the best way to proceed?
I think maybe we can combine some of them. But let's just...
I mean, I think I would say let's try and go for the benchmarks, because to some degree, why you would use GPU Direct or backplanes or DMA peer-to-peer is all down to how fast you can actually move data through these systems.
Yeah, benchmarks are important. Just put this in bold.
So I probably can kick us off there to ask, has anyone gotten a GPU Direct sort of pipeline working? And where you to the point where you've exceeded what you can get just using normal sort of copies via system RAM, because we've tried and it hasn't gone particularly well.
I'm a little nervous though, because GPU Direct is used in a couple different ways by different audiences. So could someone define GPU Direct? Is it, for instance, just how is it something that is used only when people are it's sometimes used by people that just want to get data onto another PCIe device from a PCIe device. sometimes people describe it as something that's almost akin to zero copy, which is by no means GPU direct if we try to translate that, functionally in English. So we're talking about something that's not RDMA. It's something that doesn't involve a network. Is that correct?
So NVIDIA seem to have like multiple sort of, it's an umbrella term for multiple things, because there's a GPU direct storage, which from your NVMe stuff that goes straight to GPU. There's also GPU direct RDMA, which includes between your ConnectX NIC to go straight to the GPU RAM without hitting system RAM. And
is that for Rocky and InfiniBand specifically, as opposed to generic Ethernet?
I believe it's supposed to work on Ethernet. That's at least the platform under which we've been testing it.
Ah, well, and I shouldn't have raised my concerns.
I don't know what Rocky is, I'll confess.
Rocky is RDMA over converged Ethernet. So it's basically RDMA over Ethernet instead of RDMA over InfiniBand.
Okay, I haven't heard that term specifically. Yeah, unfortunately.
Jonathan, aren't the Chime people doing that? And don't they get good numbers? They get a pretty amazing number with Rocky moving from NIC to GPU, but I've forgotten what the number is. Do you remember? Oh, maybe not.
Who was it that you referred to, Dan?
Who are the guys at Chime that put that? I think they're getting like 150 gigabits per second into a GPU.
Andre would know that.
Yeah, so we use, we're not using any of these fancy RDMA direct stuff things. So basically what we've been testing is having basically a couple of NICs. We're only running on 40 gig NICs right now, so I need a couple of them to actually saturate a GPU. But what I've been doing is basically doing packet capture with DPDK, and then I copy that to a frame buffer on the CPU DRAM, and copy that into a GPU. And with that sort of process of things, so you have a DMA to system memory from the NIC, and then there's a step where the processor does one read of that memory and then writes it back to DRAM, and then you copy that to the GPU. So you have sort of 2 reads, 2 writes. With that, I can push about 130 to 150 gigabits per second into a GPU. Getting that out of the GPU, if you go to like, say, 10 to 20 gigabits per second out of the GPU, that's pretty doable. If you try and get up to pushing it towards where like it's a symmetric thing, so you actually want to pull all of that data out of the GPU again and then put that back on the network, then what happens is you run into the DRAM becomes a limiting factor. So the utilization of the system, of the CPU's DRAM, ends up slowing down all of the buses in your system. And so then you can only really push something like maybe 70 to 80 in and 70 to 80 out of a GPU, while simultaneously doing all of the packet processing and DMAs to and from the NICs.
Maybe just for simplification, because we don't have a lot of time, I'd be interested in just the number from a NIC into a GPU, because I think it's going to be hard, given our time, to record all these different ways that you move data in and out. And do you have like a single number that you could give us for NIC to GPU?
So NIC to
GPU been demonstrated.
Yeah, NIC to GPU with 1 read-write cycle is safely 130, but it's between 130 and 150.
Yeah, that's great.
With one packet read and write cycle in addition to the 2 DMAs. Using
that's Rocky.
No, that's using DPDK. That's not DPDK, using any sort of. That's just UDP packet capture using DPDK and standard DMAs between your NIC and your GPU.
Great. Well, that's beautiful.
And you can do that per NUMA domain. So with 1 server, you can do that twice if you have 2 NUMAs.
Nice.
But
is there anybody else that wants to add into that 5B column that's got some impressive number that they want to mention?
I can't remember the numbers offhand that we've been getting. But yeah, say 70 gigabit per second sounds like what we've done, but that's just with 100 gig NIC. We haven't really tried with multiple NICs to try to get onto the same GPU.
Sorry, you said 70?
Yeah, we must actually dust off our new PCIe 4 server, because with PCIe 3 that was more or less the limit that we can get from a NIC to a GPU. But with PCIe 4 we'll still see.
James, I seem to remember Gareth getting somewhere closer to 90 at some point. Or am I?
Yeah,
that
was the investigation that he did with the, what is it called now, for the funnel in problem. So I don't know that in those investigations he was actually looking at moving the data onto the GPU. If we're speaking about the same investigation here, James.
Yeah, so 90 sounds like 90 sounds like the PCIe limit. Well, PCIe Gen 3. So like if I run just a copy to and from the GPU, I can get 200 gigabits on and off of the GPU, as long as I'm not doing anything else with the system memory, right? But as soon as you add the NIC and you add a bunch of other system memory calls, then that slows down what the amount of DRAM access that the PCIe bus can actually utilize.
That sounds right, Andre. I think that's what Andrew was remembering there, because I also vaguely remember that.
Yeah, so I think probably what we're seeing is actually a pretty straightforward scaling from PCIe Gen 3 to PCIe Gen 4, because if you're seeing 70 gigabits on, with a network capture on PCIe Gen 3 and probably fewer channels of DDR4 because it's going to be an Intel-based system, then probably I'm just seeing the natural scaling going to PCIe 4.0 with 8 channels of DDR4. And so I've got the extra bandwidth both on the bus and on the DRAM.
Yeah, sounds about right. I mean, the 70 gig was send and receive roughly, because we were running an F engine, so the transmit was a little bit less than the incoming, but roughly the same.
Okay, so that's actually very good, because yeah, send and receive for me is also only about 70 to 80.
That's send and receive off the GPU, not send and receive on the same network link. Is that right?
No, that's send and receive off of the network.
Okay.
Like off the network to the GPU, back to the network.
Mm-hmm.
Through the same port, same card.
Yes. Yeah, in my case, I was using different cards, but yeah, I don't think it matters.
So it doesn't immaterial.
Yeah.
And Andre, your DDR4 memory is how fast?
I think I generally run it at 32. What is it? Like 229 something, 2966 or whatever it is, 2933. Okay. In theory, I think you can go to 3200, but it doesn't actually make a ton of difference. And I like to have servers with like 2 terabytes of RAM, and at that point, it's really hard to hit 3200. They tend to downclock.
Have you found any difference for different like CAS latencies or different types of DRAM? There's these little things when you go to buy them that, like, do these matter or not? I don't know. Like,
I have not attempted to do that level of tuning. It's pretty hard to do actually on servers, because it basically comes down to the module you buy. You generally can't tune the CAS latencies like you can on a consumer platform. So you just have to like try and buy, I guess, high quality memory, but it's like, yeah, it doesn't, there's not a lot, you don't have a lot of control over it. There is a little bit of funny stuff that goes on in the AMD processors. So for example, one of the reasons why I don't see a huge bump in performance between the 2900 and the 3200 is because at 3200, the Infinity Fabric is running at a non-1-to-1 ratio with the memory. And so it adds like weird latencies, and apparently the new generation of EPYC chips, so I'm using the 2nd generation, the Rome chips, and then there's the new Milan chips. And those are supposed to run the clocks at the same rate. So you're supposed to actually be able to get better performance by about like 5 to 10%. But again, they're only saying like 5 to 10% improvement. So there's not huge, I don't think these are going to be life-changing things to play around with CAS latencies and infinity fabric clocks and stuff. It's, you know, it's all within the same ballpark.
Yeah, that makes sense.
Should we move on to a different topic number? Dan's estimate of 4 minutes is haunting me.
Yeah. Thanks. That's an impressive numbers. Congratulations, you guys.
We can talk about, I guess, the InfiniBand verbs optimization and such. I'm not sure what you meant by that initially. Lincoln, do you want to expand a little bit?
I guess I was wondering whether the IB verbs implementation that you sketched out in your hashpipe talk is, I guess, at all affects at all the way you sketched it out. Does that affect at all the speed that one would be able to achieve, or if one made some?
It does, because that's the reason why I changed it. I was taking too long, and I guess I was using an older generation of NIC because I think they can hold, like, you can post more work requests now. The number that you can post is not infinite. It's a function of the NIC that you have, and the older NICs supported fewer outstanding work requests. So I had to turn the work requests around very fast because the packet rate, I was dealing with fairly smallish packets, so the packet rate was fairly high, and so I had to turn them around faster than I was, and I was losing packets because I was not keeping the work requests turned around quick enough. So I said, okay, I'll just do this trick of putting in, DMing them into the data buffer directly and then just turning it around as fast as possible, just update the pointer and put it back. And that was allowed me to keep up because it was just the work requests were not turning around. So it's sort of like, you know, DMA is DMA. It kind of is what it is. I guess there's contention on the bus for that, but that was not what my problem was. My problem was keeping it, the sort of plumbing the mechanism happy to give it enough places to put packets.
Yeah, there's a very similar issue with DPDK. It behaves almost the same way in that you need to give it places to put packets really fast. And if you don't do something with those places, then yeah, you run into the exact same problem.
Yeah, unfortunately, you can have a lot of buffers and you just like change the pointers. You don't have to have, you're not limited to, you know, just if you have n work requests, you don't have just n buffers. You can have like infinite, a large number of buffers. So
yeah, and that is actually something that IB verbs does quite nicely. And one of the things well, this is very aside, but one of the things I definitely want to look into in IB verbs is utilizing IB verbs to basically have your, instead of doing like DPDK, you read the packet from DRAM and then you reprocess it into some format that the GPU would like to look at. And then you send that to the GPU. But maybe in this world where we're DRAM limited, what you actually want to do is just take the packets and put them into a queue, and then have the GPU read the packets and do the reordering step, because that, you know, there's so much bandwidth on the GPU that maybe that's the place to actually put that problem. Alternatively, and the ultimate goal that I have, if you can get the DPUs to work, is that you read the header of the packet on the DPU, and then you take the data and you either DMA that into DRAM in exactly the location that the GPU is then going to read it, or you DMA that data directly into the GPU, which is the sort of ultimate. And then you don't need a CPU and you don't need to be bottlenecked by DRAM. You're at that point bottlenecked by your PCIe switch. Right. And then that sort of backplane world becomes available. And I think in theory, this should be possible to do between different types of hardware once CXL comes out, if it ends up doing what it promises to do. And that's with PCI Generation 5. That would be unified memory across PCIe devices. But that's some years out. And so it's really hard to make predictions about how well that's going to actually work in practice. But that's the sort of thing that keeps me excited, that, you know, we'll be able to build, you know, hundreds or even, you know, thousands of gigabits per second in these servers in the future.
That's just within CLX refers to just inside a server, or among many servers which have one or another network protocol operating between them?
I think CXL is entirely within a single PCIe bus, which granted could extend beyond multiple servers with a PCIe network, but I don't believe it explicitly deals with the networking layer. But I'm not actually sure.
I think there's some standard, like a MPI derivative, like, follow on or something called, it has a G in it for global address space or something like this. And it's this huge address space that spans machines even. And it's just sort of like, it's this virtual address space that spans all the machines. It's more conceptual, I think, and where it maps into your DRAM is all handled through the local host, but it's this weird, I should recall the name, global address space, all that comes to mind. But anyways, it's an interesting concept, because this all we ever do is just assemble these things into these bigger, take little packets and make them into bigger packets and then send them on. And it's sort of like, why can't we just start with the big packet picture to begin with and avoid all this other sort of busy work? But it's never quite so straightforward.
Yeah, well, I mean, I think the one thing that's showing up in industry now that's potentially interesting, not directly to us, but indirectly because of the technologies it'll bring, is this sort of concept of having different memory pools on a server that you can allocate to directly, specifically for things that are like, there's this talk now that people want to have something that is larger than DRAM and faster than NVMe, but and it sort of like lives in this intermediate space. And so there's talk about having these like things like Intel Optane that would live on a PCIe bus, where it's like almost like DRAM, and then you can address it directly and it's really fast to access. And I imagine this is for people who do databases and stuff like that. But it's, and it sort of lives as like an additional caching layer as a device on your PCIe bus. And being able to do that effectively requires something like CXL. And I think that's what's driving it. And it's really just going to be a question of, does this sort of map over in a nice way for us? Can we take advantage of this like we've been able to take advantage of tensor cores? Or do we just end up looking at it and realizing that it can't actually, it was designed for virtual machines accessing remote storage and database people, and was never built with enough generalization to make it useful to us?
Yeah, good questions.
And I think we're just going to have to find that out in the next couple of years. But it's exciting that it might work out.
Yeah,
Tensor cores certainly did.
I always thought of Optane as like non-volatile DRAM almost.
Yeah, and I think that idea is showing up more and more in the enterprise world as something that people want, and they would like to be able to like just add it in as an add-in card. But there doesn't exist the software infrastructure to support that yet.
It's sort of interesting how data itself has, like, just the movement of the data has become like this big factor in the system. Like the compute part has gotten so fast that now it's actually just the moving of the data from point A to point B, even within a system, is like, wow, that's like a real problem now. Like, never had to think about that before.
But it's also a fascinating problem because like the network itself has become so incredibly fast because of all of these core switches that are designed for, these big data centers, that the problem is now actually in the servers themselves. It's in the DRAM, it's in the CPU trying to process the volumes of data that the networks can deliver. And FPGAs now can deliver 400 gig pretty easily, 800 gig. It should be possible pretty soon. So, but now the CPU and the DRAM have just not kept up. The PCIe is keeping up. PCIe is now fast enough to handle quite a bit of traffic. But if you have to backend all of that with a DRAM copy, that's what's limiting us right now. And so that's why I think the whole industry is moving in this direction of let's try and cut out the CPU, right? That's, Nvidia is going with, let's put a CPU and a NIC and a GPU all on the same card so we don't have to go through the CPU.
Yeah. Also, I guess, getting to, sorry, Lincoln?
I was just thinking, so the rest of the community is finally caught up to the radio astronomers.
Yeah.
I guess this is getting to your topic 6 here about the PCIe backplane and external chassis, and just have tons of these things with PCI interconnect and let them kind of do their thing and have the sort of CPU and step back and just let them kind of.
So in a world of converged DPU GPUs, maybe it's not necessary unless there's some cost advantage to doing that. That is to have, I don't know, some AMD CPU, sorry, not AMD, ARM CPU running a backplane with a bunch of PLXs on it. I just don't know whether the products exist out there. Trenton Systems used to make, or maybe still does, make some backplanes with lots and lots of PCIe headers, but they tended to focus more on robust systems for government and military, ruggedized systems, and so they never had the fastest PCIe buses. And they didn't assume that you'd want to use every possible lane simultaneously on this PCIe bus. So if no one knows about a manufacturer, then we could probably take number 6 off the list.
Yeah, I think number 6 is not something that exists today, but that might exist in 2 years.
Okay. I will take that as a compliment that I can think 2 years ahead.
There's external, isn't there external PCIe? Is that, or maybe think eSATA or something like that?
Yeah, so there are lots of, you can buy these boxes, right, where you have a PLX and you've got a, half dozen PCIe lane or slots, and then you've got one 16x connection to a server. And in theory, these things would be great if there was some way to make the NICs and the GPUs talk to each other so that you didn't have to go through the system memory. But as long as you have to go through the main system, they're utterly useless, because you then are limited, you're constricted to the 16x, 8x, or 16x bus that's connecting you to this external box. And so it doesn't do you any good.
Yeah, you want to have all the high-speed stuff happen on the other side of the bottleneck.
Yeah.
But still be able to do control and setup and that sort of stuff through that.
Yeah, so you can buy those boxes today, but they're not useful. They're not practically useful yet. Granted, the BlueField thing is new, and maybe if you can do it, maybe if BlueField can map memory on GPUs, maybe that would actually be useful today. But at this point, I don't know enough. I don't think any of us here, unfortunately, know enough about BlueField to know whether or not that's going to be something that's possible. But I'm hoping to find out soon. I'm going to be trying pretty hard to figure out if you can actually make that work with a BlueField.
Well, let's get to point 7 here. Is it fair to say that BlueField and DPU, GPUs are all interesting and seem to have a lot of promise, but too early to really say much about?
Yeah, I think so. I think we're at the point where, I could imagine that if the DPU does what I think it can do, then we could push way more bandwidth than we're pushing today per server. But I just don't know if they'll actually be able to pull that off in practice. And I think I just need to find some time, or hopefully lots of people will try and find some time to get some of these BlueFields and see if they can make them work.
So for the 2X, it's theoretically almost existing now. The notion that it might be affordable, or more affordable than what you would have to pay if you just have individual GPUs and very smart NICs, is, I think, an open question. And I wonder if anyone has heard an extrapolation from what exists now as to what a BlueField 2X is likely to cost.
Don't know.
Yeah, don't know.
Well, it's not going to be like the same price as the commercial gamer boards, right? It'll be.
Oh yeah, right. It'll be.
So I don't see why we should bother with it if we already have 150 gigabits per second with DPDK. There's really no point.
I'm kind of with Dan on that. I had a look at, okay, granted, this is just list pricing now, but for the BlueFields that are already available, they're kind of a factor of 4 more expensive than the equivalent ConnectX 6. And I don't see that they're going to deliver a factor 4 more performance, maybe 20-30%. I mean, which is nice if you had lots of money to play with cool toys. But
are you referring to the BlueField 2 with no letter after it?
Yes, no, it's the one without the GPU in it. So I would imagine that putting the GPU in is going to be considerably more expensive.
Right. So if we imagine that an A100 costs $4,000 US, I've just made that up, then it might be 5,000-ish or 6,000 for a BlueField 2X. And
Tyro, do you remember the A100's?
I think you'd be looking
prices?
at more like 10,000. I think an A100, well, an A40 is about 6,000 US, and then 4,000 after the educational discounts. So an A100 has got to be at least 8, I think. And so then if you imagine the BlueField 2 cost, and then you get the like cost of unique product, and so yeah, you're probably looking at like between 10 and 15,000 would be my guess.
We've had awfully good luck with RTX, GTX boards, and I don't. I mean, unless cost is not a concern, I don't see why we would use those boards.
I was going to ask one thing of Andre. You were talking about bandwidth on and off GPUs. Do the non-gamer cards still have the Nvidia handicapping them by having only one DMA engine, or is that a topic for the past? Because now DMA engines being doubled up in the Tesla series is just something that's a feature of the past, and I'm out of date.
I think even 1080s have 2 copy engines.
Okay, that's fine.
Yeah, I haven't run into a problem with that. Granted, I've only recently I've been mostly using A40s because that is annoyingly what I can actually get my hands on. So I haven't run into that problem.
John, have you tried your 130 gigabits per second on a gamer board? Or Andre, I'm sorry, not John.
I've tried it in one direction. I had a gamer board very briefly as a loaner, and I was able to get. No, actually, sorry. I know someone who did do a bidirectional gamer board, and I think they got 20. I'm trying to remember correctly. I think it was 20 gigabytes per second bidirectional. So that's whatever, 160 bidirectional. So that's about in line with what I was seeing. With the
we might have some numbers. We've got a 3060 in a server here. We might have some numbers as soon as next week. We just need to actually run the tests.
I'd also be interested in how much power the gamer board burns compared to an A40. I have in mind a system that would be running on solar power, which probably is therefore impossible. And because of that, I'm looking backwards and thinking, gee, the T4 looks like an awful.
So have a look at the A10. The A10 is basically the next gen of the T4. And honestly, if I hadn't bought a pile of A40s, I would have probably been buying a pile of A10s. But they're not. I haven't been able to source a vendor who can actually sell them to me yet. And I don't know if that's because they're an OEM only product or if they're just not available yet.
But right. I think I read it's OEM only, but
also the A4000 is another option too. Just sort of, I think, the Quadro version.
Oh
yeah, it's just the Quadro version of the A40, or sorry, it's the A6000. Is the A40 equivalent? There is an A4000, yes.
Single slot width card. I think that's pretty attractively priced as well.
Dave, what was the last designation? I'm sorry.
A4000. It's a single slot width card.
I'll take a look. Thank you. So.
But yeah, I mean, on paper, like I want to actually play with one of the A10s if I can get my hands on one. But on paper, it's an incredible part. In practice, I don't know how much it can actually sustain the kind of performance numbers that it claims, because it's essentially claiming almost A40 performance numbers in half the power envelope. And I can sort of believe that in the sense that, if you drop the power by half, you should only really drop your compute by like 20-30%. But still, the numbers seem a little bit enthusiastic.
Maybe just clock it more slowly or something too, and so.
Yeah, well, this was one of the things we found in Chime, was that you can often, if you clock your card down or you limit the amount of power it can draw, you don't actually lose performance linearly to power draw. You lose performance sort of, or rather, the power increase is quadratic in the amount of performance you get. So if you double the amount of performance, you end up with like 4 times as much power. And so vice versa, if you cut your power in half, you don't actually end up with half as much performance. You end up with something like 70%. And so, we started out with chips that could theoretically burn, I don't know, it was like 175 watts each. And we brought them down to like 70 watts. But I think only lost about 30% of their performance in doing that.
I was going to ask if you've noticed any performance limits due to thermal ceilings, but I know you water cooled the GPUs at Chime, and so you probably haven't seen that.
Yeah, and I'm still in the early days of testing the A40, so I've done all the throughput numbers, and I've run John Romein's kernels, but that only burns like maybe 10% of the GPU. And once I get all the beamforming engines, then I'm really going to get a sense for how it thermal throttles when I start putting in more expensive operations on them.
We have some 1080s that we're using, and we run them we record data for our observations, and then we do a reduction with the GPUs, and we see the temperatures go up to they sort of rise, reduction starts, temperatures rise up to like 80 C, and then it's just flatline at 80 C the whole rest of the time, and it's sort of like it's got to be throttling itself at that point.
That sounds, Dave, it sounds like the radiometer is measuring 3.6 Röntgens per hour or something. It seems a bit suspicious to me.
I think they're just thermal throttling themselves to stay within a temperature range.
Could be wrong. Yeah, and that's totally fine if all you're doing is gaming and you're okay with dropping frames, or if you're just doing a neural net simulation where you can just wait an extra couple of minutes. It's really annoying when you're doing something real time.
Yeah. So this is with recorded data, so it doesn't matter if it takes 10 seconds or 12 seconds, because it's
so with the old AMD GPUs, I was able to actually fix the clocks, and as long as I kept the temperature and the power in check, then they would stay at that clock, and it was really great. But the new stuff, it's really hard to actually fix the clocks. They just want to do whatever they want to do, and so you basically just have to make sure that your operations fit within this sort of long time frame thermal headroom.
You're speaking from experience with the A40. That is, the HPC quality boards do that, which is different than the HPC quality boards of lore, I guess, and so of 7 years ago. So I just want. Okay, so they are playing trickery, and you can't just manipulate them and force them to your will. Okay.
Yeah. So, I mean, with the AMD cards, you could in the past. You can't currently, which is annoying. Currently, it seems like the only thing that they really want you to change is the power envelope target. So you can tell them, don't burn more than 200 watts or don't burn more than 150 watts. And then within that envelope, they attempt to optimize their clocks to sort of maximize their performance themselves. But obviously there's a whole bunch of variability there, and if they hit thermal headroom, then they won't burn as much power because they're trying to maintain their temperature requirements.
Should we go on to one of the other? I think we have 5.5 minutes. Should we select a topic at random based on voice vote and acclamation?
Sure. Anybody want to make a voice vote or nominate a topic?
I'm curious as to what motivated the inclusion of Julia.
That's me. I just put it in there because I'm typing, so I get to put stuff in that I want. But Julia is actually a really cool language. It's sort of 9 years old now, I guess. But it has some pretty nice features in that it, like I said earlier, compiles down to native instructions.
Yes, you said so, yeah.
And it compiles it sort of at runtime, so it's like a just-in-time native compiler, which isn't unique to Julia, but they do a very nice job of it. And it goes through the LLVM, which is this large compiler suite that has lots of optimizations and things like that. It's geared for numerical processing. It's very convenient to call into C functions from Julia. It's very easy to wrap a block of data in memory with a Julia array. It's sort of kind of like, I guess, what you could do with NumPy, but it's all baked into the language and super easy to work with.
Is it, what communities are using it, or which community?
Data science uses it a lot. So I think a lot of people who use R, for example, the statistical package, use Julia. I was just the other day, they have a whole Slack community, and there's an astronomy channel, and I was talking with some people about some radio synthesis imaging algorithms, and someone's trying to get some CASA data gridded and stuff into Julia, and someone else was talking about some algorithm they have for doing that in Julia. And so there's some name dropping going on with someone said they know Larry Daddario, and anyways, kind of interesting.
Hey, this is Robert Anderson. I just wanted to introduce myself briefly. I'm not a part of your group. I work for MathWorks, and I'm going to be giving a presentation tomorrow. I'm not sure, maybe I'm speaking out of turn here, but so my expertise is in the FPGA and the heterogeneous computing space. And I guess just 30 seconds or a minute, I really want to show you guys something that you might find useful. I know you've got a lot of challenges with some of the MathWorks tools because they don't necessarily apply to open source. If I'm just curious regarding the FPGA related topics, if there's anything I could show kind of from a MathWorks point of view that might help further your causes here. My plan is to show an application that runs on an RFSoC board, something that, I've got some limited beamforming. We've got some pretty high performance direct AXI. Now it doesn't run at 100 gigabits per second. We don't have stuff that sustains that rate, but it'll give you a pretty good performance coming off the ADCs, onto the AXI bus. I don't know if any of that, something that would be relevant or interesting to the efforts that you've been sort of articulating here.
I think that sounds great. I think this is stuff more on the back end, I guess, of things
that's
talking about today.
Yep. Okay.
Robert, you probably know we use Simulink heavily. Almost everybody, all of us use Simulink to compile FPGA designs. And it's extremely useful to stitch all of our DSP blocks together. And then for the I/O, we write our own blocks for Ethernet and stuff. But Simulink is the basis, you probably know, of all the way that we compile FPGA designs.
I saw it primarily with System Generator. The stuff I'm going to show tomorrow is more centered around HDL Coder, which is more or less generic.
Yeah, I think that'd be interesting because we're interested in kind of alternate tools to System Generator and Simulink. So
fantastic. Okay, great. Thank you. Anyway, it's been a really interesting. I'm really enjoying listening to your conversation here. So I'll let it go at that.
Great. I'm looking forward to your talk tomorrow.
Thank you, David.
Should we wrap it up, Dave?
I think that's probably about it. I don't know if Jack is still with us or not. But if not, we can just wrap it up, I think, and get ready for the, I guess next up is the Bifrost tutorial. Thanks, everybody.
Thanks, Dave.
Yeah, thank you, Dave.
So I guess, Jayce, that's you.
It is me, yes. Get set up over here. Okay. Yeah. So what I wanted to do here was go a little more in depth into Bifrost and kind of show people what the interfaces look like and how you actually try to do stuff in Bifrost to try to help people get started and answer some of the common questions that we get here. So everything that I'm going to show today is on GitHub. So we have our tutorial itself published on GitHub, and that's a collection of Jupyter notebooks, and everything in those notebooks should be runnable. So all of our examples you can work with there. And so I just kind of want to give a flavor for it, and talk about what the features are. And the idea is kind of to build up in complexity. So to start with, like what the Bifrost array type is like in Python, and then build up from that to talk about different functions and modules we have inside Bifrost, and then start on low-level pipelines, and then move up to the high-level Python interface, and then also to give a preview of what we're currently working on in terms of improving the packet capture framework.
I wanted to talk about lunch. I still don't know if this truck is going to come by or when they're going to come by. But I'm wondering if you'd be
yeah, so everything we have is on the Liangtian Telescope under the Bifrost tutorial page. So we have our notebooks here. We have 9 different modules that kind of step through it, like I explained. We also provide a Docker image as an easier way to get started with Bifrost. So if you have Docker running on Linux and you have an Nvidia GPU, then you can pull down this container, start it up, and expose it to your GPU with the Nvidia runtime and start it. If you don't have access to a GPU, we also have an Amazon Elastic Compute Cloud image that you can fire up if you have an AWS account, which will give you access to the tutorial, and then you can use their GPUs at this kind of nominal rate here, about 53 cents an hour, if you want to work through the tutorials and get a flavor for what's going on. So before I start, I wanted to talk about how you actually get started installing with Bifrost. So right now, everything is on the GitHub page here, this Liangtian Telescope Bifrost. And so you can clone our latest release, which is this 0.9 branch. And once you have it, there's a few different configuration things that you will need to look through and tweak for your given system to get started on things. Because we don't have like a configure-based or an autoconf build system yet for the system. So I guess the two files that we should talk about here, there's a config.mk file, which gives some basic installation positions, if they're not defined, for where you want Bifrost to actually be installed, and where you want the include files, the header files for Bifrost to be. More importantly is probably this user.mk file here, which is where you set most of the settings of how Bifrost is to be built. So this gives you paths to the compilers, the various flags that you need. If you're doing a GPU-based build, there's this GPU arcs variable here, which tells Bifrost which NVIDIA versions to target for your cards. I mean, so the default here is for a 35 and a 61. So 35 is relatively old. I think the 2080s that a lot of people are using are 75s. So you'll want to tweak this for the cards that you're actually going to be running. And you can, of course, as shown here, you can build for multiple card families, although at the expense of compile time. A little more setup as about where your compute environment lives. And then down here at the bottom in this commented section is some detailed control of how you want Bifrost to be built. So if you want to completely disable debugging, like if you want to build a production release, if you want to have enhanced tracing of what's going on inside the kernel calls, whether or not you even want to have CUDA at all, you can build Bifrost in the CPU-only version, which gives you the ring buffers and access to all the CPU-only features. But of course, you lose all of the GPU acceleration there. And then there's a couple of other options down here which I usually use. So enabling NUMA support so that you can assign rings and other memory allocations to particular NUMA nodes. Hardware lock for doing core bindings and things. So you can bind particular threads, particular blocks to particular CPU cores. And then we also have, in this particular version of Bifrost, there's a VMA option, which uses libVMA to help with the UDP capture. And so these are kind of the things that you would usually tweak when you got it set up. But after you had these tuned for your system, you would run a make install, and then you have access to Bifrost. I guess the big thing that really hits people when they do this is that sometimes you run your make install and your libbifrost library ends up being in a place that's not in your library search path. So you end up with errors like libbifrost.so not found. And so for that, if you run into that, that's a library search problem. So you can either fix it manually by specifying an LD library path as an environment variable, or updating your overall library lookups to find it. Okay, so I think that's really what I wanted to cover with the initial setup here. So now I'm going to go ahead and move into the tutorial. So I have my Jupyter Notebook server running here on my local workstation, and I've just started up the first notebook here, which is this kind of overview of Bifrost and what the Python API looks like. Yeah, so loading Bifrost is as simple as saying import Bifrost here, and that gets everything loaded. And so this gets the core module. It loads all of the C types wrappers needed to access what is in the shared library, and then it also automatically loads some of the more useful modules from inside Bifrost. So the thing that I'm going to highlight here is this kind of Bifrost ND array class. So this is the main way that you work with data in Bifrost. So this is derived from a NumPy ND array class. And so it has all of the, it has similar features to what you get with a standard NumPy array. So you have a shape, you have some kind of data type, but it also has this optional space feature here, which controls where this memory allocation lives, whether it lives on the system, lives on the host, whether it lives on the GPU in a CUDA space, or if you have a pinned memory allocation on the host, which would be a CUDA host here. So we can run this little snippet here. So we're just defining this empty array here. It's a 2D array, which 2 by 4096. Our data type is F32, so that's a 32-bit float, and it lives on the system space. And as you can see, we can print out a variety of things that you would commonly see inside a NumPy array. So if you just print it directly, you get that it's a Bifrost array. You can get the data type stored in the dtype attribute. You have a shape attribute. And then there's also this extra .bf attribute here, which stores the Bifrost specific parts of the class. And then, of course, you can directly print it, and there's not a lot interesting here. So the data types, it can accept NumPy data type, so you can do like a NumPy.float32. But there are also these kind of string data types that are also useful because Bifrost supports several data types that aren't natively supported through NumPy. And so these are done with strings. And so it's typically a letter or two which denotes what the data type is, and then there's some width filled as an integer here. So F32, as we talked about, is a 32-bit float. CF32 is commonly what you would know as NumPy complex 64. So complex float, and then 32 bits per IQ value. So it's 64-bit overall for the entire complex number. There's also signed and unsigned integer representations for 8, 16, and 32 bits. And then we also have complex integer representations. So we have CI4 up through 32. So CI4 it's kind of an 8-bit complex number. So it's a 4-bit integer plus real plus a 4-bit integer for the complex type. And so as we point out here, they don't have a direct correspondence with what you have in NumPy, but they are fairly commonly encountered when you deal with radio data coming from F engines or digitizers. Okay, so you can also use these Bifrost ND arrays to wrap existing arrays. So you can take something that you've allocated as a standard NumPy array and then call Bifrost.ND array with that as the argument and convert that to a Bifrost array and begin to use it with all of the Bifrost tools. So here I just defined this random array of normal numbers, then I convert it to a Bifrost array. And when we run all this, we see that yes, it has been converted and it has the correct size and shape. We haven't explicitly denoted what space it's on, so it defaults to the system space. This is created on the host CPU, and then we have access to the data. And as we print things out down here, we see that they have the same kind of data value there. Okay. And so these Bifrost arrays are also, since they are derived from NumPy arrays, they also have many of the same features that you have there. So you can do direct operations on them. And so here I have an example. We're going to use this data array that we pulled in just now. So we have this in-place addition, and we print it out, and we see that all of the values, let's go ahead and run this. This in-place addition, we see that all the values have been incremented by 2. So our minus 2.3 is now a minus 0.3. And you can do direct assignment. So you can do simple slicing inside a Bifrost array. So we can assign all of the elements on the 0th element of the first axis to be 55. And we see all that happens. Things get a little more tricky when you try to do advanced slicing. And so that is not fully supported inside Bifrost for the Bifrost arrays right now. So whereas you could do something like this here, you could do this slice of all of these rows and columns 1, 3, 5, 7 assigned to 10. If you try that inside Bifrost, you actually don't end up incrementing anything in the array. And so that's something to keep in mind when you are manipulating the arrays, is that they like to have the entire array or entire particular dimension manipulated, and this kind of advanced slicing and indexing isn't fully supported here. And you also, if you want to try to get into the just-in-time compiled game to get something a little more optimized, maybe you're familiar with Julia and you like that concept where things are compiled and run much faster. You can even use things like Numba, which is this just-in-time compiler module, which builds on LLVM to try to come up with optimal code that you can run inside Python. And so we can go through and do this, and this should increment everything by 10. And yes, we see that we've gone up there. Okay, so it's kind of a whirlwind tour of the base data type. So now I want to talk a little bit more about the space awareness for Bifrost, because Bifrost is all about being able to use your data both on the CPU and the GPU in this kind of seamless way, so that you can easily move between the two spaces and do what you need to. So before, everything we've been doing has been on the system space, but we also have this CUDA host and CUDA, which I mentioned before. Okay, and so we can run these here, and so we're creating arrays, and they live in their relevant spaces. So this first one is CUDA host, so this is pinned memory, and the second one lives on the GPU. And in the Bifrost array, the copy method also has this extra argument of the space, which allows you to easily transition these arrays between the different memory spaces here. So if we want to move the original data, which lives on system, over to the GPU, we could say a data.copy and say, I would like this moved over to the CUDA space. And so that will that will send off a copy that moves the data to the GPU, and then that will also send a device synchronization call to make sure that that copy is actually completed by the time the command has returned. Because in Bifrost, we try to do a lot of the access on the GPU as asynchronously as we can. But when we're moving between these different memory spaces, we have to call a sync to make sure that we actually get the data as it has been processed, and make sure that any processing done on the stream it's associated to has actually completed before we move the data back. And so before I was talking about Numba as a way to, increase the performance for working on data in an array in the CPU space. Bifrost has a similar functionality for working on GPU-based arrays, and that's called the Bifrost map function. And so this is basically like a just-in-time compiler. So it uses the Nvidia real-time compiler feature, and so you give it this line of C or C++, and you give it some hints about what everything is. So I want A to be data 4, and I tell it what the axes are, which it should operate over, and then I give it the shapes for which it should operate over. And so then the map call goes out, it takes this, and then it compiles the PTX code needed to execute this kernel, loads it on the GPU, and then fires it off for you. And all of the map calls are also caching, in the sense that you take that initial compile hit on the first time you call a particular map function with a particular line of code, a particular set of axes, and a particular shape. And then after that, you access the precompiled copy. So there's just that one-time hit at the beginning for firing this off. And this is really great if you have something that you need to do, but you're not quite ready to write a full Bifrost block in order to work with your data. And so, and in some cases, maybe you'll get good performance and you'll be perfectly happy with what you get from map. In other cases, it will tell you that if you want, to speed things up, you may need to consider writing your own custom block. And so map is sort of magical that it kind of just allows you to do this really quickly without having to have a lot of thought and express what you want to do on the GPU. I guess the important thing that I should point out here is that all the map code is for element-wise operations. So this is kind of like a one-to-one mapping. You want to do some function on a particular element, and so it's not suitable for reductions or anything like that. And so you need some care with that to make sure that you get the results that you are expecting.
Can I ask a question?
Sure.
So if it compiles and runs a CUDA kernel when you run this cell in the Jupyter notebook, if you were running something that would be continually processing data and you wouldn't want it to be recompiling every time, how would you do that?
Well, as long as you do not change the parameters, so like the shape, the axes, and the operation, it will be cached. And so you only get that compile hit the first time.
Okay, cool.
Yeah, and it's also possible to extend the map functionality, which is something I've been looking at, where you could also extend the map caching so that it's also disk-backed. So that if you have a particular pipeline where you know you're going to use this map function, you can compile it once, load it to the GPU, as well as save the PTX to disk, so that the next time you invoke a fresh instance of the pipeline, you don't even have to compile it there, and you can just load it back to the disk. That's something that's still kind of under development.
Cool.
Yeah, yeah. So that's kind of the basic element-wise stuff. As I pointed out in my talk, there are also other things in Bifrost, like the FFT work, like during FFTs, where you need some amount of setup in order to use them, because with an FFT you need to know how much data you're going to FFT, and if you have a multi-dimensional array, you would like to know which array axis you want to operate over. And so for these slightly more complicated systems, you need these Bifrost modules have an init step. And so you create the module, you initialize it with the parameters which you wish to run the data, and then you'll execute it. And so I'm going to show that off with the FFT module. So we're going to start off, and I'm going to make this time domain signal using a map function. So I'm going to have this complex phase value, and I'm going to assign each element row. So each row is going to be a different frequency, and then each column is going to be a unique time sample. So you can think of this as having an array of 4096 time samples from 16 different antennas. Just get started here, and so we'll run this, and so there's a plot of what the signals look like. I'm just plotting real here to keep the figure relatively smooth. So at zero frequency we have a line, and we see that as the frequency goes up, the period of the oscillations goes down. And so if we want to look at this and FFT it in Bifrost, this is kind of the framework that we would use. So what I'm outlining here is an out-of-place FFT. So the input data and the output data lie in different buffers. And so the first thing I do is I create my output buffer where I want my FFT data to go. The shape will remain the same between the input data and the output data. I would like it to be this NumPy complex 64 floating point number, and I need it to live in the CUDA space, because the Bifrost FFTs are implemented with cuFFT. And so once I have my output destination, then I create the Bifrost FFT module. I create an instance of that, which is called F, and then I go through this initialization step here. And so the initialization step is the input data, the output data, the axes that you want to run it over. I just want to run it over that innermost axis. And then I set this keyword of apply FFT shift, which will tell it that I would like the data reordered so that it's not kind of in the standard FFT format of 0 to Nyquist minus Nyquist to 0. And so this will be minus Nyquist to Nyquist here, just to go ahead and rearrange that for me. And then I do the actual execute function here with the data. I will point out that these arrays here, it's kind of like dummy values, and they're just used to determine the initial layout of the array for setting out the cuFFTW call. And so you only need one init, and you can use multiple executes and change the data inside these buffers as you go. And so you can do that as long as your parameters don't change, like the data shapes or the axes that you want to run over. And so we do an execute, and then we copy the data back to the system so we can look at it. This copy does include that explicit synchronization so that we know that when we get the data back on the CPU, that the FFT calls have finished and that the data has been successfully copied. We fall back to NumPy here to compute our FFT frequencies, and we manually shift the frequency here to account for the fact that we have apply FFT shift set to true in the initialization. And then we can plot up the data here, and we get exactly what we expect, is that the first signal is at 0 frequency, and that we see as we move up, the frequencies increase. And so this is kind of zoomed in. on the plot there. So yeah, so this is kind of like the basics of how you would interact with data inside a Bifrost pipeline, and exposing you to that initial array and that array structure and what all you can do with that. Are there any questions here before we move along to talk about what is actually in Bifrost in terms of things that you can run?
Hi, I have a question about the Bifrost map function.
Yeah.
Do you get to specify the grid to use for that, or is it auto grid itself?
It has some heuristics that set automatic grid size. I believe that there are options that allow you to control that to some degree if you want. But I think for the most part, you can just fire up the map kernel and it will grid it somehow. And it's not guaranteed to be an optimal solution, but it is guaranteed to run.
Cool, thanks.
Okay, so let me close out of this one. Yes, I'm done. Okay, so next I want to talk about what are the useful functions that are inside Bifrost. So as I mentioned, there's a lot of interesting things in there. So we've talked about FFT and we've talked about map, but there's actually several other things that are in there. And so with this, I want to go through kind of what is actually in there and give you some examples of how you would use it and a couple of use cases there. And so I just start off with this kind of long listing about things that are in there. So we have the dispersion, the fast dispersion measure transform, which Hari mentioned in his talk, FFT, which we just looked at, these finite impulse response filters. We have a linear algebra module that wraps cuBLAS for matrix-matrix operations. Map, which we looked at. We have a couple of different packers and unpackers that are available. So quantize is used for moving from floating point types back to integer types for output, if you want to do that. Reduce is the counterpart of map, which allows you to do reductions on data. So if you want to move beyond element-wise and you want to look at the mean of a value across an axis, you can use reduce. We have this database gritter that's based on John Romein's gritter that he came out back with in 2011 that Hari also mentioned in there for directly gridding data. We have a transpose block and then the unpackers. And the unpackers are used from reduced bit depth data like the complex 4+4 bit integers up to like a complex 8+8 or even to a complex float. Okay, so we're going to start off with looking at the reduce function. Okay. Yeah, so reduce, as I mentioned, is for a data reduction. So you want to reduce the dimensionality of an array. And so this is analogous to like the NumPy sum, mean, max, min functions with a particular axis specified for the data. So we're going to start off by making this random 2D array that is 10 by 1,000, and we're just going to move it over to float 32. And then we're going to do a NumPy sum across this inner axis. And we end up with these 10 elements here. And so how we would do that in Bifrost on a GPU is that we would first take the data and move it to the GPU. And then we would define our output data array where we want the reduction saved to. And then it's just a Bifrost.reduce input, output, and then the kind of operation. And so what happens here is that Bifrost compares the input and the output arrays and looks at which dimension has been reduced to size of 1 and then runs the reduction along that particular axis. And it supports a variety of operation types. So there's sum, min, max, mean, and then there are what we call power operations. So that's basically a magnitude squared operation. If you want to do some kind of power detection, either of complex numbers or real numbers. And so we fire off the reduce call here, we bring back the data to the system, and we print everything out. We see that there's agreement between the two here. And then this example down here, I also point out the power sum operation. So magnitude squared and the sum along that, which we can fire off. And so this is great for detecting power, or if you need to, if you have like raw F-engine data coming in and you want to convert to power or some kind of spectrometer mode, you can use like a reduce function there and get to power as well as integrate across the data that's coming in. So as I mentioned, it's looking at the dimensionality of the data and comparing what's coming in with what's going out to determine where to reduce. And so that's kind of, explicitly one axis at a time. But you do have the option to, reorder the data, kind of just change the striding of the arrays, if you will, so that your multi-dimensional array looks like some kind of smaller dimensionality, and then use that with the reduce function. And so here I have an example of doing that thing. So rather than taking the summed magnitude squared across a particular axis, I want the summed value across all of the data. So all 10,000 points here. And so in standard NumPy world, I would say data squared, and then I would sum across that to get the NumPy result. In Bifrost, once the data was on the GPU, I would reshape it so that it was only a one-dimensional array. And so this is a very fast reshape operation, which just changes the striding. And so we're not touching anything with the data itself. We just change that little bit of striding information. And then I create my output array, which is a single element 1D array. And I call it reduce. And then I copy the data back, and I have the same answer. So that's kind of an interesting trick that you can exploit inside Bifrost, is that reshapes are very quick, and so they don't require an explicit rearrangement of the data. And so there are times when you're running on your pipeline that you find it to be convenient to reshape the data and do some operation, rather than trying to keep full dimensionality and using that, because that has impacts with how Bifrost does batching and determining what the grid sizes are and things like that. And so that can lead to better performance or worse performance, depending on what the particular case is, depending on how you set up the problem. And so I guess that's kind of one of the things to keep in mind with Bifrost, is that the setup of the problem does have some impact on the performance. And so you can have a function that runs, but it may not be optimal. And it could be that you can make it more optimal by changing like the data layout somehow, or changing the dimensionality with a reshape, or it could be that the only way to really improve that efficiency is to write some kind of dedicated CUDA kernel and then wrap that inside Bifrost and use that directly. So the next thing I'm going to talk about is transpose. And so this is for doing an explicit data transpose on the GPU. So you need to rearrange your data for some particular reason. You want to swap two axes because it's more conducive for downstream processing. So we provide the transpose operation. So in NumPy, you can find your array. You can have this .t operation here, which is the transpose. That just changes the view of the array in memory. So if you want to make it an explicit copy, which is what happens inside the Bifrost transpose method, you'd call a .copy to make a new array that has the correct data layout there. And so we see that the elements are the same here. Again, on Bifrost, we have to define the input as well as the output array when we do the transpose operation, so that Bifrost knows where to put all the data. And so the setup here is very similar to reduce. It's input, is output, it's input, and then the axes, so the order of the transpose operation that you want to run. So you call transpose, you copy the data back, and you see that things are transposed in the same way. And so I guess one of the interesting things about the transpose operation is this actually on the back end uses the Bifrost map. And so all of the transpose kernels are just-in-time compiled for when you use them and have the same kind of caching that happens when with a straight map call. And so transpose also supports multiple axis transpose. So it's not necessarily just the 2D array case where you swap the dimensionality, which you can really move things around. And so I have a more complicated example here where we have a 4D array and we're flipping all of the axes around and rearranging the data. And the setup's the same, you know, just the trick here is to make sure that your output array has the kind of right dimensionality to match the input as well as the actual transpose operation that you're interested in running. Okay. So the next thing I want to point out is the FDMT module. So this is the fast dispersion transform method, which is very useful for doing incoherent searches of dispersed pulses. This is actually one of the cases where you might want to use a transpose module because the FDMT expects a particular order of the data. And so that may not be what you're getting from your telescope. And so here on this example, let's see, go ahead and run it. And while it's thinking about it, I'll start talking my way through it. So we're going to start off by creating a synthetic dispersed pulse here. So we're going to go with a DM of 1.25, so a very low DM pulsar. And then we're going to define our time and frequency axes here. So we'll have 1,000 samples that span 2 seconds. And then we're going to be looking at a frequency space between 50 and 70 megahertz. You know, so I work with a long wavelength array, so my frequencies stop at about 90 megahertz. That's about as high as I go. And we create some initial Gaussian noise in here with the right shape, frequency by time. And then we manually inject this kind of fast rise exponential decay pulse into it at these particular data axes. So at 100, the intensity is going up by 10 units. At 101, it's down to 8. 102, it's down to 4. And 103, it's down to 1. So this is a very sharp pulse that has some kind of scattered tail, like you would expect from a real kind of single pulse here. And then what I'm going to do is I'm going to apply a dispersive delay to this. So the delay that we experience for a given frequency channel relative to the high end of the band is related to the dispersion measure. And then the differences in 1 over the frequency squared between them. So that gives us delay in seconds. And then we use this numpy.roll feature to kind of simulate what that would be. And in the end, we get this kind of time frequency plot down here, where we see that the pulse arrives at high frequencies first, and then there's this long sweep out that goes like nu squared that sweeps out for the pulsar. Okay, so what we would want to do here is that if we have this kind of pulse, we would use the FDMT module to do an incoherent dedispersion on that, and then in order to return that. In order to remove that dispersion so that we can do a detection on that. You know, so if we can remove the dispersion, then we can sum across frequency and we get a much better detection, and that will improve our signal to noise, and we can say, aha, there is actually a pulse here, as opposed to no, that's just kind of noise or something like that. And so we'll go into the setup here. The FDMT module is a lot like the FFT module in that you need this init function in order to tell it what it's actually working on. And so in our case for FDMT, what it needs to know is how many frequencies we have, how many times, well, how many DMs effectively that we want to try to search, and then it needs some information about the actual frequency setup in order to figure out how to do the dedispersion. And so that's given with a bottom frequency and then a frequency step in between consecutive frequency channels. And so then we can do this execution. So we put in the input data and then it outputs to this kind of search space data. And so the search space is dm as a function of time, and this gives you these kind of classic bow tie plots that people that do single pulse work typically show. And so it basically tells you signal to noise as a function of time and dm. And so where you get a peak is where you are at the right time at the right dm in order to see a pulse. So this kind of easily happens in the FDMT module. You can do this kind of searching directly. And this is also a really good place to talk about where the Bifrost rings come in this, because the metadata that you get with the rings can include that information you have about the frequency setup and the integration time and such, so that you can do the FDMT plots and then know how to correctly interpret them or look at the correct range. Another nice feature about the ring, particularly when talking about this kind of single pulse work, is that you pull data out of a ring in a particular size, but you're allowed to, since you can have kind of arbitrary access inside the ring, you don't have to necessarily step by in samples every time you pull from the ring. So you can read in samples, step by in halves, read another in samples. And so this is a nice way that you could pull in overlapped data. So if you're doing some kind of search like this, you can use that kind of overlapping to make sure that you don't lose an event that might happen to occur at the edge of a data boundary that you are processing. So I guess, yeah. So the last thing I want to talk about here is the linear algebra module. And so this is basic matrix operation. So matrix multiply plus accumulate as implemented with cuBLAST. And so it does not support all of the features in cuBLAST, but it's mainly focused on where you have a matrix plus accumulation operation. So these are the three formats that it accepts. So we can do this first one where you have some kind of scalar times scalar A times B, and then you want to accumulate it onto C. And then it also supports these kind of self-multiplication types, depending on if A or B is not defined. And so you can have it do a Hermitian transpose as part of the multiplication if you so desire. And so you can use these to build up simple correlators or beamformers and things where you can express your operation as this matrix multiplication. And then you have this built-in, ability to accumulate if you want to. And so if you're using a correlator, you can have your first run through it have beta equal to 0, and then have a non-zero beta for other ones, and then use that beta to reset the integrations as you want to control that. Okay, and so here I have an example beamformer, which is done with this matrix operation. So we're going to start out with data in kind of a time ordering that I am used to, or at least the data ordering that I'm used to inside the system. So I would pull data and I'd get so many time samples, and for each time sample I would have some number of channels and some number of inputs for that. And then I define my beamforming coefficients here. So the dimensionality for the coefficients is number of beams by number of channels by number of inputs. And so I can do this all in NumPy with its matmul, its own matrix multiplication array. And I play around with the axis orders to try to get everything to match up so that I get this natural summing over the inputs for my beamformer as part of that matrix multiplication. And then I have some result down here, and I also do it manually for one particular channel and time if you don't happen to trust matrix multiplication for some reason. And you do something similar inside Bifrost. So you define all of your arrays. You also define your output array here. And then you initialize the linear algebra module, and then you call its matmul method here. And so the argument order here is alpha, A, B, beta, and C. And so this will do the beamforming operation. We will copy it back over, and we'll do this axis swap to move things around so that we have time channel beam, which is kind of similar to what our input data format is of time channel input antenna. And so that's kind of a basic way in order to show how that works. And that's kind of all I'm really going to cover here for these core Bifrost features. So as a point out, we also have the FIR filter implementation, Romein. We have the quantizer and the unpacker. We'll look at the quantizer and the unpacker a little bit when we start talking about data transport and data capture inside Bifrost. Okay, so are there any questions on this section?
I have a question. So most of these main functions are for using pipelines that involve GPUs, but if you wanted a pipeline that was just dealing with catching packets streamed from an FPGA very fast, and then most of the processing was done in the CPU, would you also use Bifrost for that?
You could, yes. So you could build a pipeline where you capture data and either directly record it to disk or run all of your functions on the CPU. If you're wanting to go a pure CPU route, then a lot of these things that I'm showing here are all GPU based, and so you'd be thrown back to either using the NumPy counterparts or some other Python module, or writing a dedicated C++ function that you then wrap with Bifrost to do the particular operation that you're interested in.
That makes sense. Do you have an example of using Bifrost to catch packets over the network?
Yeah, that is coming up. That's covered in module 6 here, which I don't know if we'll get to, but
yeah, probably not. I was just curious.
Yeah, so we do have examples of that. The examples on packet capture are using the new packet capture interface that we've been working on. And so in that case, you wouldn't necessarily use the Bifrost that comes from Liangtian Telescope, but I have a fork. Let's see, yes. I have a fork here, and I have a branch called disk readers, which implements the new packet capture interface. And this is all talked about inside the tutorial as well, as to which branch to use, and then an overview of how you actually set it up to use it. Okay, does that answer the question?
Yes, thanks.
Okay, cool.
I got a question, Jayce.
Sure.
These functions that you were just showing, they work with ring data? Or any NumPy arrays, or?
Yeah, they strictly work with the Bifrost arrays. And so when you pull data from a ring, you're returned a Bifrost array.
Okay, and input and output can be GPU or host-based. It's sort of agnostic, but they can't be the same.
Yeah, they can be the same. So you will get out a data array, and then it will be sent to a ring buffer. And so where that ring buffer lives is kind of up to you, if you want it to be on system or GPU or what.
But it can't be. Can it be the same ring buffer that it came from? Like, can you do in place?
No, it cannot be the same ring buffer that it came from. It's part of the single writer thing. Because when you do a read in Bifrost, there's this guarantee operation. So every read sets a lock on a memory space, a memory span inside that ring.
Oh, for like consistency.
Yeah. And so that's to help ensure that you don't accidentally overwrite data while you're trying to access it, and then control the flow of that when you have multiple readers and your writer.
Cool.
Yeah. Okay. Okay, so the next thing I want to talk about is trying to build complexity. And so I've been focusing a lot on the very low levels of Bifrost and trying to do this kind of one-off computation. you know, you have one data array, you want to do something to it, and then you're done here. And so I want to start working towards actually building a pipeline. And so trying to start that way with a simple F engine here in this example. So similar to before, you know, we're wanting to make some time domain data for some number of antennas. And then we want to start having multiple sections of that data. You know, so we want to have samples 0 through n plus 1 to 2n, etc. And so we're going to start off by looking at that in a CPU context. So I define this function called make data, which will give you n time samples from m inputs here. And that returns it here. And if we take a look at what that looks like, so this is all time domain data, so we're going to go ahead and FFT it here just for visualization to see what things look like. And so this is what the first batch of time data looks like. And then since the noise changes across it, then a batch many samples later looks like the blue line here. And so we have some amount of variation. Okay, and so we can do something similar here for Bifrost. So this is very similar to what we had when we got started and looking at how to use the FFT operation. So we create our FFT object, we initialize it, and we do this execution of the FFT. And now since we want to integrate the spectra, we're going to then couple that with a reduce operation. So we're going to take that FFT data, we're going to do a power mean. So we're going to do magnitude squared on the FFT output, and then we're going to average across all the time data that we have to come up with integrated spectra. And then we pull it off here, and we see that things are much smoother than they were in the single snapshot case, because we're integrating up and we're beating down noise. And we're seeing the kind of same structure there without some of the weirdness. And so we can think about trying to extend this to do it multiple times. So now, rather than having this discrete sample of time, we actually are going to have a very small data stream that has 5 such chunks of data, or what we would call a gulp in Bifrost. That's what you read from Marine as a gulp. It's a span or a gulp, depending on who you talk to. So we're going to loop through a collection of 5 gulps. We'll make the simulated data to try to get away from where the data actually comes from. We'll make the data inside the gulp, and then we'll do our FFT. We'll initialize it each time. We'll initialize our arrays, and we'll just kind of naively loop this up. And we end up with kind of a similar picture that we had before. I'm just plotting several more inputs here. The thing that you'll notice here is that this is a relatively simple loop, and there's a lot of things that we're doing that we don't really have to do. I mean, the FFT operation is ready once it's been created and it's initialized, so long as the data doesn't change. So there really is no reason for us to keep making new FFT instances every time we process another gulp. We're also doing the same thing. We keep reallocating the output for the FFT data. So we're not reusing those arrays on the GPU. We just make a new one each time. And then we rely on garbage collection to clean up all of these extra arrays that we no longer need. And we do the same thing with the spectra. And so you can think about trying to rearrange this, and so you have this kind of initial setup where you predefine all of your destination arrays. And then you do your initial setup of the FFT. And so then inside your loop, as you're processing these subsequent gulps of data, all you really need to do is make sure that you can shepherd the data around to where they need to be. Bifrost provides this copy array, which allows you to do this kind of direct copy to a pre-allocated memory space that you need. You do your execute, you do your reduce. Here's another dedicated copy from the GPU back to the CPU to this pre-allocated area, and you kind of end up with the same results. The important thing here is that if you do pre-initialize, it's always a good idea to make sure that you delete what you're done with when you are done with it, so that the garbage collection can go through and clean up some of these extra objects and no longer used memory spaces. as an alternative to that, you can think about doing things in a slightly different way. So rather than pre-initialize, where you say you already know what all the dimensionality is going to be, you could try it in a slightly different, possibly more Pythonic way, depending on who you talk to, where you wrap everything inside these try-except blocks. So now, rather than pre-allocate, you have this try-except block here, and it tries to use that memory space, and then it says, oh no, that doesn't exist. And so it goes ahead and it initiates that memory space with this direct copy, and then all subsequent calls, it reuses that same memory space. And you can do the same thing with the FFT call. You try to call it, it doesn't exist, and then you go ahead and initialize it, and then use that for all subsequent calls. And this is just a different way of thinking about the problem. And it really comes down to whether you're in a situation where you can pre-initialize everything before you start processing data, or if there's some kind of uncertainty in what the dimensionality of the data is going to be, or if there's something that is parameter specific. And so depending on the kind of situation you're in, you may prefer one form over the other. But the goal is the same. It's to try to move everything that only needs to be done once outside the loop, or to make sure it only happens once, so that you can minimize time spent on these things and minimize the memory footprint by reusing memory that you've already allocated. Okay, and so this is same stuff down here, and then at the end, it's very important in this case. It's actually probably more important here to make sure that you clean up all these temporary variables. Because if you are in a situation where your data parameters change and you're inside this loop, all of a sudden you're hitting this statement. FFT is defined, but there could be some kind of data mismatch. And so you end up in an error condition here because the data doesn't actually match how that particular FFT instance was initialized. Okay, and so this is kind of the basic example of where you get to go when you're actually starting to build a pipeline. And so this is leading us to actually building a block. And I've surprisingly used up almost an entire hour now. But that's kind of where the tutorial goes, is taking these ideas and building it up and showing you how to actually put together pipelines here. And so in this tutorial, we talk about ring spaces and how you define rings and resize them and manage them. And in the later modules, we talk about how you actually build blocks. Yeah, so this is all about rings. I'll kind of quickly go through these to try to give everyone a little bit of a flavor of what's going on. This is kind of the block structure. And so it's how you would set up one of these blocks that I was talking about. And so at least on the low-level interface, the Bifrost blocks are kind of implemented as Python threading objects. And so you have this kind of initializer, and then you create this thread that calls the main function over again. And so inside here, you're reading from you're setting up your output ring buffer. You're creating your data parameters. So this is a data generator here. And so then it shows how you loop through how you get data in your output spans and how you write there. And so this kind of builds up complexity for there. I don't know if people are interested in continuing on or if people have other things scheduled, but I'm happy to remain here for at least a little bit longer to talk about Bifrost and provide information and talk about the tutorials. So it's up to y'all.
Thank you. That was really great. I think for everyone who's still interested in staying on the Zoom's going to stay open. But I also know that it's really late in some time zones, and so I just want to make sure nobody feels pressured to stay.
Mm-hmm. Okay. Well, I mean, if people are still interested, I can keep working through the tutorial here, and explaining, how everything fits together. So yeah, so I'll go back to the ring section here. So as I mentioned in the talk, the rings are really the glue that holds the blocks together. and helps move data between the rings and helps ensure that there's data integrity and that things move down the pipeline as needed. And so this is done through a Python instance called a ring. And so rings have names and they have a space. And so the name is part of the kind of performance and information logging that we have inside Bifrost. So we name our rings in order to keep track of who is sending data to who and who is reading data from where. And then the space defines where that ring lives. And so rings can live in all the spaces that the Bifrost arrays can live in. So you have host, CUDA, and CUDA host. And so ring is a section of memory, and you can resize it. So when you do a resize operation like this, it takes in this kind of single value. You can give it a single value, and this is what the gulp size would be. And so this is kind of like the quanta of data, the quantum of data that you would read from the ring. And so this would correspond to what your gulp is. And so this is a size in bytes, so that's the total size of your data. So, for a typical setup that I would use, that's going to be in time samples from however many channels, from however many antennas, coupled along with the size of the data type that you're interested in using. If you give it two values, the second value is interpreted as a buffering factor. So by default, a ring has 4 segments that are of this gulp size, but the second argument allows you to tune that. And so in this example here, we're deciding to allocate 5 segments into the ring. And so you can use this to make larger rings if you want to. Larger rings can help sometimes if you have like map calls or something like that, where you need to be able to buffer some amount of data to cover that initial compilation that you have in a map call. Or if you have some kind of other lengthy initial setup, maybe you need to pre-compute some delays or coefficients that you need in a filter. And so there, having a slightly larger ring could allow you to temporarily cover that without dropping data. So that's kind of the point of resizing. And then, as I mentioned in the talk, the rings are also have metadata associated with them. So it's not just the data. There is a time tag that denotes when that particular sequence of data starts. And then there's also this header that contains all the metadata associated with the ring. And those can be kind of free form for you in Bifrost. If you're working at more of the lower level like this, at the higher levels inside Bifrost, there are definitely required elements, which Bifrost uses to try to automatically determine, how much data you process at a given time, and what the axis orderings are, and what the data types are. So for now, we're going to start, at the low level interface to kind of show you, where everything goes before we get to that high level. So here we're making another ring, which is called another ring. And we're going to use this as an output. So what we do is once we have our ring defined, we're going to create this context manager for it, and we're going to say ring.begin writing. And so what that does is that tells Bifrost that we are about to start sending data to that ring. And so as part of this, we're gonna be defining the metadata and the time tag associated with the sequence of data that we're going to start writing. So our time tags are integers here. Our headers are initially Python dictionaries, and so you can pack all sorts of information in here, and then we just dump it to a string that's been JSON serialized. So with the setup, we then do a ring.resize so that Bifrost knows how much data we're going to be writing at each time, which is useful for making sure that we can get access to those spans inside the ring so that we can write our data there. And then we say we begin the sequence. So we're starting a new sequence in the ring because rings are sequence-based. And we give it the time tag, the header. And then we start reserving blocks in there. We reserve a block and we get a span or a gulp. We have a view of that data there. And so with the span, let's call it just an an 8-bit integer, so we can write to it, and then we put some data into it. And then once we leave this inner context, this inner with output sequence, that data is released to the ring and it's ready to be read by any blocks downstream. And so in this particular example, all we're doing is outputting random numbers. And so if you had run this, you would go through different gulps within the ring, and it would kind of output, it would output which gulp it is in the ring, and then some preview of what that data is. And so that's the basics of writing to a ring. You must make the ring ready. You must provide it the metadata and everything it needs to define the sequence. And then after that, you write to the ring in these kind of reserved sections. Similarly, you can read from a ring. And so for this, it's like an iterator here. So you iterate over sequences within the ring, because the rings are sequence-based. And so the outer loop is that. This is the Bifrost guarantee here, and this tells Bifrost that you want to guarantee the integrity of the data that you're reading from the ring. It is possible to use guarantee equals false if you don't particularly care what happens to that. There are cases when you may want to use that, particularly in the case of like some kind of triggered action. So say you have data that's flowing into a very large buffer, which you use to give you some amount of look back time. And so downstream you have some processing which is looking for events. And so what you can use the guarantee operation do is you can go back to the ring and you can use that to lock that large buffer and then pull out a particular section of data. So that's one case where you might want to change how the guarantee is done. Yeah, so we iterate over sequences here. So in the sequence, we can pull out the header, and we also get our time tag. And so we have information about what is actually in the sequence that we're looking at. We define our gulp size for how much data to read, and then we have this inner iterator where we just iterate over sections of data that we're reading from the ring. And so it's a similar setup with the writing. You have the span, you can do a data view on it to get it coerced into the right data type that you're expecting, and then we just print it out here. And then so we see that since this runs after, so in this particular example, this runs after this one's run. So the first part of the data is actually outside of the ring's boundary. And so we end up only with these last few samples here. And those should match everything that we're getting out of here. Okay, and there's just some explanation about guarantees and things like that. So that's kind of the basics of the low-level ring operation. You open the rings for writing or reading, and then they allow you to iterate through the data. And so this is very similar to what we had in the previous example where we were iterating over the gulps. And so the operations on the data would lie inside this innermost loop here. And then of course you can combine the two. You can create your output ring, and then you could also read from an input ring. And so you get data from the ring that you're reading from, you do your operation on it, and then you put it into the output ring. And then that's how the data flows through the system there. Okay.
I have kind of a maybe Python question versus Bifrost question, but at the end when you use the delete function or keyword or whatever it is to delete the objects, how does that differ from just assigning those variables to none or something like that?
So when I use the delete, so the objects that are exposed from the libbifrost library have destructor functions on them. And so by calling delete, I'm sort of explicitly telling it to go ahead and call the destructor there and that I'm done with it. And I'm not trying to wait on the garbage collector to notice that I'm done with it.
Okay, so it's a little bit more assertive of a delete, like.
Yeah.
Okay, thanks.
Okay, so in the previous example, so we've looked at how we operate with data in the Bifrost framework with the Bifrost arrays and the kind of functions we have. And we've seen how rings operate and how we can use rings to move data between these different operating blocks. So now I'm going to start talking about how you build a pipeline from these pieces that we've talked about. So as I mentioned, in Bifrost, each block is kind of geared to be its own thread. And so we do this with the Python threading module. And so we define these kind of these block classes, which we initialize, and they always have this kind of main function. And then the threading is done on the main function. And that is where all the reading, the processing, and the writing occurs. And so this is kind of what a typical source block would look like. So this one's called the generator op. So we initialize it with the ring that we are interested in writing to, how much data we want to write to, and then we have a couple of other parameters. We have a shutdown event, which is very useful to have on source blocks so that you can tell them to actually stop at some point and have the pipeline gracefully shut down. And then there's also this core option, because I find it's very useful to do explicit core binding on blocks to make sure that they run where I think they should run. And so then all of the magic happens inside this main method here. And this looks very similar to what we had seen in the ring case. For the generator, we open the ring for writing. We define all of the parameters that we need for the metadata. We set up information about the gulp size in the ring, so we know how much data that we are going to release to the ring for each iteration. And then we begin actually processing the data here. So we'd start the sequence with all the metadata. And then while we aren't in this kind of shutdown condition, we just kind of continuously write data to the ring. And so then I have this kind of extra loop step here to try to help simulate what a real telescope would be, that you would have some data coming in at some particular cadence. And so that's kind of limited to whatever cadence that you would have. It's kind of an artificial limit there. Okay, and so this is all the stuff that we looked at before, and this is just a little bit of an explanation of what all the different steps are. Similarly, we can define this kind of writer class here, which is analogous to the read case we're looking at. Again, in the setup, we have the ring that we want to read from, how much data we want, whether or not we want the contents of the ring to be guaranteed while we're working on it, and then we have a core that we may want to bind to. And then again, in the main function, we iterate over sequences coming from the ring. We unpack all the metadata so that we know what to do. And then we just loop over sequences. We look over spans inside that sequence, and we do an operation. And here the operation we're doing is we're taking in the data, we're reinterpreting it as a float 32, and we're changing it to match the shape that we sort of expect, which is kind of time beam channel polarization output. And then we just send it to bytes and write it to unique files. And in order to keep track in time here, we know how much data is coming in, and we know something about the setup of the data from the metadata or the instrument setup that we have here. And so we can forward propagate this time tag that we get from the metadata so that we have this time tag for every span that we process as we go through. And so how you would actually put this together is that you would need a ring. And so what you would do is you would define your ring that you have, and then you would create this kind of operations list. And inside that operations list, you'd put in each of these operations, and then you would convert them to threads here and start them running. And then you would, so since I don't want this example to run forever, I put in this kind of brief sleep before I call the shutdown operation. That's in this initial generator up here, operator, which would cause the event to be set and for this inner while loop to exit here. So that would stop the data flow and then close all of these context managers here. And so if you run that, you see this kind of diagnostic information that we're printing out. We see the start of the sequence. And then we just have the stream of file names and how much data that we're printing to them. And so this is kind of just like a simple way where you can put a source block together with a sync block with a ring, and then orchestrate it with a Python threading module and get it to run and iterate through the data. And so these are kind of, I would say, they're kind of, well, I don't have a good word to describe them. They're a source block and a sync block, but sometimes you want to do something other than just generate data or write data. And so in that case, you would have something like this copy op block here, where you will have both an input ring that you want to read from, and then another ring that you would want to write to. And so here, there's the initial setup, and then in the main function, we have this hybrid of the generator and writer op. We set up that output ring and tell Bifrost that we're ready to write to it. And then we have this inner iterator over the ring that we want to read from. And so we get our sequences. And once we have all this metadata, we can define the information about the output. So we can make the output metadata required to start writing to that output ring. And then down here, we have the loop. We start that output sequence, and then we iterate through the inputs. We read data, and then we write it to the output inside this reserve span. And so when you put it together, now you need two rings because you need to copy from one ring and write to another. So we define a new copy ring, and then we insert this copy op in here after the generator op and before the writer op, and making sure that we hook the rings together in the right way. Generator feeds to copy, copy reads from copy and writes to write, and writer reads from write. And then you have the same setup here, and then you have this kind of extra information, this extra output line that I put in the main function copy op that lets you know that it's actually doing something. And then we have this kind of sequence that we get from the writer arc like we had before. So that's kind of how you would put together things at the lower level inside Bifrost. And this is actually a lot of where I do my work, is kind of at this lower Bifrost level. There is a higher level interface, which, I mean, if you've noticed, there's a lot of boilerplate in these examples. When defining like the generator op and the writer op, there's really the only thing that you're doing a lot of changing on is the main op. And so that's kind of the point of the high level interface to the Bifrost blocks, is to hide a lot of that from the users, so that, if you want to do a quick pipeline, you can say, I want to copy this data and I want to write this data here. And then Bifrost figures out all of the plumbing necessary, what rings are needed, and how to read that. And that's something that is covered down here in the section 7 tutorial, is what that high level interface looks like. But for now, we're gonna stay down on the lower level interface to look at some of the other features in Bifrost and where they're implemented and what they actually mean and what information that you're getting out of them and what's really happening under the hood. Okay, so one of the things I talked about was logging. So Bifrost provides a variety of logging interfaces to try to help you understand what's going on inside your pipeline. So in the previous examples, we could see that we were getting sequence information because we had a printout of what the headers were, and we could see that the writer op was actually writing, but we didn't really have a lot of insight into the performance of the pipeline. I mean, data was flowing through the pipeline, but we didn't really have a good sense of how long each operation took, or really what was going on inside there. And so that's kind of the point of the logging things in Bifrost, is to provide lightweight ways in order to inspect a running pipeline so that you can understand what is going on. And so we're going to start off. This is the copy op that we had before. So this is just a copy and paste of what we had before. Nothing particularly new here. And so the Bifrost logging is done through a module called proclog. And so what this does is this writes everything to the shared memory space. So this this memory-based file system on the Linux host. And so that's where we put all of the performance logging. So it's relatively fast to write to, and it doesn't really bog down any other systems. And so the idea is that, use this proc log functionality to record things as they happen inside Bifrost. And so everything inside this directory is structured by the process ID, the block name, and then what performance or other metrics that you're trying to log. And so for the proc log interface, these are kind of the common things that you will see recorded in a Bifrost pipeline, either explicitly recorded in the low level or kind of implicitly recorded at the higher level. So we record binding information, so which CPU are we on, which GPU are we using, if any. In and out define how the blocks are connected together. So in defines what the in rings are, so what rings are feeding into our block, and out defines what rings are feeding out. Size gives us information about the gulp size, so how much data we're processing at any given time. And then sequence is a way to log what the metadata going through the pipeline is for a given sequence. So if you want to inspect a running pipeline and you don't have any other way to understand what that is, the sequence can capture that. And then finally, we have something called perf, which is where we put all of the performance information for the block. And so that performance information, which I'll get into a little bit better, is one of the ways that we use to look at how a pipeline can be performing. And so these here can be defined at initialization because you know what your input ring is and what your output ring. And this shows kind of the importance of having the ring name so that you can relate input and output for a given block. And we also know the gulp size here because that's one of the input parameters when we initialize this particular block. And so that kind of defines most of what's going on. So the two that are more dynamic are the sequence and performing, the performance metrics. So inside the main, we set our core and we bind this particular block to a core, and then we update the binding information stored in the Bifrost logging. And then we get down into reading the data for each sequence in the input ring. And then we call this update to the sequence proc log, and we just dump the header directly there. So you can look at that. And then down here, once we actually get into the main body of the loop where we're iterating through data, we're writing out data, then we start to hit the performance logger. And so the three things that we keep track of are the acquire time. So how much time does it take to get data from the ring that we're reading to? We have the processing time, which is basically all the time that is not acquiring or waiting to release data. And then we have the reserve time, which is how long does it take us to acquire a section, acquire a span in the output ring that we can actually write data to. And so all of these kind of give you different insights into what's going on in the pipeline. The processing one is kind of obvious. It tells you how long it takes you to get through some given gulp of data that you have, which can be very telling. If you have 10 milliseconds of data and it's taking you a second to get through it, then you have some pretty serious problems in your pipeline. But you can also kind of get that information by looking at acquire and reserve times of other blocks on the pipeline. So one of the things that is looking at reserve time. So if you imagine a pipeline where you have two consecutive blocks, and that first block has a very high reserve time, what that can tell you is that downstream block, for some reason, is having trouble releasing the spans that it's reading. And so you can kind of use this to gauge where the performance is maybe not what it needs to be. And this kind of gives you an idea of where to look. And this information is exposed in our top like utility called like top. which gives you information about the blocks that are running and kind of snapshots of what the acquire, process, and reserve times are. And so all of this is kind of, at the low level, you're kind of responsible for doing this. As I mentioned, at the high level, this kind of happens for you, and you can get some ideas of what's going on. And here's basically everything that I have just told you written out for when I'm not here. Any questions here on a couple of things that we just talked about block structure, hooking things together with rings, or any of the logging that happens?
I have a question, not surprisingly, I guess I seem to be the question asker today.
Yep.
I'm wondering how ring and block reservations work when the rings live on the GPU. Is that still managed by the CPU? Or the rings sort of, how does that all get kind of sorted out?
Yeah, so when the ring lives on a GPU, I think the CPU still manages handling the locking of that ring.
And the kernels sort of wait until they're told to go, I guess? Still orchestrated like marionette style from the CPU or something like that?
So the kernels are kind of limited by the ring structure, right? So if they cannot get a span from an input ring, they end up waiting for that span to become available and be returned. And so that kind of artificially limits it. So you
so they wait on they wait for a block or a span to become available.
Yeah, they wait for a block or span to become available, and then the processing happens, and then at the output side, they wait for the ability to reserve an output span before they will write data.
So they have some awareness, I guess, of lockedness or not locked.
Yeah. The ring keeps track of that and only allows acquires and release as they can actually happen. And so this gives you a fairly tight coupling of the individual blocks. And so if you have a performance problem downstream, it very quickly flows upstream. And you can end up with these very obvious situations where you start losing all of your packets because you have a backup all the way to your packet capture or something.
So kernel runs, it takes input span and processes it and puts the information in an output span.
Yeah.
And then it goes and waits for the next input span automatically, or does it?
Yeah, it goes and waits for the next input span automatically.
Okay. Yeah. And then how does it get the next output span? Does it have to wait for that to be given to it, or does it?
It requests it when it has finished working on the next input span, if that logical sequence makes sense.
I guess it has some autonomy then, I guess, about the sort of reservations of the rings, because it could go through a few rings before it comes back to the CPU side of things.
Yeah. So this kind of gets to the Bifrost asynchronicity model. So the blocks are designed to be asynchronous, but everything inside a block should be synchronous. And so the rings kind of help. Well, you need to make sure that that condition is required, is satisfied when you're working from the rings.
I think that answers my question. Thanks. I think that answers my question. Thanks.
Okay. Yeah. Okay. Close this out. And so the next thing we're going to look at is data capture, since that's a lot of what people want to do, particularly with these online systems and hybrid FPGA GPU systems, is you want to read data from the network and do some kind of processing on it. So as I pointed out earlier, so this is a preview of what the new packet capture interface we're looking at for Bifrost is like. So the original Bifrost packet capture interface supported exactly one input format from our Approach 2 boards. So this is an attempt to try to generalize that to make it easier to capture different kinds of data. And so that's, yeah, so this is what it currently looks like. And so again, we're working on kind of the low-level interface, the low-level Python interface of Bifrost. So things are very similar to what we have, but we have a lot of extra import statements here. So we have a Bifrost address, which tells Bifrost about what kind of port binding that we're interested in doing. We have a UDP socket that we can work with, and then we have this packet capture module, which defines a packet capture callback that we can use, and then the actual UDP capture. And so the address is kind of the typical IP address port number. We create a socket, and then we bind that socket to that particular address, and then we set a timeout value on that so that we can detect when, say, the packet flow stops or something. And so then we can move into this capture op, which is kind of synonymous to what we were looking at before with the generator op, except there are many extra parameters here, and these extra parameters are needed by Bifrost to figure out what data to expect and then determine how to actually unpack that data and organize it into the output ring to get it flowing down the pipeline. And so the common things here are the socket instance that you want to work with. There's a number of sources parameters, so Bifrost wants to know how many sources to expect data from, and this is part of its packet validation scheme. It wants to know what the first source number is. Again, this is part of determining where packet data goes. It wants to know a maximum packet size to expect. And then you have these kind of two options that tell it how much data to work with at a time. So in the Bifrost packet capture, it opens up two buffers of this particular size here, and then it starts filling them, and then once data for a third buffer comes in, it closes out the oldest buffer and releases it to the output ring. So that's kind of the basic setup here for what to expect from the data. There's also this other new method here called seek callback. And so what this is a connection between the Python API and the actual packet capture in C++. And this callback is used to define that metadata header. And so this is kind of a format-specific call. You start off with self, and then you get a sequence number. And for this particular format, you get information about your sequence, your start channel, information about the number of channels and number of sources and things. And so the callback uses that to build this kind of JSON serialized object, which is then passed back into the rings and stored for propagation downstream. And so yeah, this is all format specific here. So what your actual callback function looks like will be a function of what your packet format is. But you know, for all this setup, the actual main block is relatively small. So you define your callback holder, you set the callback you want to use for the format that you're interested in capturing for, and then you set this context manager which runs the capture. So you have the capture format, in this case it's our chips format, so that's 32 4+4-bit samples within a packet. You have the socket, sources, first source, maximum packet size, which we always set to jumbo packets, and then this kind of timing information, and then the callback that you want to use for when you have detected a new sequence, and then the core you want to bind to. And then you just have this inner loop, you just call capture.receive, and it returns you a status about what's going on. And this kind of runs indefinitely until the shutdown event is set. So that's kind of what the packet capture look like. We have a lot of explanation about what the formats are and what all the individual parameters mean, and how you would go about setting this up. So a lot of the,
why do you have to set it to jumbo packets from within Bifrost rather than just when you configure the network interface?
So you definitely have to set it at the network interface. The jumbo packet thing is related to, so this interface is a combination packet capture interface and disk reader interface. And so it can either read from the network or it can read packets recorded to a file on a disk. And so the max size is used to help deal with the disk case, where you don't have a nicely defined packet and you need to make sure that you read the correct amount of data that corresponds to a packet.
Thanks, that makes sense.
Yeah. So we have some explanation here, and then of course we're talking about the disk reader here. And so this is an identical interface for reading from disk as it is from reading from network. It's just that rather than say UDP capture, you have disk reader. And then there's also a couple of caveats about you need extra information because the packets are all mushed together on the disk. And so the formats are slightly different. For chips, you can determine that just kind of on the fly from the UDP capture, but for the disk reader, you need to get a little bit of information, like the number of channels to expect here. So that's what the capture looks like. There's also a corresponding writer interface in the packet writer class, and it works a little bit differently than the packet capture. And so the packet writer is more like the traditional Bifrost functions, like the reduce and the map, where it takes in some amount of data and then it does an operation on that, as opposed to the packet capture, which writes directly to a ring. And there isn't this kind of intermediate Bifrost array that's exposed. But similar to the reader, it's kind of a two-part interface. You have some kind of header info, which is used to populate common portions of the packet headers as they go out, and then you have the actual writer. And so here I have an example where we're writing some data. So this is one of the eldergrade formats, which is a time series voltages that are 8 plus 8-bit complex. So we open up the output file, we define the disk writer here, we create the header. There are two particular values in this format, and we define those. There are two particular common values for this format. We define those with these two calls here. There are other methods that you can call to define other things that lie in the header info. We create a time tag. Since we need to time tag our data, we make up some random data in order to pack in the packet. Since we have complex numbers, this is a NumPy complex 64, but our format is looking for complex 8 plus 8. So we use the Bifrost quantize function. And so we take our input complex float data, we scale it by this factor here, and then we cast it down to this Bifrost CI8 mode. And then we do a transpose to get it in the format that we're interested in for sending. And then we just have this send line here. So the transpose is necessary because the send has this kind of automatic indexing over the inner two dimensions of the output data. So one of them is interpreted as one index to iterate over, and the other one is the second index to iterate over. And so that's encapsulated in the send here. So we have the header info that we've set with the common information we need for the headers. We have our initial time tag, which corresponds to the next to last axis in the output data, and then the step in the time tag as we iterate across the next to last axis. And then we have the value for the last axis as we iterate going on the output packets and the step there. And so then that gives us the output data there. And so this gives you a way to send multiple packets at once and make sure that the relevant metadata is updated correspondingly. And so this can change up to 2 things at once as you iterate through packets. So that's sort of a limitation there, is that you can only change up to 2 as you iterate, and that those are directly linked to the axes in the data that you you send in. Behind the scenes, there's also data type checking to make sure that you're sending the right kind of data out, and that things are occurring in the right sizes. So yeah, that's kind of a brief overview of what that interface would look like that we are shooting for. So the question now comes down to, what happens when you actually want to define a new packet? So we have the packets that we use, and we have a couple of LWA specific formats. And so the process of adding a new packet is going into the C++ portion of Bifrost and defining a couple of extra files. And I characterize this as straightforward, but not necessarily easy in the current scheme. And so I've sketched out a brief flow here. I mean, the basic idea is that you need to tell Bifrost, what the packet looks like, and give it a way to validate an incoming packet, so that you know that it's valid or not. And then you also need to tell Bifrost how to put that packet into an output ring. And so this is the reordering of the data. And then once you have that kind of basic format step, then you need to tell Bifrost how to deal with packets. And so, so this particular part is about letting Bifrost know what a sequence looks like and how to know if the sequence has changed, and then defining what that sequence callback looks like, so that you can go back to Python and then generate the JSON serialized data that you need in order to propagate downstream. And so I've kind of sketched it out here. I mean, if you want a new format, you have to tell Bifrost what the format looks like and what to actually do with it, and when to know that something has changed. And so I've sketched all that out here. Yes, that's kind of the idea of where we're going with the packetizing in Bifrost, both for the capture as well as the output. The other thing I think I should probably point out is that we have this kind of break between the packet capture and the underlying packet capture method. I mean, so as we're thinking about adding IB verb support, that would be changing out the kind of capture code. So rather than saying use UDP capture or something like that, you would just say use verbs capture. And then that you'll have a common interface where you can give it an address and a socket object. And then it will go through and figure out everything that needs to happen in order to use that particular capture method. Okay. Dave, any questions on this one?
No questions from me.
Okay.
Oh, Jayce, I have a question.
Sure.
It's not really within the spirit of a tutorial, but given the development timeline for integration of IB verbs, how long do you think it might be until you have a speed test so that we can assess whether there's any tension with regard to performance of stuff at Toronto?
So the verbs receiver interface is currently in use at our station, Savietta. And so we're using it. That is, of course, limited to the bandwidth that we're getting from our F engines. The work that's missing that I'm hoping to do with the CSSI funding is to finish up the transmit side so that we can also use verbs for transmitting. But in principle, if you just want to do a capture, you should be able to build this particular fork and branch of Bifrost. And if you have a suitable system for generating data, you can just see what happens.
Okay, thank you.
Yeah, well, I guess that also reminds me, I should probably point out that all of this capture and stuff is also multicast aware. So you can give it a multicast address and it will know that it needs to subscribe to a multicast stream in order to capture packets, and it makes sure that all of that happens in the background for you. Okay. And so now we come to the high level, the long promised high level tutorial. So I know everyone's, what?
I'm sorry, I'm gonna have to leave the call, but the Zoom will stay open. And
Okay.
This is really useful. I just have to go now.
Yep, yeah, no problem. Okay, so now we get to the high level Python API. And you will notice that I have momentarily reverted to Python 2 and print is no longer a function, which I should probably fix at some point. So in the lower level interface and looking at the lower level blocks, there's a lot of boilerplate and a lot of setup. And so that's what the high level Python interface wants to combat. And so rather than having these large classes where you initialize it and you have a main function and then you manually set up the threading and then you launch all the threads and then you wait for the threads to complete, the high-level interface wants to deal with a lot of that for you. And so this is kind of what a high-level Bifrost pipeline looks like. And so you have these high-level blocks. And so this is a source block here. It returns some data. You feed it into the next block that returns some more data. And then you kind of feed it through, and Bifrost knows based on what's returned and how this particular block is structured, it figures out which rings to create and then how to put everything together so that when you actually want to run it, you just have to, call this default pipeline that's defined here and then use the run method on it. And so it's significantly more compact as opposed to what we've been looking at before. And it does hide a lot of the implementation details and what's going on. So the limitation here is that not everything in the low-level API has a corresponding block in the high-level API. And that's definitely something that we are also wanting to address with the CSSI funding, is trying to bring the high-level interface to feature parity with the lower-level interface. And then also make some of these more complicated things a lot easier to do, like inter-server communication. And improve like monitor and control aspects going inside blocks. So what happens in going from the low-level interface to the high interface? So when we go back to this copy op example that I've been using off and on throughout the tutorial. So this is just another recap of what that looks like. So we have our init where we set up, and we have our main function where we actually do all the work. And this is all stuff that we've seen before. I don't think anything's really changed here. Inside a high-level block, things are a lot simpler. And so what we do is, we import the pipeline module from Bifrost, and we create a new class. And rather than making it just a generic Python object, we make it a subclass of this pipeline.transform block. And so a transform block is just, it's a block that takes in data and writes out data. That is to distinguish it from a source block or a sync block. And so we have this initial setup. We call the init method of the parent class. And then the only two methods we really need to define in the high-level interface are this on sequence and on data. And so they're kind of self-descripted as to what they do. So on sequence is called when Bifrost detects a sequence change. And you do whatever you need to do It gives you the sequence, so you can pull out the header and the time tag, and you can update any internal structures within your block that you need to. And then the other method you need to define in the high-level interface is the onData method. And this takes in input data and it writes output data. Okay, and so for a simple copy op here, we get the input data, we save it here, and then we just do the simple copy and we return how much data we actually sent out. So that it greatly simplifies a lot of the stuff that we saw in the low-level interface and makes code that is significantly more compact and a lot easier to read going through it. As part of this, you do give up some, you can give up some flexibility depending on how you write things if you want to have very detailed, control of your blocks. But if you're doing, something that's, relatively straightforward, it does not involve a lot of going in and monitoring control aspects where you need to change things. And the high-level interface definitely makes things a lot easier. And so we have some explanation about these. If you want to write a source block that generates data, you would do a subclass of source block here. Source blocks are a little strange since they're mainly geared for things that are reading from files in how they're structured. So they have this kind of required create reader method, which returns something that you can iterate over. It has this onSequence method, which now, instead of taking in information about a sequence, actually defines the sequence. And so you give it accepts a reader and some kind of name, and then it's responsible for generating all of the metadata. It also has this required metadata instance called the tensor. And so the tensor is kind of the magic for the high-level interface. And so this contains information about what the data looks like and how the data are shaped and how you iterate through the data that Bifrost uses to set up the rings, determine the gulp sizes, and hook everything together. So in this case, we have the required elements of the data type. So this is one of these Bifrost data type streams. So just float data here, and then we have a shape. And this gives the data here. And this -1 along the first axis is a key that tells Bifrost that this is what we iterate across with a gulp. So we will read some data from a ring, and it will contain this information, and then we iterate across this. And then we have the onData method here. Again, it's a little bit different from the transform block. We have our reader that generates data, and then we have our spans that we write to. And so we get some data and we write to the output spans, and then we return how much data we have written. And this kind of returning how much data you've written is part of the control inside the high-level pipelines. If you're no longer reading data, then the pipeline knows the data has stopped and can close out rings. Yeah, so here's some explanation about that, talking about a little more about this create reader method and its requirements and what it's supposed to return. And then there's information about how the tensor dictionary works and what all Bifrost looks for in there and how it's used in order to do the blockchaining and get everything to work together. And then, of course, you can have extra information here about scales and units and encapsulate those things so that downstream blocks have even more rich metadata with regards to that kind of information. Okay, and then I guess the final thing is the other side of the chain, which is the sync block. So how you would write data. And so the onSequence is the same as the transform block, but the onData only has a read span. And so it gives you the input data, and then you do whatever you want to with it. And this tells it that there's no output ring associated with this. And so we can define, we've defined, these analogs to what we had before in the low-level interface. And so we just chain everything together here. We make a new generator op on the high-level interface. We feed that into a copy op, We take that output and feed it into the writer, and then we just run the default pipeline, and everything is hooked together. And so that's what it looks like, and it's a lot easier way to write a pipeline if you are interested in doing that, as opposed to low level interface, and you have a problem that can easily map that way. And there are a variety of features in the high level interface, which I'm not going to talk about, which allow you to combine different operations together. So if you have, for example, 3 different GPU-based blocks, you can say, I want to combine these blocks together, and it will run all of the on-data sections together before it releases the data to the output ring. So there's a lot of interesting features there, which aren't really covered in this tutorial here. Okay. Questions on the high-level API?
I'm good.
Okay. So moving on to the final segment that we have prepared here. So this is kind of to give an idea about how you move beyond the kind of blocks that are included in Bifrost. Let's say you have some kind of operation that you want to do, and you're finding that for whatever reason, what's included in Bifrost isn't working for you. Map is too slow. You're using some kind of correlator op, and you would much rather use XGPU or this new Tensor-Core correlator. And so how you would actually get that inside Bifrost. And so, there's a couple of different ways depending on what the problems are. I mean, you could, depending on the problem, you could have a pure Python implementation. I mean, maybe this could work at sufficiently low data volumes for writing, final data output of a pipeline. So you've gone through, you've done your correlation, and you've integrated up for, a few seconds, maybe 10 seconds, and then you can use something like the Python Casa core wrapper to write out a measurement set. And so that's one thing you can do. There's also Numba and Map, which I just talked about. And then I guess the last thing, is if you want the ultimate control in how the data is processed inside the block and control over the kernel, you would write a new module that goes inside Bifrost, and then write the corresponding Python wrapper that goes for this. So this is definitely, something which there are a lot of examples are present in current Bifrost, since that's how most of this low-level functionality is written. So the idea is that you create your new files inside the source directory of your checkout of Bifrost. And ideally, these functions that you write should take in a Bifrost array, the low-level C++ Bifrost array, and then return some kind of Bifrost status code, which is defined in this header file here that sits with Bifrost. Then you'll want to create a C-compatible header file in source Bifrost. The C compatibility is to make sure that the C types gen, which is used to generate the Python wrappers, can parse everything that is inside the header file. And then you update the make file. And at this point, you will get the C++ module inside the Bifrost library, and then access to the C types gen generated Python wrappers, which you could then wrap into a module inside the Python Bifrost module to make it a little bit easier to work with. So that's a lot of steps depending on what you want to do. I will also advertise here that we're working on this plugin system to try to make it a little bit easier. And so instead of doing steps 1 through 5 here, you would need just to do steps 1 and 2, and then the wrapper will figure out how to build the Python interfaces. So long as your code is structured according to its currently relatively strict standards for what to look for. So yeah. But yeah, that's all I've got in the Bifrost tutorial here. I hope it's given everyone a flavor of what Bifrost can do and how you actually do things in it that is a little more illuminating than some of the other documentation we have, which tends to focus more on the high level interfaces. But yeah, as I mentioned, there's a lot of features here. I have focused mainly on the Python side of things. It's also possible to build things on the C++ side and never touch Python if you're not interested in doing that. But that's not really covered here. So
thanks.
Yeah, thanks for sticking around for another 2 hours to listen to me talk about Bifrost.
That was nice. Thank you very much.
Well, I guess I'll do one last call for questions. And then if there are none, I'll go ahead and sign off.
There was a question in the chat about where these tutorials live, but I think someone answered in the chat also.
Okay, cool. Yeah, I think I've been completely ignoring the chat as I've been going on here. Let's see, chat. Yes, that, yep. Bifrost there. Systems, okay. Okay, so I think most of the questions in the tutorial, I mean in the chat, have been answered. Okay.
I guess I have one question.
Sure.
Have you run any of these pipelines through the CUDA profiler?
I think Hari has run things through the CUDA profiler. I typically have a stance where I do the minimal work to meet whatever requirements I need, and as long as it happens, I'm not inclined to try to look under the hood.
Well, it's great if things work the first time out of the gate, but you know, it's
I've done
a recent
most of
convert.
the filing with the NVIDIA profiler. I've also tried using it with the NSI, but that was not successful. But with the NV profiler, I have done that.
Yeah, I think profiling is amazing because you see things that you had no idea were problems, and things you thought were problems aren't that big a deal. It's very non-intuitive, I find, but useful.
Mm-hmm.
Would you say a couple of words about the data formats that you're using or where to go see more information about those? You notice you talk about the metadata on each file, so you're sort of like creating what's needed as you go on the files, but you mentioned a couple of higher level places that was defined or data requirements were defined.
Yeah, so a lot of those requirements typically flow down from when you are either capturing packets over the network or reading some kind of pre-recorded packet stream. And so there, you know, it's ultimately, you know, what the data is. I don't know that there's any, you know, hard and fast rules here. It's just making sure that you're pulling out the right data, the right metadata for your data. So I don't know if there's any fixed format other than having this kind of tensor dictionary in the high level interface. I don't know if that answers the question.
Yeah, so you're just creating the data that's needed for the particular application and counting on the fact that it's in the metadata of the file.
Yeah.
I think the only rule is that things are different at every telescope.
Yeah. I think the only thing that we have not really tried with Bifrost is probably the use of Tensor-Cores, I think. At least I have not tried it, but I don't know if Jayce or someone else has done that. We have used texture memory. I think we're able to do those things, but we have to do those at the CUDA lowest level of the CUDA level coding.
Yeah, yeah. So a lot of the lower level stuff that you would want to try, and more detailed optimizations, that definitely is pushing you into using the C++ kind of CUDA layer, or possibly the plugin wrapper if your problem is well matched for that. Yeah, I think it'd be really great if we could try out the new Tensor-Core correlator, particularly on the LWA, just to see what kind of efficiencies it has. I mean, I'm always looking for ways to try to reduce power usage out at the station. So it's pretty cool.
So I guess the NVRTC that you use, you'd have to use like WMMA intrinsics or something to utilize those?
I'm not entirely sure what all the real-time compiler can do and what detailed level you are. I mean, the impression I have of the WMMA is it's more low level than that. And you have to very explicitly tell it what you want to do. But that's my impression after looking at it for about a week. So.
Yeah, the only thing with the NVRTC is that it's not always optimized. Mm-hmm. It's not really the best kernel that you would get. So if you really want to go ahead and optimize it, then again, you have to step into the CUDA domain.
That's true with any optimization. I think to really, fully optimize, you're going to have to get your hands dirty. There's no way to avoid that.
Yeah. Yeah, if you want to get the most out of every part of your system, you definitely need to be prepared to work to get to the edge.
I think that really has come out pretty well with the EPIC side of things.
Well, thanks again, Jayce.
Yeah, sure, no problem.
I'm going to take off, and I'll see you guys all tomorrow.
Yeah.
Yep.
Okay.
Bye, everyone.
Cheers.
Thanks for sticking around.
Bye.